Hey, everybody. Good morning. How's everyone doing this morning? It is time for some statistics. Let's do this. Let's hop over to the main screen. It is time. Is everyone having a good morning? Waking up, get that Red Bull. It's like, this class is sponsored by Red Bull. I already had my Red Bull. So, good to see everyone here. Stevenson, Nicholas, Ben. Let me turn the sound up just a tiny bit. We'll go one notch higher on that volume. Looks like we're good. We're hitting just the yellow, which I like. So it seems like struggling. No, is it just like the morning? I know what it's like. I'm gonna know what it's like next semester at 7 a.m. in Texas. It'll still be 8 a.m. in Tennessee, but 7 a.m. in Texas. Ooh, that 7 a.m. Texas is gonna be. It's gonna be like, ooh, waking up right there. But it'll be pretty good. I think I've got like a lot of classes on. I think all my classes are on Tuesday, Thursday. I think I'm teaching 3 classes Tuesday, Thursday. Yeah, it's gonna be like different. And then I think I'm teaching one class in the afternoon on Monday, Wednesday. So that gives me like Monday, Wednesday. I think I can sleep into like probably I might like I'll sleep in those days, and then I'll just relax. And then I'll Tuesday, Thursday will be my big days, and then I'll do office hours and stuff. So there'll be office hours and all that good stuff. So if you're taking 474, is anyone hopefully maybe signing up? I know Ben. We used to have 474 last summer. We had it right after this, so I miss it. I miss having 320 and then 474, and people just went straight through. And it was really cool. Like I think I mentioned it yesterday. I had like 6 students, like Raul, who was just talking to Raul. I am, but in the fall, awesome. Well, hey, well, if you're taking it with me, that's awesome. If you're taking it with someone else, that's great. I'm having a meeting with Dr. Lou. Yeah, it's the fall coming up, right? I'm having a meeting with Dr. Lou later today. So if you have it with Dr. Lou is excellent. I'm trying to think if anyone else is teaching it, but Dr. Lou and I team teach it. And so young Lou, and he's awesome. Oh, we did it last fall, and he's so good. He's such a great guy. And it was his first like he had just gotten his PhD, and he's so excited. He's so cool. Um, okay. Oh, well, thank you guys. Well, don't worry. If you take it with someone else, you can still watch our lectures. You can still talk to me. You can still interact. But Dr. Lou is great. I just want to put that out there. Like Dr. Lou, he is very good at communicating the material. He's got a great teaching style. And he and I team teach it. So I'm throwing some big support out there to Dr. Lou, who's also completely awesome. And he and I are meeting later today. So we're a team. Dr. Lou and I were just like, boom, we're like buddies, just like that. Schwarzenegger and what it was not it's not Schwarzenegger. Was it Schwarzenegger? Yeah, it's Schwarzenegger and the guy who plays Apollo Creed. When Predator, you guys know what I'm talking about, Predator, right? Like he's like Dylan, and he's like then they give each other the strongest, best handshake ever. Anyways, memes. What is his name? You said twins. The armor class, you know what I'm talking about. It's like um yeah, Dr. Carl Weathers. Carl Weathers. There we go. Thank you very much. 50 points right there, Carl Weathers. Yeah, and he's in Arrested Development. I should remember Carl Weathers. Yeah, Carl Weathers is awesome. He's a great actor too. He does like acting school in Arrested Development, but Weathers. Now I'm imagining Schwarzenegger and Danny DeVito like doing that. Sorry, Danny DeVito. It was just like Arrested Development is such a great show. Yeah, it totally is. Oh man, 50 points, all this good chat right here. 50 points. If you're talking, it's some thinking Thursdays. We're getting our brain going, but check it out. And I keep hearing maybe it was during mini term we were talking about because Carl Weathers played Apollo Creed, and I think Carl Weathers played Apollo Creed, and then yeah, I'm like 99% certain on that. And then Michael B. Jordan played Creed and Creed's son in the Creed movies, and I've heard those are really excellent. So I need to check those out because Michael B. Jordan is like Black Panther. Like man, he just he, yeah. Can you turn it up? Yeah, let's turn it up right here. Oh, is it gonna work right well? Okay, it's as loud as it goes. And so here we are. Let's do this. So check it out. Creed is good. Yeah, that's what everyone keeps telling me. And I don't watch nearly any movies anymore, but everyone keeps saying that Creed is really awesome. Everyone's like, check out Creed, watch Creed. So I need to watch Creed. Everyone's like, yeah, go check out Creed. Is Creed 2 good? Is Creed 2 good? Heard Creed is great. And then yeah. And you know what I should do? I should watch Creed with my dad because growing up we watched the Rocky movies together. Creed 2. They're both good. I know. I'll watch Creed 1 if I like Creed 1 a lot, which I'm sure I will. Yeah, Rocky is. Oh, then it looks like mixed opinions on Creed 2. Creed 1 looks to be great, and then mixed people might be like Creed 2. It's hard. Sequels are hard. It's like, yeah, it's like the second Thor movie is like, that's not a good Thor movie. Sorry, Thor, but second Thor, Ragnarok, that wasn't Ragnarok, was it? Second Thor movie was pretty bad. Second Creed isn't as good. Yeah, it's like when you do such a good. It's rare that the second movie is like way better. Like Dark Knight is like Batman Begins is great, and one of my friends was recently saying he thinks it's better than Dark Knight. And then you got Ragnarok, yeah, and it's Dark World. That's what Thor 2 is called, is Dark World, and then Ragnarok was great. So yeah, it's hard because like it's like, do you just remake the movie and hit the same beats? Thor Dark World was terrible. Yeah, Thor Dark World is like, it's almost unwatchable in my opinion. It's like one of those Marvel movies where I'm like, this is just one of the worst Marvel movies. Thor Dark World is sorry Thor, but all the Iron Mans. Iron Man 1 is just too good. Cobra Kai, I've heard good things about Cobra Kai. I need to watch Cobra Kai. Iron Man 1 is so good that I think it just dwarfs all the others. Like, it's just like Iron Man 1. Just, I saw it in theaters like 3 times, and just like, that was so awesome. Yeah, forgot Thor. I'm sorry. Let's go to a more happier topic. You ready? Let's go back to talking about what we were talking about yesterday here. We got our fun out of the way. We woke up. We're thinking about some Marvel movies, which is always good. And maybe we'll talk about some Marvel movie data here in a moment, because we do actually have the movie data frame. I don't know if we have in this class. QC. So the ways we talk about correlation is very important right here. So if we look right here, we can highlight that, and we've got direction. So here's the things you should know instantaneously: strength, direction, form, unusual features. I'm sorry, Nicole. Strength, direction, form, unusual features. I want to see it in the chat for 20 points. I want to see strength, direction, form, unusual features. You should know those just like this in your head. People often get them confused with things like the shape center spread of just a univariate distribution. Boom, Brad 50 points right there, and Sarah and Brendan. Everyone else gets 20, but they were first. So strength, direction, form, unusual features. The direction is literally just positive, negative, or mix. Doesn't matter what you call the other ones. Like neither, not really well described, but positive, negative, neither. That's direction. That's super easy. And then we've got form. This is where it gets more complicated. This is where people start to get lost with the form. When it comes to form, there's 2 types of form. So you want to have in your notes that there's 2 types of form. We've got linear and not linear. So it's like well described by a line, not well described by a line. And not well described by a line could be anything that bends. Like, it's not like, here's a line. This pen's a line. This pen can't bend. So if we have a bend, that is not well described by a line. And so you can see here that within nonlinear, as in within nonlinear, there's 2 things it can be. It can be monotonic, and who for 50 points can remind us what monotonic means? It's your favorite band. Which favorite band again? What's monotonic mean? Your favorite band, 50 points, first person. One Direction. Sarah right there, 50 points right there. So monotonic means One Direction. So 20 points everyone else. You can get up to 200 points today. Keep going, keep getting those points. So and remember, if you're chatting, even if you're late on the answers, you're still getting those stream up points. Like just by chatting, just by being here, but just by watching, just by chatting, you're getting those stream up points. So keep watching, keep chatting. You're still getting those points. Oh yeah, and stream up should be awake. We'll see Henry. Henry gets another 20 for checking the points right there. I'll make sure, because I think I didn't turn it on in the background. Let's see if it does it without Brian. We'll see. Streamers, you awake? Streamers, you there? Yes, it is. It looks like I don't have to go to the webpage when I turn on. Like I'm still like, whoa, Ben, crazy points, Ben. So we have here things are monotonic if they go in one direction and non-monotonic if they go in multiple directions. So pretty easy. Strength. This is exactly where we stopped off yesterday. Strength is the vertical scatter. So when you think about strength right here, do not blend the other topics. This is where people make mistakes, is when they talk about strength, they start blending the topics together. And they start to say things like, oh, this isn't strong because it's not linear. Like, oh, this isn't strong. No. We've got, I think, a lot of graphics coming up right here that show that strength is just the vertical scatter. Like, I can't make this more clear than highlighting it 3 times to be like, I'm going to highlight this multiple times right here, if it'll let me. I'm just going to keep highlighting it. I have to highlight more each time. Strength is the vertical scatter. Can't make that more clear than ever. Streamlabs, good job. You get a 1,000,000 point Streamlabs. So strength is the vertical scatter. What do we mean by vertical scatter? We literally mean these red lines. Is it the density of data, like making it darker? Yeah, pretty much. Jonathan, 50 points right there. It's how tightly clustered it is. And so to put it another way, it's how tightly clustered it is around the form. So it's how tightly clustered it is around the form. So do we have the examples in here? Here we go. So which of these, graphics 1, 2, 3, or 4 is the strongest? Graphics 1, 2, 3, or 4. 100 points first person right answer. Graphic 1, 2, 3, or 4. Which one's the strongest? Ooh, Brad. Brad got it. It's graphic 1. You might be wondering, how in the world is it graphic 1? Graphic 1, which can I get a nice view on it? There we go. Graphic 1 is perfect parabolic. Every point is on a perfect parabola. Graphic 2 is pretty strong. Graphic 3 is the second strongest, but you see there's some vertical scatter. If you notice the vertical scatter, it's still pretty tighter on its form. It's very, very strong. 200 points, max points today. 200 points, max points. Good question right there. Austin, 50 points. So we go right here, and you can see graphic 4 is the weakest. Graphic 4 is the weakest because it is just spreading out. It actually has a change in the strength, which we don't really like. But if you notice, it goes and spreads out further. So it starts out very strong, and then it gets weaker, and then it gets stronger again. So you can see the strength over here and the weakness in here, and the strength, not like Schwarzenegger and Weathers right there. Just that's some strength right there. So there's the epitome of strength. So we go right there. We've got this. Let's go back a little bit, but I like that right there showing it. And you can also see strength. Now, be careful. I'm just showing this off because I really like the plots. The weakest correlation we have here is a correlation of 0. Now, this one is weak, and it's also a non-existent correlation. If you look at like a band put through here, it's the weakest. If you go over to this one right here, it's a lot stronger because it's a lot tighter. So you can see it getting stronger. But we'll talk just a moment about what this correlation means specifically. We've got one more thing to cover in here. Okay, unusual features. So when we get to unusual features, what we have are 2 unusual features. So let's just review. Direction can be positive, negative, or a mix of directions. Positive, negative, like it goes up, then down. So we've got direction. We've got form. Form can be linear or nonlinear. Inside of nonlinear, you've got monotonic and non-monotonic, meaning one direction or not one direction. And then you've got strength, which is the vertical scatter. And have these on note cards. If you use note cards, this is a great way to put these on note cards and be like, strength, the vertical scatter of the scatter plot, like how tight the vertical scatter is. Like, know these things pretty well. And then we have unusual features. In unusual features, you'd have 2 note cards. You'd have heteroskedasticity. And I really like the heteroskedasticity word. Let's hop over here to the main screen. Heteroskedasticity is probably the funnest word to say because we can do homoskedasticity or heteroskedasticity. And when we look at homoskedasticity versus heteroskedasticity, we have to understand what these words mean. So there's heteroskedasticity, and here's homoskedasticity. So what does, right above my head. It's like the hardest word to spell. I think I can spell it right. Homoskedasticity. Did I spell it right? Oh, it doesn't even like it. Google's like, that's not a word. I think it's right in the chat right there. And it didn't like it. It put the underlined bar around it. It said, nope. But I'm like, wait, it's on the screen. I'm showing it. It does exist. Google Googled it. And look, we'll go back to the main page here. Here it is right here. Heteroskedasticity, homoskedasticity. So what does the prefix homo mean? What does the prefix hetero mean? So what do those prefixes mean? Knowing the prefixes will help you out right here. Like, what does homo mean? What does hetero mean? Same. Yep. So when you see homo right here, it means same spread. When you see hetero here, it means differ spread, like differing spread. Like there's a different spread. And when you look at these graphics, which are very, very tiny, I don't think we can get any bigger on them. So if you notice, this is a heteroscedastic relationship here because it changes spread. It has differing spread. This is the only homoscedastic one. And we could scroll down here just a little bit. Yeah, there we go. They're showing homoscedastic, heteroscedastic. And yeah, it's right below there. There it is. And do we have another good? This one's kind of homoscedastic. So it's keeping about the equal spread. They're showing it with the bars right there that it's got about an equal spread. And here we go. Oh, it looks better there. Yeah, you can see it right here. I like the coloring they did on it. So, oh, this is a great homoscedastic relationship. Yeah, they're being like, this is a perfect homoscedastic relationship. And, oh, there you go. There's homoscedastic, there's heteroscedastic. They didn't label it below. But obviously, they're showing you that the good one is the homoscedastic. And let's talk about why that is. Let's talk about why we want a homoscedastic relationship. So, why do you want it to have the same spread throughout? Because the spread is the what of the relationship. The spread is the what of the relationship. The spread is the what? The vertical scatter, the strength, Sarah, 50 points right there. It's the strength. That's exactly right. So we want it to have Corbin 50 points. It's the strength. So you want it to have equal strength throughout. This is what they call unequal variances or stuff like this. We called it in Stat 201 the plot doesn't thicken. So if you remember in Stat 201, Ben, just a moment ago, we talked about the plot doesn't thicken. We don't want to see this where we see this expanding outward. That's plot thickening, where it's like really strong down here at the bottom, gets weaker, weaker, weaker. So that's a heteroscedastic relationship, and we don't want to see that. This one is heteroscedastic and has outliers or maybe some nonlinearity because it kind of bends up, like it kind of goes this. So maybe there's some sort of like nonlinear heteroscedastic relationship. So you get to sound really smart. You'd be like, oh, there's a nonlinear heteroscedastic relationship. And they're like, can you speak? And I'm like, I don't know what I'm saying. This one right here mostly seems to have outliers right here. So if you look at the outliers right there, that is really, really big. And one of the things we like to point to, and I'll talk about outliers here for a second, is this will be throughout the lecture, you'll see. QQ, yes, exactly. It really is that. We want to do, when we do regular old regression or when we do correlation, QQ straight enough, no outliers, plot doesn't thicken. So we want it to be a straight enough relationship. And let's open up R real quick, and let's look at something really cool right here. So let's do this. Let's open up a new script for today. So one of the cool things we have is inside of reg class. Let's go one bit. Library starts with an L. Inside of reg class right here, we're going to use core demo. What correlation demo does is it actually does correlation for you and does a demo of it. Oof, that's... Oh, okay, there we go. Look at that. Now it looks normal. So look at this right here. The correlation is perfect. Does everyone see here? Correlation and the plot thickens. I should say that. Then and I'll tell you why I say plot doesn't thicken. So the notes a lot of times say plot thickens, but I guess it makes for a better joke when you say plot thickens. I do agree with that. But the condition would be plot doesn't thicken because we don't want the plot to thicken. We want the plot to have about the same thickness throughout. So the goal is that the plot would have equal thickness. Sorry. The plot would have about equal thickness throughout, which is our goal. And so if you look at this, this is a pretty good relationship right here. But watch what happens when I add in one crazy outlier. I need it to vanish. With this one crazy outlier behind me right here, the correlation of 0.91, which is a very strong correlation, is all of a sudden going to go, whoa, whoa. First person to type in the chat gets 100 points. What did the correlation become? Here's it without the dot. What did the correlation become? Here, I'll show you it again. Ready? Boo. Oh, okay, I changed the answer. I'll try to make it the same answer. No. Griffin is right. So you're right. Griffin got the 100 points right there. So if you were watching along, the correlation went from this right here to 0.17. Of course, yes, I'm not trying to change it. I can't make it the same anymore. Eventually. There we go. Look. Oh, it's exactly what it was previously. So yes. And here we'll end this. We'll redo it and watch this. Okay. So now I'm going to do the following. And these are answers to your next homework. These are answers to your next homework. So be watching or remember where this is on the video. Like, wait a minute, Brian did these. So that was a point making a very strong correlation weak. But watch this. if Brian makes a box, what is the correlation of a box? Like if I make just like a square like this, like it kind of looks like this. What is the correlation of that object? Like think, what's the correlation of this object when I make it? 0, Austin, 100 points right there. We're going crazy. And whoa, I did it. Do you see the correlation up here? The correlation is 0. If I put 1 point way over here, what's going to happen to the correlation? I could put more points in here. Like I'm just kind of making this circle and filling it out with a bunch of points, and it's basically 0. Like, don't be like, well, it's slightly negative. Be like, okay, well, I'll fix that. I'll fix that. There we go. It's 0 again now. So this is just a filled in box right here. Yep, core demo. Yep. Right there. Sorry. Great job. Hey, who did that? Jordan, 100 points. Thank you, Jordan. I didn't see, was there a question where someone said, how do I do this? Yes, Jonathan, 100 points, and Jordan, 100 points. Jordan, thank you for answering a question. I missed it there. I was looking at the plot. And then everyone's saying this will increase it. Watch as the correlation becomes almost 1. This one red point right here, changed a correlation that was 0 all the way up to 0.92. Why do we say no outliers? Why is it QQ straight enough, no outliers? It's because 1 point, one extreme outlier could drastically change it. And that's why we say no outliers. It's not like, oh, QQ straight enough, no outliers. I mean, yes, no, I love it. I love QQ straight enough, no outliers. Like, it's just like it's a serious thing. It's because if there's an outlier, that outlier might be dictating the whole. Exactly. Outliers have a big impact. Nicole, 100 points. Tons of people are going to get their 200 points today. That's exactly what I want to hear is like, that's what you should know is like outliers can have a huge impact on it. They can make a positive correlation negative. They can make a negative correlation positive. They can make a weak correlation strong. They can make a strong correlation weak. They can make a non-correlation correlation. So what can outliers do? 8-letter word, 100 points first person. What can an outlier do to a correlation? 8-letter word, 100 points first person. What can an outlier do to a correlation? What do you put a lot of points in the top right? Oh, it'll make it super strong. Great question. 100 points right there. I like that you asked that. It'll just make it stronger. I don't know if it'll eventually become 1. It's like so close to 1 now. What can an outlier do? What can an outlier do to a correlation? 8-letter word starts with an A. I'll take strengthen. Sarah, 100 points. Strengthen's one of the many things it can do. No, Sarah, that's a good answer. That's a good answer. It's like, yeah. It can strengthen it. It can weaken it. It can make it positive. I'll take it, Griffin. I'll take that. It can. We don't really think of normality with this, but it can. I want you to think like, okay, I've named so many things. An outlier can do this to correlation. Note you should have is that outliers can do anything. Anything is possible. Anything. Is that 8 letters? Someone's gonna be like, Brian, that's 7 letters. I'll be like, oh, I don't know how to count. But outliers can do anything. Exactly, Jonathan, right there, 100 points. They can do anything to correlation. 20 points, everyone else. Great job. You should have that in your notes that outliers can do anything to correlation. Anything. They can make a positive correlation weak, a weak correlation positive, anything. Outliers can do anything to correlation. Is it easy to be in R and delete those outliers? Kind of. And that goes to a big discussion, like what do we do with outliers? Don't immediately delete them. Outliers require additional consideration. Like when you have an outlier, you think about what to do with it. You like say, should I remove this? Should I do the analysis with and without it? You don't just delete outliers. You don't instantaneously remove outliers and be like, okay, I'm just going to delete my outliers. It just depends. We do have the option of considering a log plot. I think this is in your assignments a little bit. You just take the log of the variable and you might get a better plot. Transformations are some of the hardest things to do because it's like, what transformation do I do? I don't know. I really don't know because there's tons of transformations, and transforming the variable changes the units. So you can see here where we have the sales and then we have the log 10 of sales. And it's going to pull in these values. It's going to cause a different spread to the Y. And it's an option. And it's used a lot in like finance or accounting, especially when we're dealing with large amounts of money. If you take the log of it, there might be a better relationship with the log of Y and X than just the regular values of Y. So it's an option. It's used in many disciplines. And if your discipline uses it, definitely understand when your discipline uses it. It's a very big option. Association is and this is something we should know also, is that correlation is a special type of association. Association means that if we know Y, or excuse me, if we know X, technically if we know Y, if we know X, it gives us information about Y. Knowing one variable, specifically X, because that's the one we say explains Y, gives us information about another variable. And this is like the 10th time you're hearing me say it. It should be like association means if we know one variable, it gives us information about another. I need to put this definitely as like a multiple choice on the test. Like, what is an association? It's like when knowing X tells you everything about Y, when knowing X gives you information about Y. And it'd be the latter. It doesn't mean it tells you everything. So I'll throw in some tricky ones right there. But if you see this as a multiple choice on the test, literally the answer is going to be as close to possible as. An association is when knowing X, and it says narrows down, I think right there, I bet it does, but it says narrows down. It narrows down, there it is. That's Petrie's wording. Yep, when X gives you info about Y. Yep. It doesn't have to give you everything. Nicole, on fire. You're at your 200 points, but keep commenting, Nicole. Keep commenting. But that's awesome. I love the notes in the chat. When knowing X gives you information about Y. Boom. Narrows down the values, gives you information, helps you understand what Y could be. It's like, I know this. That tells me something about this. It doesn't mean you know the answer, but it means like this is more possible. Like, let's say you know your team just recovered a fumble. So your team is more likely to win the game now. Like teams that recover fumbles are more likely to win games. So you could be like, well, it could be the end of the game. You're like, well, it just gives me information. If my team recovered a fumble in the game, my team is probably more likely to win the game. So it's just probabilities. Like, or if your team fumbled, your team would be less likely to win. Like fumbling the ball gives you information about the team winning. So correlation is a specific type of association. Correlation only applies to two quantitative variables. Like, I can't state this enough. It's like Brian's big pet peeve. And I want to put this on the test also. I wish I could just like everything I say I want to put on the test would just magically appear and the test would write itself as I'm like, I want this on the test. But a correlation is only when we have two quantitative variables. It's a very specific type of association. So you don't say things like gender and eye color are associated. I mean, oh my gosh, you can say that. Gender and eye color are associated. Gender and eye color do not have a correlation. So you can't be like, but, or gender and height. A lot of people like to say that one. You wouldn't say gender and height have a correlation because you can't say as your gender increases because that doesn't make sense. Kind of like Moneyball, more runs correlates with more wins. Yeah. Mm-hmm. So more runs like correlates with more wins. Yep. Or more like getting on base correlates with more wins. And you can say like the more you get on base, the more you win. Whenever you do correlation, it has to be like if one goes up, the other goes up or down. So you can't say gender goes up. You can't say your pet preference goes up. Like you might say pet preference correlates with, what would that correlate with? How much money you spend. And so you can be like, well, as people get different pets, they spend different amounts of money. Like if someone has a horse or if they have a dog or if they have like a ferret, then they spend different amounts of money. That might be true, but it'd be associated. The pet you buy is associated with how much money you spend on that pet. It's not correlated. Does that make sense? Like the pet you buy is associated with how much money you spend on that pet. It's not correlated because your pet preference can't go up or down. It just changes across different categories. Who can tell me for 100 points, how would we make a visual display of pet preference and how much money you spend? Let me give a hint. Pet preference, how much money you spend. So that was pet preference, how much money you spend. Very easy test question I could just write like this, like what would be the visual display for a pet preference and how much money you spend? Who knows that? What visual display you would see instantaneously for that? It's a review question, box plots, boom, 200 points right there. Yep, and Mila also 200 points. It'd be because pet preference is the X, and then amount of money you spend is the Y. And those are things we should have down pretty well. And this is the skill set we want to develop, where when we hear these things, we can kind of see it in our head a little bit and visualize it. Well, the way you have to correlate, Sarah, 100 points, yes. Weight of pet can go up or down. That's quantitative. And food, Sarah, you're at 200. You've done. I love the thinking outside the box questions. I love the, well, what if we did this instead, like the weight of your pet and how much money you spend on food? That would be correlated because the more your pet weighs, the more money you might spend on food. Now, I'm not saying that's true, but that's kind of the logical relationship I would think exists. That the more pets weigh, the more money you spend on food. Because I mean, they have to eat. They're bigger. I mean, it's not like a little gerbil or something's going to eat as much as a horse. So here we are with correlation. Excellent. Philip, 100 points. You're cracking me up in the chat. So we've got here correlation. Correlation is values between -1 and 1. So it can go as low as -1, it can go as high as 1, and 0 indicates no linear. I can't stress this enough, that when there's 0 correlation, there's no linear correlation. If you have 0 correlation, you can still have correlation. If you have 0 correlation, you can still have, not correlation, you can still have some sort of association. Sorry, my brain's still waking up. But it means there's no linear, and we do have examples of this right here. This was the strongest one we mentioned. Remember, this was the strongest, but its correlation is 0. Say it in the chat for 20 points, because why? Why is the correlation here 0, but there's still an association between these points? Why is the correlation here 0, but there's still an association? How is that possible to have a correlation of 0 and association? Sylvia right there, and Griffin and everybody, it's nonlinear. It's nonlinear. So we see here that the value of R is only associated with linear. So these linear ones right here are accurately displayed. Excellent work in the chat. Man, 20 points, everybody. Keep it up. Look at this right here. This is a very strong linear. This is a positive linear correlation. This is a moderate negative. These words moderate, negative, moderate, strong, they're very subjective. This one right here I'd probably call weak, and maybe these are good numbers right here. 0 is non-existent. 0.3 is weak. 0.6, which it doesn't matter if it's positive or negative. It just matters how close it is to -1 or +1, is moderate, and 0.9 is strong. But what if you saw a correlation of 0.95, what would you call it? Or let's say -0.95. No, that is negative. But what would you say for that? Brian just called this strong. What would you call 0.95? And these are very subjective in what you'd call them. Very strong. Boom. What would you call 0.99? And you could call 0.95 strong. That's perfectly fine. You call it near perfect. I like all these answers. Yeah. Yeah, you could call it near perfect. 1 is perfect. That's probably one of the best ones you can say. Like 1 is perfect, and 0.99 is near perfect maybe, or extremely strong. You could say there's an extremely strong correlation, or like very strong, super strong. Like if everyone knows this here, these words are more subjective, but you would never call something like 0.3 strong. It's just the closer it gets to 1 or -1, the stronger it is. 0.99 near perfect, yeah. And once again, these are very subjective, what we're calling them. So the strongest possible is 1 or -1. Those are the absolute strongest. The weakest possible is 0. And when it's 1 or -1, it is perfect linear. So very important to know that 1 or -1 is perfect. Like that's definitional. You can say 0 is non-existent. Like there's no linear correlation. So you'd say there's no linear correlation. So the only ones we really have, like this one right here, this one can be defined as there's absolutely no correlation between X and Y. Like there's no linear correlation. As there are for the graphics on the next page, you can say there is no linear correlation between X and Y, but then you would also have to say, especially in this graphic, there is a very strong parabolic association. So I might even clarify there's no linear correlation, because if you were to put a line, the line would go flat through here, because the line does not fit this data. It'd probably go down through here. If you fit a line, which you can do, the line would go flat through the data. There's no linear correlation, but there is a parabolic association. Does everyone see the change in words? Take note of those words. There is no linear correlation. There is a parabolic association. For something to be 1, does it have to have a 45-degree angle? Oh, amazing. You know what? We're going to the website where we learn everything. Let me go over here. We're going to go to the website that teaches us everything. Wikipedia. Oh, God, it's scary to put in correlation already. So let me show this right here. That probably works. If you notice right here, I really love this middle graphic on Wikipedia. We're going to main screen because it's bigger. Okay. So, there we go. There we go. Okay. Exactly, Jonathan, 20 points. And look at the middle line right here where they show you it doesn't matter the slope of the line. Strength is only indicated by if it is, like these are all the same strength because they're all tightly clustered the same way. Like this is perfect positive, this is perfect positive, this is perfect positive. Now, this one right here in the middle, you can't mathematically do. The reason this has non-existent correlation is because there is no variation in y. And the mathematics breaks down. I think we show the equation in here, but if you look at the equation, the variance of y would be in the denominator, and since the variance of y is 0, you can't solve the math. You can't math this one. Does that make sense? Like this one, just there's no math for it. The math turns out to be meh, and so you can't actually calculate it. It actually took me 2 semesters of teaching Stat 201 back in like 2012 to like find out why, and I was like, I don't know why there's nothing there. And then I looked at the equation and I was like, oh, it's just incalculable, because correlation is about how, X explains Y, but there's nothing to explain in Y. Just think about this for a moment. Y has no variation. So since Y has no variation, there's nothing to explain in Y. If there's nothing to explain in Y, then you can't calculate the correlation between them because there's nothing to explain. Especially when we look at R squared, talking about like X explains blank percent of the variation in Y, there's no variation in Y. Y is a flat line, like the y-axis over here. Like if you did a y-axis, there's no variation. And since there's no variation, there's no r squared. If there's no r squared, there's no r. So thinking about it that way might help. That's a theory question, which takes me sometimes a while to be like, why does this exist? And then I'd look into it. This right here just shows you it's negative, but everything on this middle row all have the same what? 100 points first person. Everything on this middle row all have the same what? Except for this incalculable one. I mean, it kind of has the same, but it's just incalculable because of that. Strength. Yep. I'll take correlation also from Alex and Corbin. They have the same correlation, but the same strength, which is kind of the same value of correlation, because correlation, we generally think of the value of R. So you can see here the different correlations. This one right here has the same strength as this one over here. Like these have the same strength. It doesn't matter if it's positive 0.8 or negative 0.8. That doesn't matter. All these on the bottom show you correlations of 0 that actually have some sort of relationship. So all these graphics on the bottom right here, this is some sort of association that has a correlation of 0, but it's associated in some way. So those have associations, but they have a correlation of 0. Good stuff. Good stuff this morning. Excellent work. Here's the demo. We were looking at this earlier. Fun stuff. And then we get to R squared. Yeah, R squared. We were just talking about you. What you doing, R squared? So R squared is the coefficient of determination. And I felt so smart because I looked into it and I was like, oh, what is 1 minus R squared? 1 minus R squared is the coefficient of non-determination. I don't know. I've always felt smart for knowing that, but I don't, it's like so useless. Sometimes when you read things, you find things that just like no one knows and it's not important. But that's the coefficient of non-determination. So you get the coefficient of determination, R squared. You'll probably never hear it called the coefficient of determination again. Everyone just calls it R squared. Frankly, if someone said coefficient of determination to me, I'd be like, oh, R squared. I'd be like, it would take me a moment because I call it R squared. Everyone calls it R squared. It's what it is. It's like if someone calls me like by my middle name, I'm like, oh, I guess that is my name. But it's so weird. Very quick story. My middle name's Joseph. And I mean, I like my middle name. It's all good. But when I was in high school, for some reason, the roll had like Joseph Stevens. And then we would have substitute teachers every once in a while, and they'd always be like, Joe Stevens, or Joseph Stevens. They're like, do you go by Joe or Joseph? And I'd be like, I go by Brian. And the people would be like, is your name Joseph Brian Stevens? I'm like, no, it's Brian Stevens. And they're like, well, why'd they call Joe? And I'm like, I don't know. I don't know why my middle name is the first name on the roll. What's going on here? But it happened more than once. And then people were like, what is your actual name Joseph? And I'm like, no. Yeah, that's so weird, isn't it, Sylvia? It's just like, what's going on? What are you doing? And I don't mind Joseph. It's a good name. It's my grandfather's names. I'm cool with it, but I just don't go by it. I go by Alex, but yeah, exactly. Yeah. So, well, you see, but that's the thing is I'm not Joseph Brian Stevens. I'm like, I'm not. I'm Brian Stevens. I go by my middle name. So yeah, it's funny. I've got a friend, Cody. Cody, why can't I think of his last name? Cody Howard. There we go. I was like, my brain blanked. But his name is James Cody Howard, and he goes by Cody Howard. So, but he goes by, it's James Cody Howard, but he goes by Cody. So, but I can't imagine him being a James because I've got other James friends. So I can't imagine be like, hey, James, like, and he would, if he heard that. So whole point being, I like the Griffin right there. Oh, he is Griffin Judy. Yeah, I see that. Yeah, yeah. And my name's kind of like if Stevens was Steven, then I'd have 3 first names, like Brian, Joseph, Stephen. Like, it'd be 3 first names. Yeah, so Griffin, that's pretty interesting. Probably they're like, Judy Griffin. And you're like, that's not my name. So coefficient of determination, R squared doesn't like being called that. R squared likes being called R squared. This is R squared's middle name. R squared is just R squared. It's R squared coefficient of determination. Don't call it coefficient. It doesn't like that. Don't do that to it. It just likes being called R squared. It's cool with that. So now when we talk about R squared is when you know X, it gets you blank percent of the way to knowing Y. And so this is an excellent way. You'll be doing this in your assignments. But when I'm highlighting things, it's like you should know these things instantaneously, especially since they're in a box. If you know X, it gets you blank percent of the way to knowing Y. Or blank percent of the variation in Y is explained by the variation in X. That's my classic way of doing it in 201. Blank percent of the variation in Y is explained by the variation in X. Or, once again, if you know X, it gets you blank percent of the way to knowing Y. So what's the whole point right here? X explains Y. Does everyone hear that very clearly? That X explains Y. I got R squared wrong on every... No! We'll get it right. Okay, let me do this right here. Literally this. This is how you get R squared right. We're going to get it right. We're not going to... Sylvia, you get 100 points for that right there. Because now you're going to get it right on every 320 test. Here's how you do R squared. And we're going to do it multiple times in this class. But here's how you do it. I'm going to write it here. So whenever you see R squared, it's just blank percent of the variation in Y is explained by the variation in X. That's it right there. It's the whole thing. Now, you need to put in what X and Y are, but this is it. Blank percent of the variation in Y is explained by the variation in X. And usually I like to do this right here. Art's going to get mad at me, but I'll do it. So that's it right there. Blank to yes, Jonathan right there. 100 points, Jonathan. So blank percent of the variation in Y is explained by the variation in X. You can go off this slide also like by saying like, if I know X, it gets me blank percent of the way to understanding Y or knowing the variation in Y. But I like this way. It's the way I do it in 201, so I keep it this way in 320. But there's other acceptable ways. You don't have to do 100% of what I say, but I mean, you have to be close to it. You have to like have something in the ballpark of what we're doing. But if you do this, you'll be fine. Like blank percent of the variation in Y is explained by the variation in X. Now, why am I underlining these things? I'm underlining these things because you have to put in what the Y variable is. You have to put in what the X variable is. You can't just write this on the test and be like, I'm good. You have to then input what the Y and the X are. So I think we'll see some examples here, but we'll try to do some R squared interpretations where we say like 60% of the variation in somebody's height is explained by the variation in their weight. And actually, you know what? We can do it really easily. Oh, what did I do? Oh, I clicked the button twice. I want to see the changeover. Let's look at the speed run. Oh, okay, cool. Let's do a speed run of interpreting R squared. You ready? Give me 2 seconds right here. We're going to do a speed run interpreting R squared. We got to get our speed runs in. You know we do. Is it stronger if the percent is smaller? Yes. Perfect answer right there. So Emily, 100 points right there. Yep. The higher or lower it is, the stronger or weaker it is. And so, like with correlation, like more variation is explained. You generally want more variation explained. And I'll need our studio. Where are you at, our studio? And give me 2 seconds to get my window framed up for our studio. And I'll have to... no. Why can't I get that? Oh my gosh. Okay, one moment. Because I'm going mad, everybody. Look at that right there. There we go. Okay, let me increase font 1 time. Let me increase font 2 times. Okay, so finish this plot off and we're good. And let's talk about R squared in the speed run. Here we go. So one of the easiest ways to get R squared right here, we've already got reg class loaded up. Sorry, I hope that doesn't DQ the run. So we've loaded up reg class. Let's go to data survey 10. Now the reason I love survey 10 so much is because it's got the variables height and weight. And we can just call here height tilde weight. This is our classic format, y tilde x comma data equals. And we're going to go here to survey 10. Now what this did was it looked at y and it looked at x, and this is our data frame. That's the format of this linear model we're making right here, y tilde x comma data equals. So y tilde x comma data equals. Ignore that graphic, it's not useful right now. So we're putting in here our y variable, our x variable, and our data we're using. This will store the object M in the global environment. You can see here object M has been created. We also have survey 10 loaded in. This line of code did that. This line of code stores the M. Let's just do that one more time right here. That when we do this right here, we load up red class. That loads up all of our packages and all that good stuff. This loads in data survey 10, which was inside of red class. We're not reading in an Excel file. That loads up a data file, which we had access to, like a preloaded video game. And this right here creates the model M. Now what we can do is we can actually just do a summary of this model. And guess what we get? We get, you called it, R squared right here. Coefficient determination. It's like, don't call me that. Okay, cool. You're not coefficient determination. But I need somebody in the chat for an extra. We're putting you at 300 points. I need someone to interpret this. Remember, this is the Y, and this is the X. So who can be the first person in the chat to interpret this right here? And we change it to a percentage. We multiply it by 100. But remember, here's your Y, and well, that was the X. So that's your X and that's your Y. And here's your R squared. First person in the chat is at 300 points today. 36.1. Oh, wait. Oh, Austin, that puts you at 200, but not the 300. Oh, no. Oh, no. I need full interpretation. I need accurate. I need the actual words in there. So, oh, wait. Oh, you guys are so close, but no. Yes, I think Brad got it. 36% of the variation in weight is explained by the variation in height. No. No. So close, Brad. Brad, you're at 200. Sylvia. This made my day. Sylvia, you got the 300. If I'm correct, no, Brad, I'm sorry, Brad. Brad's at 200. Sylvia was the person who got it. And I'm not joking. And so what small thing happened? Sylvia got it because there was a small switch and I caught it. Because when you do it, it's 36% of the variation in Y is explained by the variation in X. So great job. Excellent work. I'm going to be super nice. If you participate in this, you are at 300. Sylvia's at 350 though. So because she won it. So, and I'm so glad because she was saying I got it wrong every time. Like, and then just boom, got it, destroyed it. So, but remember 36% of the variation in height. So we got to make sure, got the previous thing up here. 36% of the variation in Y is explained by the variation in X. So to make sure to have which one is explaining which one. So this is your Y. Oh no, that's not the Y. This is your Y, this is your X. So this is the mistake people make. It's 36% of the variation in height. And then you have to think, can be explained. Whatever you're going to say next is going to be your X. Can be explained by the variation in weight. Does that make sense to everybody right there? Like, this was a good speed run. We went sub 4 minutes. Who feels like they could interpret another one? Like, let's do it. Like, let's do this right here. There you go. Interpret this one. Interpret this one. I need to figure out if we can crab rave again. I know we need some crab rave back. It's just that if I do it, then Monster Cat will take our video and put ads on it. And then you'll just see ads on like our videos. And people will be like, Brian, why are you putting ads on our lecture? And I'll be like, I'm not. Monster Cat's taking our videos. How do we interpret this one? Who can do this one? 1.8% of the variation in height is explained by GPA. And then by the variation in GPA. Did I do variation in GPA? By variation in GPA. So by the variation in GPA, yep. And then variation means it's not just people's GPA, it's like the variation. Like people with higher GPAs generally, like linear model stands for, LM stands for linear model. Great question, Ryan. Ryan, you're at 350. I'm breaking all the rules today. No, Ryan, really good question right there. Like, I want you to ask me what the code means. That's linear model. So 1.8% of, make sure, wait, 1.8% of the variation in height is explained by the variation in GPA. And then you can say knowing someone's GPA gets us 1.8% of the way to understanding their height. That's acceptable. I like to say the variation stuff. But so the variation means like the variation, like people who have this, like a higher GPA generally have a higher height. There's really not much of an association right here. Does that make sense? 1.9% of the variation in height is explained by the variation in GPA. Boom. Yep. I know it is. It is, Alex. You are totally right, Alex. Another 50. You're at 350 right there. I like those answers. Like, people like, that's not that great of an R squared. Also, oh, but the model's significant. Look at this p-value. And the model's statistically significant, but it's not as statistically significant as the last one, which was ridiculously significant. And if we have R squared, this is on the homework too. So if we have R squared, how would we get correlation? How would we get correlation if we have R squared? So if I have R squared right here, how am I going to get correlation? square root it. There you go. There's the correlation. And I think you can, I so rarely do this. Well, you know what you can do? Watch this. Here, we're going to go. Speed run over. You can go to associate, and you will do this on this assignment. And if you do associate, so now we're using, does everyone notice why y tilde x comma data equals is a very, does everyone notice why y tilde x comma data equals is a very good format to know, like y tilde x comma data equals. That's why I keep telling you, like, y tilde x comma data equals, y tilde x comma data equals. So you'll use that throughout. Even in 474, we use that format. It's just like, it's the formula format followed by your data set. It's just very common when you're doing statistics. And so now we're doing associate. And look at this. Here's a scatter plot with histograms on the side, because histograms are univariate. It'd be $5 a month. I think maybe I'll just buy it this weekend. Maybe I'll just be like, I can pay $5 a month for us to have Crab Rave. And then I get other songs. Like, I've thought about, we could just have like chill music in the background sometimes, like on office hours. But I just can't find enough music. Monster Cat is very much like techno, trance, electronica, like all that very interesting. Like, I have friends who are into that kind of music. Like my friend Austin, he's like, man, Brian, I go out to the raves and stuff. Austin Glines. But yeah, it's like, yeah, it's, if you guys, I don't know. I need to find enough good songs that I think we could play. I did not do the full thing. Oh, I didn't do the, let me try it again. There we go. There we go. We'll be seeing this graphic here very soon. But if you notice right here, associate is a very smart function that will change what it's doing. And here, let's make the output. Okay, I'm going to have to, there we go. I think it'll work now. Okay, good. Let me make it bigger now. Okay. So take a look at this output right here. We get the correlation. You guys are too funny. I know. You guys need to help me out with this. You guys need to help me figure out how to do this and what we can do on the stream. You can make it rain on fire for some crazy transitions. Oh, yeah, I know, right? Well, that's what we're also going to use the grant money to like get better transitions and help other classes do fun stuff like we're doing. We'll have more stuff. We're going to, this weekend, while I'm making the test, hopefully I'll be at home. I've got After Effects on my laptop. This computer is much easier to run After Effects on. Send me info on that, Jonathan. Send me info on that. So here's the Pearson, and we'll talk more about Spearman in a moment. But here's something I want you to know. With this class, you need to know what all this output means. Does this output look, on a 1 to 10 level, how scary does this output look? We've got a few graphics over here in the background. So we've got these graphics. We've got a scatter plot. We got histograms on here, which show us the univariate relationships of the variables. Like, here's the univariate of height. A 5's good. And then here's permutations. Ooh, we got some permutations down there. And then we have these right here. And here's your correlation value. Here's a p-value. Is this correlation statistically significant, yes or no? Is this correlation right here statistically significant? Is that Pearson correlation statistically significant? Here's the value of it, and here's the p-value of it. Yep. Yep, 100%. Are you confident of that, or is the interval conclusive or inconclusive? Is the interval right here conclusive or inconclusive? I'll zoom in on it one time. Is this interval right here conclusive or inconclusive? Conclusive, because it doesn't contain 0.05. And that's a p-value interval. This is an interval for the p-value. So it's conclusive. We're trying to estimate the p-value, and we think the p-value is in this range. Let me make this as clear as possible. This p-value we get via the permutation procedure is estimated. Like, we are estimating the p-value. We're not saying we know the p-value is this. We are saying I'm 95% confident that the p-value is contained in the interval blank to blank. If you remember stat 2.1, I am blank % confident that the true blank is contained in the interval blank to blank. Yep, Spearman we'll look at. You got it, Alex, in just a moment. Spearman is going to be for nonlinear. Spearman will be for nonlinear. So we will see Spearman here in a moment. Great question, Alex, right there. Great question, Alex. So r squared only has values between 0 and 1 because think it's r squared. So when you do r squared, you're squaring r. So if it's -1, it's 1. If it's 1, it's 1. If it's 0, it's 0. So r squared, because r is contained between the values of -1 and 1, if you square r, you get values between 0 and 1. So R is between 0 and 1. For correlation to have any practical significance, we need to look at the R squared. Now, could an R squared of 20% be significant? Could like understanding 20% of the variation in something be practically significant? Yes or no? The answer is most definitely 20% of the variation. And the answer is yes. What if I told you I understand 20% of the variation in the stock market? Like knowing one variable gets you 20% of the way to understanding the stock market. Like 20% of the variation in the stock market is explained by this variable. And the situation, yes, Ryan, excellent. Yep, you'd be like, sign me up. Like, what is that variable? I want to know what the variable is. What explains 20% of the variation in the stock market? And that doesn't mean if you know it, you know the stock market will go up. It just means you have information about the stock market and what it will do. You understand 20% of like the structure of the data. Like if you explained 100%, it would be perfect, but there could be variation. It doesn't mean you know it'll go up. So there we go, getting some stock tips in the chat right there. And so what if I told you, since we're all millionaires now, we've all just made it rich. Dave Ramsey's proud of us. Thank you, Dave Ramsey. Now we're all going to go skydiving. And I understand 20% of the variation in why your parachute opens. 20%, I understand 20% of the variation in why your parachute opens. Do you like that? Do you like that? Like I'm like, we understand 20% of the variation in why your parachute opens. All of a sudden now you're like, wait, why do you only understand 20%? That doesn't sound like a very good amount to understand for my parachute opening. Shouldn't you understand like all the variation in why my parachute opens, or like 99.999% of the parachute opening variation? You're like, I'm not going skydiving. I'll invest in the stock market with you, even though you only know 20% of the variation. If there's a 20% variation, I'm not going yet. So it's that we understand. It's like, how much do we understand? You're like, well, I'm like, well, your parachute opening kind of I don't really understand why it opens. I mean, we just got these new ones and I don't really understand. I mean, it has something to do with like the way it's packed in there. Like that explains about 20% of why it opens. The other 80%, I don't know why it opens or doesn't open. Like I don't really know what's going on with it, but I've got a good hunch on certain things. But 20% of the stock market is like, well, I don't really understand all about the stock market, but I've got a good hunch on some things and at times I get things right. So like 20% of the stock market would, if you understood 20% of the variation of the stock market, you'd be a millionaire. You should just invest all your money. But I don't think anyone understands 20% of the variation, because you could leverage that to make decisions that you would constantly, like, you'd beat the house. You'd come out ahead. If you only understand 20% of the variation, you 100% don't care. Austin, best joke of the day. You're at 350. Austin, best joke of the day. I like that. That's man. See, you guys come up with better jokes than me. Good jokes in the chat right there. I like it. So to get R squared, all you do is square R. So awesome, Austin. So you just square R right here. Pretty easy to see. R squared, R squared. I mean, like, here's R, there's R squared. Now, one thing people neglect is that when you square root R squared, you have to look to see if it's positive or negative. So when you do a correlation, I think I can show in the background right here. Like this graphic right here, I know that R is positive because the line goes up. Now, there is a non-linear relationship to this. There's a little bit of non-linearity, especially at the end. You can see the non-linearity to it. We could expand it just a little bit here. And you can see that it bends at the end, and there's outliers. So we got outliers. We might have a little bit of heteroscedasticity, like it's thicker here and it gets thinner in here. So this is a positive, somewhat non-linear, heteroscedastic. It's monotonic. It's monotonic because it constantly goes up. It doesn't like go back down. So it's monotonic, non-linear, a little bit of heteroscedasticity and outliers. So that's a big review right there. How is the what is the so wait, is this a question right here, Alex? Though exactly how large is the eye of the beholder? What does the beholder say? Is this rule of thumb? I don't know if I get it. You might have to expand. It might be something I don't get. It might be like a movie quote. So one thing we have right here, and this will start branching into even more assignment stuff. Let me click the main screen zoom. Hopefully that helps out a little bit on this one so you can see it a little bit better. This is a correlation matrix. And I don't think we really use this in this class because correlation matrix, it's like, what we use is all correlations. All correlations couldn't be more aptly named. All correlations runs all correlations. So all correlations runs all correlations. So that's what all correlations does. I can't, like, if you were watching the reviews or me doing the office hours, I'd be like, what does all correlations do? It runs all correlations. So let's look at the format of it. All correlations takes a data frame. So the input for all correlations, for correlation to practical significance R squared should be large. So exactly how large is, oh, it's literally so subjective. That's the thing. Good question right there, Alex. It's so subjective. Checking all betas. You might be thinking about beta weights, Brad. Maybe in regression we talk about beta weights, like the coefficients in models. A little bit like that. It sounds a little bit like that. It's similar. It'd be like looking at the individual betas between all the variables, and that'd be like beta weights in regression. So that might be what you're talking about. It's like, yeah. So you can check all the variables right here and look at each correlation. And why would we use this function like all correlations right here? Because it's got additional things. The additional things that it has is the argument right here, interest. So the interest argument right here allows us to select just one variable. And we'll do this right here. And then we've got another one. We've got sorted. Sorted will take this whole list and sort it. And so check this out. Let's say there's a variable you want to analyze. Let's hop over there. Okay. So what variable do you want to understand about your fellow students? Let's go to survey 10, and here I'll do it this way. Okay. So what variable do people want to understand? Really? Suck at me, graphics arrow. What variable do you want to understand about your students? Now only pick a quantitative one. Number of phone contacts. Okay, let's do it. And this one doesn't have nearly as many variables. Number of phone contacts. Right there. Brendan, great job. We're going to go to all correlations. And we're going to go to survey 10, because that's the data frame we're using. You see, it even helps. We're going to do interest. Now, this has to be in quotes. And then we're going to do sorted equals, it has to be in quotes, magnitude. That's the one we like to use there. So the number one thing that explains people's, you go a little wider. That should do it. The number one thing that explains people's phone contacts, who would have thought? Own attractiveness? Oh my gosh, we got to do that right now, right? Was it on here? Was it own attractiveness? There you go. We need to know why people think they're, that's how attractive someone thinks someone is. So the number one thing that explains phone contacts is how much people text. Pretty good right there. Phone contacts, here we go. Own attractiveness. The number one thing that explains own attractiveness is the percent of people you think you're more attractive than, percent of people you think you're more athletic than, percent of people you think you're funnier than, more intelligent than. But look at the own attractiveness is like, it's basically like, I think I'm so beautiful. Don't clip that. And then people who think that also think that they're very attractive and they think they're more attractive than others. I'm going to pull up dataset survey 11 right here. And let's look at survey 11. So all I'm doing, if you notice how quick and easy it is to analyze data with this, okay, what variable are we going to analyze here? Just tell me X whatever. X whatever are we going to analyze? What X are we going to analyze here? And there's a trick. You have to make sure to not tell me something that's categorical. What X do you want to analyze? Which one is that? Oh, here it is right here. Tell me the X, because then it'll be easier for you to collect it. How much people sleep at night? And look at this. I'm just going to change this to that. And I'm going to change this to this right here. This is how we run data really quickly. It's so long it went off the screen. And then we're going to go down here. Do that. No, we got to go back one font. Okay, there we go. Let's bring us back in here. Okay. The number one thing that explains how much sleep people get at night is how much people talk on the phone. And look, there's a negative correlation right here that people who talk on the phone sleep less at night. Age of first kiss right here. Let's do it. And where's age of first kiss? Which number is that? Oh, no. Here it is right here. Age first kissed. And let's go here. Age first kissed is best explained by... Really? I thought I had this sized properly. Why would you do that? Age of first kiss is best explained by weeks in longest relationship. And whoa, what is so interesting about this? This is pretty interesting. What is that, Jonathan? Does anyone notice here that this correlation is positive? Indicating what? What does this indicate to us? That people who had a later first kiss have what are weeks in their longest relationship? Oh, I'll tell you that in just a moment here. Brad, great question. Yeah, you can limit the results to the top 5. Just go here and go rows 1 through 5 and all columns. And now you can get, oh, I like that right here. Great question. So that's how you get just the top 5, or you could store it and do head of it. So you're right. People who waited longer to have their first kiss are having longer first relationships. We could also view this with the associate. Yeah, we're going to associate up here. So if we wanted to view this, and it's pretty weak, and there's going to be a lot of scatter to it. So we could put this here, and we could go weeks in longest relationship. Does how long you wait to have your first kiss explain your longest relationship? And once again, remember, this doesn't say everybody, but here's the plot. And we've got around here, if you notice, there's a lot of variation. It is statistically significant, but if you look, there's these people have probably never kissed. We should have no data for them. Like, if we're going to clean this, I don't think they're counting a first kiss at 0. And this is, I don't know. It's very interesting how people report this data. You see a lot of data in here in like teenage years, and then some in the 20s. What is the dotted red line? Ooh, we'll talk about that here in a moment. Here, I'll explain it right now. This is our correlation, and these are correlations just as extreme. Let me vanish. So this is our correlation. This is the Spearman correlation. This is our observed result. And then this is a correlation just as extreme, which this is going to lead to the p-value. Great question, Alex, right there. So this is our correlation for the Pearson correlation, and this is a correlation just as extreme. Notice how this is right below 0.05, and this is right below negative 0.05. So this is our result, and this is a result just as extreme. And the results on the outside would be the what? Like if you shaded the outside regions of these, like outside here and outside here, you'd have the what? So, oh, is there somebody? Oh, really? Wait, age of first kiss and weeks in longest. Oh, you're right. That's very interesting. That's like a year, isn't it? Well, that's, yeah, well, it's their call, But that's interesting. Yeah, interesting data, right? We'll be going into that here in a moment, Grant. Great question, Grant. And it's in the slide. So one is for linear, one is for nonlinear monotonic. Like this one is linear, and this is nonlinear monotonic. And I'll explain it here in a moment. And I think Brad had a question. I think Brad had one. Variable 1, variable 2 are interchangeable. Yes, I remember that. The reason, let me pop back in the screen. Boop. The reason that it switches, I'm going to make the graphic like this. It'll switch where variable 1 and variable 2 are at. It's just the way the algorithm runs. And maybe I could tell Dr. Petrie we should have it so that the variable you choose is always variable 1, but it's still just like you're getting all the combinations of the variable 1 and variable 2. Yeah, that's the thing, Jonathan. It's like, how do people report it? It's like, are they reporting when they were like in kindergarten, which that's way before kindergarten, but they're like their friend kissed, I don't know. I don't know. It's data. This is what you get when you ask people questions. This is real data. Real data leads to, well, what the heck does this mean? So yeah, I don't know. Real data. That's the problem with real data. Here we'll do one more in here. Let's do another variable. Another variable. Chair's squeaking. Did you guys see another one? Like, I like doing these. It's so much fun. Like if you look at 25, what is 25? See, now I've lost it. Let me go to names. What was 25? There's names. Okay, 25 is how much do you exercise? And exercise is explained by, wait, did I not do it? I thought I ran correlations on that. What is going on here? Oh, ha 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 ha. There we go. Exercise, which we only have some weaker correlation. How many people you've dated, how fast you drive a car. So those right there. Yeah, that's what people might be counting, Dennis. Dennis, 20 points right there. That's what people might be counting. It's like, you know, the survey did not do a good job defining what it meant by first kiss. Exactly. We call that an operational definition. Like, it should have like operational definition. Like, first kiss means this. Like, make sure you are following these guidelines when defining. You know, like, this was when my first kiss was. So, yep. So awesome stuff. So if you can't tell, hop back to the main screen right here. One big thing to note is that this function right here, all correlations, is super powerful. You might see more commonly if you're doing research that we have here a correlation matrix. I won't show this much in the class because, I mean, people use it. It's very important to know. It's just the correlations are like, if you scroll down here, score is correlated to this one like this. So this is score and fashion score have a correlation of this. The one right here is because it's the same variable. So X is correlated with Y 100% or at 1 if it's the same variable. But the all correlations is an advanced method which literally lets you narrow down and look at correlations between certain variables and then sort the list. It's way more powerful than making a correlation matrix. Like, to make this like list of things right here is way easier to look at. You can sort it rather than being like, here, look at this table. It's like, here's the variable I'm interested in, and here's the variable sorted. Like, here's the strongest correlations. And then you could do the top 5 like we did a moment ago, like where you take the top 5 correlations. So great questions right there on how to do those things. And spurious correlations, amazing thing right here. Some of my favorite stuff in this lecture is about to occur, because correlation does not mean causation. This is like, everyone, hopefully you've heard this by now. If you haven't, it's all right. You should know the phrase correlation is not causation. I hear it so much that I'm like, surely everyone's heard that phrase. Is this anyone's first time hearing correlation is not causation? There's silence. It's all right if it is. It's just like, I hear it. Every time I hear it, my brain jumps at, like, yeah. Oh, Alex, that's awesome. 20 points, Alex, right there. So I'm glad I say it, because, I'm almost 40. Sad day. And when I turned 40. And so correlation is not causation, because there's so many things we see that are just like crazy. Like, this graphic right here is how much the US spends on science and space technology. You got some SpaceX going on right here, and then really sad topics. We show these types of graphics because the correlation down here is this. Look at the correlation. The correlation is 99.2, or we don't really tell what correlation as a percent, but if you did an R squared of that, like here, let's find the R squared. So the R squared on this is 98.4. 98.4% of the variation in these very not fun topics is explained, sorry, it'll get very fun very quickly again, is explained by how much we spend on science and space and technology. But that doesn't mean it causes anything. This is like a series, and the reason it got dark, I'm sorry it got dark so quickly, but people abuse this all the time in statistics when they say like, oh, these things have a correlation of near 1. Well, this has a correlation of near 1. But it's probably just due to population growth. I'm not saying population growth is causing this, because more people, more money is spent, more people die. Sad like that. But this is where people misuse statistics all the time to say like, oh, it's got a correlation of basically 1. Well, that doesn't prove causation. They're like, well, it's almost 1. It's like, well, there's so many things that have correlations that are almost 1 that are not causation. There's some website that has one, you bet. Oh, we'll be looking at that website very soon. That is the website right here, the spurious correlation website, Tyler Vigen. Amazing website right here. So if it's not practically significant, this is where the judgment comes to play. Yeah. Yep. And so big rule, but commonly, yeah, exactly. Connor puts it perfectly. Like, it can be really great correlation, but it doesn't mean, like, ice cream sales and shark attacks is a very classic one that we see that there's more ice cream sales, the more people die via shark attacks, but that's just summertime. Probably due to summertime. We can't say it is due to it. We can be like, well, it makes sense that it's due to it. And then we have here how long, how old you live and how many TVs you own. So we see right here, and it's countries, but it's still probably true for like a person who owns more TVs lives longer. So does owning TVs make you live longer? No, it just probably means you have more money. Sharks do love ice cream though. I agree with that. But it's not spending money on technology that's killing people. The real killer of people is, you guessed it, I know what you're thinking, Nicolas Cage. Just look at this face. He knows it. This is a man living with the pain that his movies, except for Kick-Ass, which is the best movie ever, he knows it. That is his, like, what have I done to the world? And she's just happy. She's on, this is definitely a plane. You can tell it's a plane. Oh, I know, right? He is. I love that picture. So what's going on right here? Nicolas Cage in movies is associated with people, unfortunately, dying. So I know, right? This is one of my favorite things to talk about. But if you're not convinced, look at the correlation right there. There's something wrong going on here. Just look at the correlation. This is the actual correlation between, he is a national treasure. This is the actual correlation. I wonder what Nicolas Cage thinks of this. Surely someone's shown him this. And we got to continue this plot out. It only goes to 2009. Hopefully this continues. Watch the plot not work in later years. I'd be so mad. Yeah, I do agree. The second movie wasn't nearly as good. The first movie was amazing. Second movie was, second movie was, but first movie was awesome. Chuck Norris biopic. Wait, Ghost Rider. But we see right here, this is a correlation that is kind of just by random chance. It's like one of those things. So lurking variables are variables that are the actual cause of an association. So we did the homework yesterday. I think we're gonna do an activity tomorrow, but we did the homework yesterday, and we might do it later during office hours, and we should be able to get a good bit further in these notes today. So we'll talk about it a little bit more here, but we'll probably do some during office hours today. Office hours. So we see right here a lurking variable is a variable that is actually the cause. And some of the classic things we have are like piercings and height. So would we say that people, like you can generally say, if someone is taller, they have fewer piercings. But if someone is taller, then what? If someone is taller than what? They're more likely to be what? You guys are cracking me on the chat. So if somebody is taller, they're more likely to be what? Older's true, and maybe then you have more piercings. But if someone's taller, they're more likely to be male. And if they're more like, and it doesn't mean they are. I mean, there's females who are taller than me. There's female. It's just it's about trends in data, and what we see here is that if you control for these lurking variables, it goes away. So that's one thing. Like Brian gets into too many online debates, and people always say things to me like they'll be like, "Well, correlation doesn't prove causation." I'll be like, "Well, true. Correlation doesn't prove causation." But we do see a relationship between these two variables, and I don't have a lurking variable or some variable that somebody can put in there. Like, to the best of our understanding, because if you controlled for population growth, like if you went back to this fun graphic back here and you controlled for population growth, which is probably the lurking variable, then it would probably make this go away. Now, this is a spurious correlation, which is probably just something that happened by random chance, because you can get correlations that are strong just by random chance. What percent of the time will you find a correlation that is by random chance that doesn't actually exist, that you'll say is statistically significant? What percent of the time will you find a correlation that you say, yep, Henry, 50 points right there, Henry, you're exactly right. Yep, 5%, because 5% of the time we reject the null. Oh man, where's our random at? It needs to come back. So we get to one of our last topics today, and the big thing you should know on this page is that a lurking variable is the variable behind the scenes. So when you talk about shark attacks and ice cream sales, what's the lurking variable? So this is a good note you should have. Shark attacks, ice cream sales, what's the lurking variable? It's not that sharks like ice cream. Shark attacks, ice cream sales, what's the lurking variable? I need to pay $5 to Monster Cat. Season of the year. Yeah, summertime, season of the year, time of the year, heat index outside. That's going to, if you control for that lurking variable, it'll make it go away. What's the lurking variables between piercings and height? Because there is an association between piercings and height, but it's gender. Like people's gender explains their height, people's gender explains their piercings. And although that's not quantitative, it's still a lurking variable. Like you can't do a correlation on that, but you could do an association. So you could control for that and look at the association. So people oftentimes think, well, you're stuck because if you say like, well, X and Y are correlated, that doesn't show causation. You could then control for a variable someone says is lurking. So I really like this kind of stuff because it's like one of the big things I look into is like when you look at different pays among males and females. One of the things is the pay difference we see is going to actually exist after we control for a certain amount of variables. And there's a really good was it a JAMLA article on nurses. And also I want to say this too. The pay differences vary from industry to industry. It's a very complex topic. And that's what I hate is a lot of these topics are boiled down into talking points and to things that are just like are meant to be like by both sides. Like when you look at the blank position on this and the blank position on this, they're trying to turn it into talking points. Meanwhile, this is like very complex stuff. And there is, from what I've seen via all the research, and I can send it to you if you want. If you're like, hey, Brian, send me that research. I'll look at it. There is actually a differences in pays between male and females, especially in the nursing industry, which is one of the articles I looked at. When you control for variables like someone's specialty, how much time off they take, how many years they've been in the industry, all the different variables you can control for. And then when we put gender in the model, it still plays an important statistically significant role. Now, the other variables do explain portions of variation, like someone's specialty, somebody's years in the industry, how much time they take off. All of those will explain some amount of variation. But the fact that we then put in gender and it still explains variation, we've now controlled for those other variables. So someone can't say to me, which they'll say to me online, they'll be like, well, have you considered this variable? I'm like, yeah, the model includes that. They'll be like, well, maybe it's due to that. I'll be like, well, the model controls for that. So the model controls for the lurking variables when we put the variables in the model. And now, once again, the complexity of this is that every industry has different variation in it. Does that make sense when I say it's like every industry has different variation? So when Brian looks at the nursing industry, which is an article I've read, and it's looked at the variation among salaries among males and females, controlling for variables like how long they've been in, specialty, time off, family status, all these different things. And it controls for all those variables. And then it sees a difference that is statistically significant. And then you could ask, well, is it practically significant? Because what if it's $1? So you could then look at that. The statistical significance is this difference we observe by random chance? And the practical significance is the difference we observe something that we would say is a big difference. Now, I'd say any difference is a difference as long as it's statistically significant, because it's like, oh, they're going to pay this person $1 more, and it's because of gender. What's going on there? But this is the big thing. And this is how we try to talk statistics. And I guess it drives me nuts because when people tell me, well, how do you know it's not due to that? And I say, because they included that in the model, that's the end of the story. Does that make sense to everybody right there? Like, if you include a lurking variable, you have now controlled for that variable in your model. And the variation you are seeing between whatever the two variables are would be the variation those variables have, controlling for this variable here. So this is how we try to do statistics. We try to isolate variation, and we try to come at it from an unbiased viewpoint, which is the way I always try to do these things. I try not to we all have biases, and I'm always open to people saying, hey, Brian, you're wrong. Here's this article I've seen. Here's this research. And I always try to read the technical research on it, like the literature on where people are analyzing and taking in data. And I should find that research paper on it. So maybe I'll try to find it. I'll find it at the end of class right here. I'll see if I can find that. I think it's a JAMLA article. So, but that's got it right there. But check it out. Always be looking at research, good stuff to do, and then question the research. Be like, I don't know. Let me look at more research. Let me look into the data more. Test for correlation. With the test for correlation, what are we talking about right here? The tests for correlation are going to tell us if what we are observing here is likely by random chance or unlikely by random chance. So with this right here, what are we going to do? How are we going to test this? How are we going to test correlation? You know it. You know it. I need to see a chat got really quiet. Oh, Alex asked a question. Let me show Alex right there. Generate permutations. So Alex, to answer your question, here I'll show you. I'll show really quick how to do it. So since correlation is between two variables, and this is what our class will be getting to. Let me show you, Alex. If you want to include a third variable, the way you want to do it is go right here and just add in a third variable with plus. Now I've created a model where my x's are weight and GPA. So take a look down here. I've created a model where my variables are height. Well, my height is my y, and then my x's are weight and GPA. And then I can make a summary of my model, and I can see that what is really explaining height right here is people's weight. So if you notice right here, weight has the significant p-value, and GPA does not have a significant p-value. So this is how GPA explains height after you control for weight. Does that make sense right here? This is how well GPA does at explaining height after you control for the variation in weight. So now we've added in the variable to the model. So great question right there, Alex. How would you do this? You would just literally add it to the model. So my model right here has the two x variables I want, and then we can see how well weight does at explaining height when we control for GPA. So that is how you just add a variable to a model, and then the variables will see what explains what, and this model does not care. So that's the big thing about the previous thing I just said. When you make these mathematical models, they don't care about what you're trying to do. They don't care about your biases. You just add the variables to the model, And we have a very famous example, probably ruining one of our examples, it's the Harris Bank example. What data set is that? Is it bank? Where is that data set? Well, no, I got to finish the rest of these notes. I'll show you to the end of class. No, let's show it because I went on that little rant. Okay, we need the Harris Bank data set. Can I search this? I can't search it. Okay, we're looking for the Harris Bank data set. And it's in reg class, I believe, unless I'm going mad. I think it's one of these EX ones. Diet, churn, bulldoze, auto, appliance, account, tips. I'm looking for Harris over here on the right. Junk mail, NFL, Pima product, purchase, speed, tips, wine. Is it not? Let me go to help. Salary, there it is. Reg class salary. Yep, you can search right here. So it's salary data set. So it's the salary data set. And so this is a very famous court case. And it's older now, but it obviously still applies. So I'm going to load up the Harris Bank data salary, and we're going to talk about this for the end of class, since I brought up, because this is a very famous court case where we look at this. So we can go right here, and let's take a look at salary. One of my favorite functions, which we so rarely use, is in dplyr, which you can load dplyr if you want. I'm going to load these things up. So if you want to load dplyr, it's installed up packages, and then dplyr, you'll have to run this. And we've got a function here called glimpse. So glimpse is going to allow us to take a glimpse of this data frame. And so we see right here, it has the salary. Whoops. Oh my gosh. Sorry. We have the salary, we have the education, we have the experience, we have the months, we have the gender of the individual. Feel free to tell me if I have the screen all weird like that. So, oh no, Grant, so sorry. Yeah, just noticed it right there. Grant, 100 points. So we have the salary, we have the education, we have the experience, we have the months, we have the gender of the individual. So what someone could do, and we'll be seeing this later on in the notes, especially coming up here soon, is someone could say, well, let's make a model to see, or let's do associate. Let's do associate to see if somebody's salary can be explained by their gender. And so there we go. And it says figure too large. So we're going to see if somebody's salary can be explained by their gender. Really? Do try catch error. Invalid. I've seen this. This has happened lately to me. Let me save untitled here. So my R is just going mad these days. Today is June 10th. Okay. Let me close out of R. Let me reload R. I think it's because I constantly change like font sizes. It doesn't like that. There we go. Okay. So library reg class. And this should do it. Wait. Salary's not loaded. There we go. We're going to put this. There we go. Good. Now it did it. Okay. So here are the salaries based on gender. So if you notice right here, it might be a little hard to see. I think I can maybe decrease font size. Let me remake the graphic now. We're mainly just looking at the graphic as our main thing that we're concerned about. Here's the salaries of females. Here's the salaries of males. And this is a review question right now, because would we analyze them with means or medians? And we could probably do means because, except for this outlier, it's mostly normal. This one does have a little bit of a skew, but we could do means. And down here we see that the difference is statistically significant. But then someone says to me, wait a minute, Brian, there was more variables in this data set. This salary data set had education. So how would we see if all of a sudden, this is the last question of the day, and I'm just going to finish off talking a little bit more about this, and I'll just go a little bit into the break, but this is the last thing you should really know. What if somebody said to me, Brian, maybe someone's education, their experience, or their months on the job explains their salary? Those are like the lurking variables. What would I do to see if somebody's other variables are actually explaining it? Like maybe it's not just gender. Maybe it's their education. Maybe it's their experience. Maybe it's all those other things. What would I do? What would I do if someone says these might be the lurking variables? Because right now, gender is very significant. Yep. Add them to the model. And watch this. Andrew might know this trick. Oh, yeah, Grant, great job. 350 for all those people answering if you're here at the end. The dot right here means all the variables. Stupid graphic error. And now let's do a summary. So now this output right here, and this is real data. Look at this. Wow. The most significant variable in this model was whether or not someone was male or female. And the difference in their salary was $481. And just so you know, this is 100% real data. This is the Harris Chicago Bank data. This is a real court case that happened. And they were sued for discrimination. So it's not saying discrimination's everywhere. I mean, not saying it's not. It's a complex topic. But this was a very real court case right here. The Harris Bank court case. And here it is. Jury, bankruptcy, judge orders. It looks like stuff is still going on. Like, I just find new things. So let me do gender discrimination on it. Because this took place in like the 70s. Here it is, okay, Harris Bank loses again in job bias case. So here it is, 1987. I said it was the 70s, it was the 80s. The Harris Bank case in history, 1999, $14 million settlement based on sex and race discrimination. So we should get a fuller data set on this. So I think Dr. Petrie created this, it's in reg class. But just so you can see, this was an actual court case, and it was within my lifetime, within maybe some people watching's lifetime. But what you notice right here is that someone can't say, well, maybe the males are getting paid more because they have more education. Maybe the males are getting paid more because they have more experience. Maybe the males are getting paid more because they have more months. Because as Andrew should know, we've now controlled for this. And I want to get the other variables, but we've now controlled for the variation from the other variables. So if someone said, well, maybe it's the other things. No, we've controlled for these variables. The variable of somebody being male or female right here is actually the most significant variable in this model. The most significant thing in somebody's salary, the most statistically significant, is whether they're male or female. And their monthly salary has about a $500 difference. And that's controlling for their experience when they come in the door, how long they've worked at the company, and their months, well, that's how long, and their education. Which I would say that's like 3 super important things, like how long have you worked for us, what's your education, and what's your experience at this job. And then all of a sudden you see a difference right here of $500 based on gender. Once again, real court case, 1989 or 1987, but pretty crazy right there. And this isn't saying, it's like you have to just analyze the data. If 51% of the variation, we could just do alone gender. How much did gender explain by itself? Gender by itself explains 30% of the variation in someone's salary. 30% of the variation in someone's salary is explained by their gender. Does that... That doesn't sound like a good thing. Andrew, what's up? Do some VIFs. Multicollinearity looks to be good. This is a glimpse into the future. This is a glimpse into the future, 320, of what we'll be doing with this when we analyze this output right here. But real court case, not much, just woke up trying to wake up, like it. I should drink I've only got one more Red Bull. If I drink my last Red Bull today, then I won't have a Red Bull for tomorrow. I mean, I could go buy more, but, you know, I'm trying to be on a 1 Red Bull day. But, yup. The complexity of these crazy issues. So, what I really like about this class is we try to use real data all the time. So, you know, this, if you go here, you can read, like if you do question mark salary, it'll show you the Harris Bank salary data, a data frame of 93 observations on the following 5 variables, and then real data used in a court case lawsuit, 93 randomly selected employees of Harris Bank from Chicago from 1977. Okay, so it did happen in the 70s, and then the court case was finished in the 80s. Wow. So it literally took like a decade for this court case to be settled. Values in this data have been scaled from the original values, experience in years instead of months. Education starts at 0 instead of 8. Because I guess maybe this was like I don't know, that's interesting. Adapted from the case study at Stat University of Alberta. So that's interesting. And so they have a open link in browser. Oh, it still goes. Page still works. That's awesome. So here's their page on it. And glance at the data. So here's their data. Wait, what? I'm not seeing the data right now. Show me the data. Stage design, checking the assumptions underlying methods, obtaining histograms and box plots for each gender, checking the normality assumptions, making difference on final comments, brief view study. Oh, cool. They got all their courses over here. Pretty fun stuff. I like it. I will take a break and be right back. So we'll take a break and be right back here. See everybody soon. Bye. Hey everybody, how are we doing this morning? How is everyone doing? Trying to use the sound effect board more, just have a little bit of fun. Everyone having a good time in the chat right here. How's everybody's morning going? Tag someone in the chat for 20 points. If you saw someone saying hey to you, or if you weren't talking up in the chat yet, tag someone in the chat. Remember, the more you chat, the more points you get. Streamlabs checks how long like you're chatting, how long you're in the stream. So if you're here, if you're chatting, you're getting points, you're interacting. Good to see you, and Vedrina. Good to see you here, and Andrew, and Alex, and Caroline, and Anisha, and Carly. Good to see everybody. Tag someone in the chat though. Tag someone like exactly. Vedrina tags someone in the chat. Awesome. Andrew tags someone. Jordan tags someone. Madeline tags someone. Yaoji tags someone. Awesome job right there. Great job. You guys are cracking me. You guys are crazy in the chat. Oh, I love it. I love, it's that's the thing. Let me hop over to the main screen. Like, even though we're like talking in a chat right here, does it still feel a little bit like you get to see your friends in the morning? Like when you see someone in the chat and you say hey to them, does it still feel a little bit like you're waking up and seeing that person and be like, hey, what's up? You're like, we're in the chat together. We're just chilling out. Like we're in this, like sometimes, this might even feel a little bit more personal than maybe being in a classroom where you can't. Yeah, exactly. It might feel a little more personal, I think, than actually being, yeah, it makes me happy too. Thank you guys right there, gals. New York, everyone's guys. So, but it just feels good to like see people in the chat, say hey to them, just the positivity. We're Stat Nation. Yesterday, one of my 2-1 students, I'm giving away stuff. Tell me what you guys think about this idea. Tell me what everyone thinks. I should start saying everyone. It's just like all my family's from New York, and it's like y'all. Like people in the South say y'all, and maybe I should just start saying y'all. Like it'd probably be better because that's more like just like everybody. And when I say you guys, it's like what I mean is everybody. That's what I mean by it. But it's just like ingrained in my head. Like I don't think when I say it, I just say it. But maybe I should just start saying y'all because I've been in the South. Be like, hey, what's up, y'all? I should just say it because I don't know. It kind of makes more sense. But so I'm like, I'm moving to Texas. I'm doing all this stuff, and I've got some Volapalooza shirts. Here, let me show one off. Let's show the best Volapalooza shirt off. I can't move myself here. Let me see here. I'm gonna hear. Wait. Okay. 2 seconds. Be right back. There was the off chance that I could have knocked down the green screen right there. Like it was very possible that I could have like literally just knocked down the green screen, and I would come back and you would just see like the wall behind me or something, because like it'd been too funny. So we've got this Volapalooza shirt right here. They're all very clean, but this is, which year is this? This is, you guys, this was Ziggy Marley. So this was the year. This is an event staff Volapalooza shirt from Ziggy Marley. So you can't read that right there, but it's Ziggy Marley. And I've got others. I've got like 6 of these maybe. And then this one right here. Oh man, this is such a good one. This was the first time we did it in World's Fair Park. And this was, so there's the Sun Sphere. And so this was the Passion Pit. It was Asher Roth, Flogging Molly, Passion Pit. So that's this one right here. And I think I have a yellow one of that also. And I guess that's not an event staff one, but I worked Volapalooza. Like I don't know, Volapalooza was a really big thing. So I did a ton of Volapaloozas. And so what I'm thinking is I might just like give them away, or we could do like a Stats 201 auction or something like that. I mean, I'm not trying to make money. Like we would put it towards the channel, or whatever, but I might just give them away. And I'd want someone to like, like if we give them out to students here, it's just like something they think is cool. Like I have a piece of UT history and like they wear it and the friend's like, whoa, that's like a vintage Volapalooza shirt. But to me, Andrew remembers his big song right there. And everyone was like, oh, it's an I Love College song. But yeah, and we got to meet like Asher Roth, Flogging Molly, and Passion Pit. Passion Pit was pretty crazy. They're lots of fun. But good times remembering Volapalooza, and I don't know if Volapalooza is still around. Like, I guess it didn't happen this year, and I don't know what happened with like contracts and stuff. Um, yeah, exactly. And so I wouldn't want anyone to think I'm trying to make money off this, because if I like I am selling some, like I'm selling like my dressers and stuff for like, like trying to sell those on Facebook Marketplace. But the Volapalooza shirts I'd kind of want to just give to students, or we could raise money. Do you think people will actually, like, it seems like people want them in the chat. That's why I bring it up right here at the start of class. But I might just do like like a raffle or something like that, and just like give these away. Because my fiance was like, she was like, you have some shirts that you've gotten at Goodwill that you just really love. And that was someone's shirt that they, had memories with. And they're like, because these things, like that's 2010, that's a decade old now. And I don't even know if I ever wore that shirt, but I bought it because I was like, I want to have like the memories of it. And so, it's a good shirt. It's a good shirt. And then I've got other ones just from different years of Volapalooza. And the only one thing I'm keeping is like the Ben Folds one. So cute and vintage. Yeah, I like it. So I'm going to keep my Ben Folds shirt though, because I think Ben Folds in the other closet. But the Ben Folds one, I'm a huge fan of Ben Folds. And he played in 2008. No, because my sister she was chair of CEB when he played. So it was like 2006 or 7. I want to say Ben Folds played in 2006. So that's a 14-year-old. Gosh. Oh, man, it's so crazy. Okay, so I'll figure out something going on with that in the next few weeks right here. So stay tuned. Do you guys think I should just do something free with them, or try to like raise money for the channel? I'm leaning towards free, to where I just like post them and say like, hey, come pick up the shirts. And we just figure out a way to give out the shirts for free. And I just want someone who's really excited about it. Someone who wants a piece of UT history, who's going to be like, I got this Volapalooza shirt and free. Yeah, I'm leaning towards free. It's just easier. I don't want people to be like, oh, Brian's trying to make money. Is the money actually going towards this? I think free. Like, that's what I'm thinking. So yeah, let's do free. It's going to be much better. So stay tuned for that. I'll put out the word. Yeah, I'll still be here at UTK 100%. So I'm still here 100%. They're letting me teach from Texas with my fiance. So I'm going to Texas with Chelsea. Congratulations to her. I'm so proud of her, because she's a veterinarian, and she's an intern right now, and she's going to be a resident doing oh my gosh, what do I got? Anesthesiology. I think the Red Bull's not kicking in. Anesthesia. So she's the smart one. She'd laugh at that. She'd be like, what are you doing? When I do these things, I pretend I'm having a conversation with her. Oh, thank you so much. No, she's my favorite couple, and I'm just lucky that I'm with her. So, but no, it's so cool, and I really, I don't know. I'm just so proud of her, because, I've seen her go through vet school and do extremely well, and internship and residency, and just her drive. I think that's the thing. This is Brian's life advice. Life advice with Brian. Find someone who kind of complements your life and makes you work harder. And it's that whole cliche thing of like wanting to be a better person when you're with this person, like wanting to, like, and thank you, Anisha, right there. It's like when you find that person, I believe you always want to like do better at life, and they inspire you. Find someone who inspires you. And so if you find that person in life who gives you inspiration, who makes you want to do better at what you do, and then you do the same for them, I think you have a really good dynamic going on. And yeah, and definitely, try to have a positive relationship. And that's what we try to do. And so thank you guys. So just some positivity here in the morning. That's what we like to do. Let's do this. Are you ready? And so we will do the shirts for free. I think there was pretty unanimous. We only had 2 votes on that, but I was leaning towards free. I'll figure out some way, and I'm just going to try to, give away some stuff at my place, because there's some stuff, and I'm selling for like so cheap. Like I sold a really good wooden drawer for like, like actual wood drawers for like $20. So, but I mean, if you were to go to a department store, they'd be like 100, 150. So, and like I gave my sister my TV. So I'm giving away a lot of things, and other things I'm selling for like cheap. But the shirts, we're going to give those away. So stay tuned for some pieces from UT history. I do have one bookcase. So Adam, it got a little bit of water damage. Maybe I'll just like Adam. So I wonder if I can, I think the shirts, we'll see. Brian's just giving away all his possessions to his students. All right, we'll continue on right here. You guys ready for class? You guys ready to get serious here? We've learned about life, and now it's time for class. Let's do this right here. So yesterday we were talking about how to measure distances. So when we talk about how to measure distances, we have the Euclidean distance, which is one way to tell how far two things are apart. So we've got the Euclidean distance right here, which is simply just the square of the two observations distances on one dimension. And so you look here, you've got observation 1, observation 2, which is A and B technically, on dimension 1. So X dimension, observation A, observation B, you square that distance, and then you add it to the squared distance on another dimension for observation A, observation B. So what does this mean? Like, what is this? Like, we want to explain what this equation means. We have two people. We take their differences in their ages. We square that differences, and we add that difference to the square of their differences on their shoe size. So this is their squared difference because it's just taking the difference between the two individuals, individual A and individual B, on characteristic 2. And then we go all the way through and we do it for multiple characteristics. And we say, okay, now we're going to look at their salaries. And this is where we're going to lead into the next topic. But does it make sense what this equation is doing? It is going through two people, person A, person B, taking the difference they have on a characteristic like their age, their shoe size, their salary. It's squaring that difference, adding up all the squared differences, and then square rooting them. And you might say, why do we square that difference? Why are we squaring the difference? 100 points off the bat, 200 points max today. Why theoretically would you be squaring these differences? Why wouldn't you just add all the differences? Why are you squaring the differences? I mean, we're square rooting them at the end. Why did we square them? And then 100%, yeah, that's why. Because if we have some differences that are positive, some differences that are negative, amazing answer, 100 points in. Because if we don't square it, there we go, Yao Ji, 100 points also, and Anisha, you guys got it, 100 points. Because if you don't square it, some differences will be positive, some will be negative, and it's going to create this jumbled mess of like, what is the difference? So we square it, and then why do we square root it? Because we want it in units of the actual problem. So we square root it to bring it back to the actual units, to an actual difference. So you don't want squared units at the end, you want just the regular units. And that's going to lead to kind of an interesting issue right here because, and that's just the difference we talked about yesterday, is that some of these variables are going to be very much on a different scale than others. Imagine your boss tells you you're getting a $50 raise. Who here would be super excited? You'd be jumping for joy. You'd be like, oh my gosh, this is the best day ever. Oh, this is so awesome. I'm getting a $50 raise. Who would be jumping for joy? Show someone. Me, Adam, you are right. You know why? Because it's $50 an hour. Yes, exactly. Andrew already jumped in there. Yep. So you guys get 50 points for that right there. So you get $50 an hour raise. But that's a lot different than $50 a year raise. $50 a year is a lot different. You guys are awesome in the chat. $50 an hour would be an amazing raise. Where $50 a year, I mean, it could have been one. I like it right there, Dennis. Good to have you here, Dennis. Hang out. I love it. So this is literally the idea of when we standardize variables, we're going to put them all on the same playing field. So if scaling is not done first, then whichever characteristics has the largest range will dominate the dissimilarity score. So think about this. If we were to compare people based on their shoe size and their salary, if people have a difference in their salary of like $1,000, we'll square that difference. It'll literally go into the calculation here. And the difference in their salary of $1,000 would be squared. But let's say this person has a size like 1 shoe, like extremely small, and this person has a size 15 shoe. That's ridiculous. That's a huge difference in shoe size from size foot 1 to size 15. And I'm about to rant on something. And then over here, their salary has a difference of $1,000, which I'm not saying $1,000 isn't much, but in terms of salary, that's a smaller difference. So we standardize them. By standardizing things, we put everything to the same playing field. So what does standardization do? Usually we just turn things to z-scores. So you can standardize between 0 and 1, where 0 is the minimum and 1 is the highest. I don't like that. I like doing z-scores. So z-scores is to put everything to a 0 for the mean and 1 to the standard deviation. I prefer this right here. And my quick rant is, I hate shoe sizes. I think it's ridiculous that we have male and female shoe sizes. Shoe sizes should just be one metric because one time, it's like personal experience. One time I was buying shoes and I was buying some 11s and they were like, I don't think you want these. And I was like, what do you mean? They're like, they're size female 11. And I was like, oh, stupid male, female. Like, why don't we just have, this is a size blank shoe. This is a size blank shoe. Like, just tell me how long the shoe is. Just give me a number and then tell me how long my foot is. Why do we have 11? Why don't we just say your foot is this many centimeters long? And then like the shoe would say like for shoe sizes blank to blank. And they'd be like, oh, my foot is this long. And like, it's just so weird. Why don't they just tell you how long your foot isn't? Like, yeah. Oh, and they differ by country. See, then we need to be the first country here. We're going to go metric. It's never going to happen in the US. But, so wait, I think it's shoes width difference between males and females shoes. So there is a size difference. Yeah. So I guess like, well, you see, then they should just do like wide foot, small foot, or they should do like there, because this is, yeah, ladies' sizes and clothes I don't understand either, like 0 and 8 and 14 and 00. And this is very odd. I mean, at least in my opinion, I prefer just like, this is like, because then you run into the problem, which I've heard a lot of ladies say, is that like if you get a size 6 somewhere, it's not the same size 6. Like you could get a size 6 at one place, not the same size 6. But when I buy pants and they're like a 32 waist, it's the same 32 waist no matter where I go. Unless, I mean, some places are a little like the cuts might be different, but generally I'm going to see less variation. You see, that's the thing. What does statistics control for? This is the whole conversation. Statistics is about analyzing variation and understanding the variation so we can limit variation by saying like, okay, you need to measure like the size here, and then you're going to put that on your label. And then, I don't know, I don't know if you know oversight. That is like big, like this is the business analytics of it. So right here, that's like question, would people prefer like size 6, or would you prefer like actual measurements on it? Which maybe some places give like the actual measurements, like they would say like all the different measurements on the thing you're buying. Would you prefer just give a number? Like the clothing I buy doesn't do that, but what would people prefer? Like it have a number or the measurements? And feel free, I don't care if you disagree with me. It's like, because this doesn't impact me, and you know, it's preference. Measurements, that it just makes more sense to me in different, yeah, and that's, yeah, actual measurements. It's so interesting. I wonder how this started. Like I want to know the history of why, and maybe there's measurements is better, actual measurements, yeah, but just, yeah. And so number, ooh, I want to see. So for the people wanting number, I'd be interested. Like, and it's interesting. It's just, this is variation. And think literally, this is the business analytics of it. Like maybe they figured out something about the analytics that it's easier to sell something with a number. Maybe also people are less likely to return stuff. I mean, we kind of know, and then you'd want less variation within the numbers. So yeah, Anisha's right. Like we want maybe to limit the variation within the numbers. Like maybe, you know, or like there'd be charts like this store, this number means this. People would rather see the number 10 than a number of it. Yeah. And Dennis might be right there, that people would rather just see this number than this. And maybe it's easier to see. Maybe it's just like people, maybe that's what they found. It's easier to sell something like I bet if we went to someone who's in like marketing, they might be like, it's way, yeah. And that's the thing. Yeah. So there we know. And that might be the psychology of it. That might be the marketing. And this is the business of analytics. Like the analytics might say it's easier to control the variation, but then the business side might say it's easier to sell something with a number. And if they're trying to sell the product, then they might say the numbers, like they might have done research on this. Like I don't do this kind of stuff, but probably someone's researched, is it easier to sell something with numbers or measurements? And maybe the measurements just complicate stuff. Like it's too many numbers, people get confused. And then you don't find the exact measurement you're looking for. You're like, well, I'm a 33, this is a 32. But then people feel more safe with a number, like, okay, there's a 10, but I'm an 8. And so it's the business side of it. So that is the complicated part of it. So good discussion on that. It's the reason people would rather buy a medium t-shirt than a large with a length and height, even it would be more accurate. Yeah. You know, that's the thing. I'm talking about this here and I do it right now. These are medium t-shirts. So what is a medium? Brian, wouldn't you want all the measurements on that t-shirt? Brian, wouldn't you want like it to say like, you know, like, I don't know, like what, 38, I don't know, 36, I don't know my measurements all around, but I'd have to look and be like, okay, this neck is this everything, bust and waist and everything here. Like, yeah, it's like more confusing for women. Yeah, exactly. And then we have all that. So, and you know what you've just done? What have we just done with all of these sizes? What have we just created with all these sizes? We've just created what's? Literally, we're totally on topic with this whole discussion. 100 points first person. What have we created with all these groupings of like sizes? We've just created clusters. Sarah, 100 points right there, first person. Yep. And Andrew and Caroline, 100 points. All of you right there. 100 points, everyone answering clustering. You're following along. You know what's going on. Getting those points. So we see right here how we can do this right here. And yet, Brian's very, gosh, so crazy. Just crazy how all this works in business. And I love talking about this. I love the business side of it. A z-score is just the original observation minus its mean divided by its standard deviation. So you should know this formula instantaneously. So Brian is 75 inches tall. The mean for guys is 69. The standard deviation is 3. So Brian is 75 inches tall. The mean for guys is 69 inches. The standard deviation is 3. What is Brian's z-score? Brian is 75 inches tall. The mean is 69. 75, 69. And the standard deviation is 3. Brian's z-score is what? 2. Nin, 50 points right there. You're right. 200 point max today. 75, 69, 3. And that's the z-score, which says Brian is 2 standard deviations above the mean. If a guy is 5'9", he would be exactly the mean, and he would have a z-score of 0. He'd be scaled to 0. And it just means he's exactly the mean. Anyone who has a negative z-score is below the mean. Anyone who has a positive z-score is above the mean. Anyone who has a z-score of 0 is the mean. So is an average of 0. So it's not bad. It just means you are the mean. You can do this right here. I don't like this method, but this is where you scale, as I was saying previously, between 0 and 1. It's just, I do z-scores. So this is the scaling between 0 and 1, where 0 is the smallest value and 1's the maximum. So you're literally just creating a scale right here where the range is this, and then you're seeing how far up it is. So the highest could be the maximum, which would this be max minus min over max minus min, which would be range over range, which would be 1. So this is just scaling it across the range of the values. And then if you did the min, it'd be min minus min, which is 0. And then max minus min, doesn't matter what that is. It's 0 over some value, which is 0. So the lowest value becomes, the minimum becomes 0, which is the lowest value, and the maximum becomes 1. So you're scaling between 0 and 1. So you could scale between any range of values, but use 0 and 1. Handling categorical variables, really briefly on this. Categorical variables are handled pretty interestingly. Don't expect tons on the test on this. It's just we have to have a way to handle them, and it works better when they're ordinal. So we have here ordinal categorical variables, and we have here nominal categorical variables. So it makes more sense if you have something like small, medium, large, that you could say like small is 1 and medium is 2 and large is 3, and you could do distances like that. But a lot of times we have things that are just nominal categorical variables. Here's an ordinal one, and right here we have if A and B have different levels, if A and B have the same levels. Now, what are we analyzing? It was said previously, so I might repeat it for you. This right here is the dissimilarity. So this is a value of dissimilarity. So when we were doing the Euclidean distance, the smallest Euclidean distance was what? What was, for 50 points, the smallest Euclidean distance two things can have? 0, nin, 50 points right there. Yep, that's the smallest Euclidean distance. Yep, because that means that they're the same in all their characteristics. 50 points, all those answers. You guys are doing excellent today. Y'all are doing excellent today. There we go. And then we go right here, and we go to 0. And if you notice right here, this means they have the same level. So this is for categorical variables. If we were talking about quantitative variables, we're going to go back in time right here, and you can see how we analyze the quantitative differences right here. So this is quantitative differences right here. Stats Nation, Les Keaton, so good to see you. Keaton, 200 points right there. Keaton, so good to see you. Check out the start of this stream right here. Check out like 10 minutes backwards. I was talking about giving away some Volapalooza shirts. Keaton, check it out. And here we go, looking at the Euclidean distance. And I'm sure Keaton knows about those z-scores that we were talking about just a moment ago, and handling the categorical variables. And our whole goal right here is just to see if they have the same levels or different levels and how similar / dissimilar there are. Unlike in regression where we incorporate L levels of categorical variables, we define a set of levels L minus 1. All levels will receive an indicator variable. So it's basically like, is something green or not green? Is it blue or not blue? So we're not going to do like blue is the reference level. We're going to do it's either blue or not blue, and do they share that characteristic right here? So the scaling of variables should happen before converting categorical variables into indicator variables. So we're going to scale the variables, and then we're going to convert. So everything right here, scaling of the numeric variables should happen before converting the categorical variables into indicator variables. So we're not going to scale the indicator variables. And a lot of the algorithms will do this for us. So we've got the code here to do it, but a lot of the algorithms nowadays will convert these to indicators to figure out if things are dissimilar or similar. So if there was somebody, is there anybody in the class to me right now who has the same, who has a value of 0 for color of t-shirt? Does anyone in class right now have a value of 0 for color of t-shirt with Brian? Does anyone have a value of 0 for color of t-shirt? Anybody? Bueller? No. Does anyone have a value of 0 for color of t-shirt with Brian? Which that's a categorical variable. 0.1. You can either have 0 or 1. What is your value of t-shirt with Brian right now? What is your value of color of t-shirt? Sarah's wearing a blue shirt, it sounds like. So Vedrina's wearing not a blue t-shirt. Nitin's wearing blue. Adam's wearing blue. So you can see who's wearing blue t-shirt and who's not wearing blue t-shirt. So the people typing 1 in the chat should not be wearing a blue t-shirt. The people typing 0 in the chat should be wearing a blue t-shirt. So, or some sort of, if this is purple, whatever this is, I don't know. It's purple, it's blue. It's something that you found similar enough to what you're wearing. So, oh, Andrew, there you go. Andrew, the answer is 0. Same color. So it's kind of purple. It like changes colors. We could change the lighting. We could, oh, my lighting doesn't change colors today. So, so then we continue on right here. And we see right here, it is contentious issue whether to scale your indicator variables or not. I don't do it. In my opinion, you should create sets of indicator variables that are equal to 0 to 1 and scaling them. Sure. Most procedures just create indicator variables that are 0, 1s. That's what I was saying, is most just do the indicator variables for you. The opinion is split to whether to scale them or not. There will be some situations where one method likes better and others that favor it. Yeah, most procedures in Sonar won't scale them. Like I said, just let the procedure do it. I mean, the good thing is you can always look at the literature and see what the literature is saying to do. And these methods will advance as time goes on. We figure out better ways to do stuff in statistics, and then we have reasoning behind it. We're not just like, oh, this is better for random reasons. We try to say, like, here's what the research suggests on it, that this is what we should be doing, the best practice for dealing with data. And we just learn as time goes on. So, 5-10 years from now, we might have a better opinion on this. But right now we're like, scale those indicators? I don't know. K-means. This is awesome. We're up to K-means. We talked about nearest neighbors a little bit yesterday, and we're talking about K-means now. So let's go and draw some graphics right here. Hopping over here to the main screen, not snipping tool. Go away, snipping tool. Okay, so what is K-means? Well, the K in K nearest neighbors was how many nearest neighbors you had. So make sure you watch yesterday's lecture to understand the K in K nearest neighbors was how many nearest neighbors you had. Now the K in K-means is how many whats there are. The K in K-means, when we say K-means, it's talking about what? The K in K-means is talking about how many whats there'll be. The K in K-means is talking about how many whats there'll be. 100 points, first person who knows. The K in K-means is talking about what? How many whats there'll be. Close, good guess right there, Sarah. Close. And so K-means and K nearest neighbors are two different things. The K in K-means means how many nearest neighbors we'll take into consideration. The K in K-means means how many. So one thing, listen, and this is what it makes sense once you like, okay, wait a minute. The K in K nearest neighbors is how many nearest neighbors. Nitin right there, 50 points, you're right. Or did I say 100? Whatever I said you got. It's how many means there'll be. So the K in K nearest neighbors is how many nearest neighbors will be used in the algorithm. Once again, to review that very quickly, we went in greater detail yesterday, is like if you have a whole bunch of people, the amount of people voting on something, so we could draw, let's do this right here. So the amount of people voting, like if we vote on this area right here and it's K nearest neighbor 2, then these two people would probably vote on what that area is. They'd be like, I vote it's this, and I vote it's this, and then we'd average their votes. If it's quantitative, we'd average it. If it's categorical, we would take the majority level. But if it's K nearest neighbor 3, then these 3 people would vote on this area. They'd say, I vote it's this, and I vote it's this. So if they're voting on maybe if someone will buy a product, the 3 nearest neighbors to it will vote. And like, we'd say like, okay, this person bought the product, this person brought the product, this person did not buy the product. So if there was a theoretical person here, would we vote that that person buys the product or not buys the product? What would we vote for that red circle right there? That they bought the product or did not buy the product? That red circle, we would vote that it buys it. Yep, because their 3 nearest neighbors buy it. So the 3 nearest neighbors to where that is, which are going to give us an indication of what people would do in that area, but the 3 nearest neighbors to it are going to be the one, we're going to say that person there would buy the product because their nearest neighbors are voting that they bought the product. So then what the heck is k-means? Well, I did something here, and this pattern is very indicative of k-means 2. So I drew a pattern that is something you would get with k-means 2 because, and it's probably k-means 2. You could do a k-means 3. K-means is though we put a mean here and a mean here. And look, it's like kind of like we got 2 different whats of data. What's that word for 100 points first person? What's the word? It's kind of like we got 2 different whats of data. Kind of looks like we got 2 different whats of data. This would be k-means 2 because there's 2 good right there. 100 points, Madeline and Caroline. So remember, 200 points today. We have 2 different clusters. Don't worry, 100 points right there. So 2 different clusters of data. So you got cluster 1 and you got cluster 2 down here. And so we got 2 different clusters of data. And we'll see this in the notes as we look at some k-means right here. Let's look at k-means. Okay, so with k-means, the whole point of this right here is to figure out the similar characteristics and then create kind of is it called a centroid? I think it's called a centroid. I think, is that in term of the notes? Might be, we'll find out. But to create this like center mean, it is a mean, and it's going to be like what the middle of that cluster is. So centroid, I guess, works. And here we are. You can see it. And there's a different scaling in this. Sorry, it's going to look a little bit weird here. I wish I could stretch the graphic, but I noticed this last semester with the new notes that the X2 scale is scaled differently. So it might look a little bit odd as you see what happens right here in the algorithm. And it looks a little bit odd on the distances, but this is the biggest thing I can show you. So let's talk about the k-mean algorithm and how it works. So when the k-mean algorithm works, listen very carefully to this. This is on your assignments, and you have to understand very exactly how it works. When the k-mean algorithm works, I'm saying everything that's in the notes. Step 1 is to pick 2 random spots. If this is k-means 2, now you could use k-mean 3 and it would pick 3 random spots. The k-mean algorithm works by picking random spots for the means. Random spots. Does everyone understand? These are just, how are those picked? Randomly. Dang, I can't hit the button. I want to hit that button every time now. But we pick 2 random spots. We'll play Monster Cap $5 probably eventually and get our music back. So we have here k-means, the first mean center and the second mean. The first, second doesn't matter. It's just, this is k-means 2. How do you know it's k-means 2? Well, like in this algorithm right here, this is using k-means 3, and we're seeing iterations of it. We could also see patterns that are indicative of like k-means 4. I know we have a k-means 4 in here. Am I going mad? Here is k-means. Oh no, don't tell me I removed that. It's like my favorite graphic. That's why I don't like these slides. Here's k-means 4. There it is. Here's k-means 4, where you can see right here 4 different cluster centers. And we'll talk about how to know whether to use k-means 2, 3, 4, 5, 6, 7, 8, however high of means you want. But does everyone see the difference here where there's 4 cluster centers, where in this previous padding, way back here, you mainly have 2 cluster centers. Now, we're not going to pick this, but you can kind of visually see there's a group here and there's a group here. Does everyone see it's like there's 2 clusters in the data? So you're not going to pick this yourself. I'll explain more in a moment how to pick it, but we need to figure out where the cluster centers are. Now you might say, Brian, I think the cluster center's here, and I think the other cluster center's here. It's probably pretty good guesses, but we're not going to use our way of guessing this. We're going to use an algorithm. The first step of the algorithm is to pick the amount of to pick the cluster centers we want, the k amount of clusters, like k2. This is k-means 2. Pick the centers randomly. Step 1. Write down step 1 right now. Put it in the chat for 20 points. Step 1, pick cluster centers randomly. Pick cluster centers. Yes. I want to climb K2. 20 points, Andrew, right there. We pick the cluster centers randomly. So pick the cluster centers randomly. Step 2, assign the group identification by how close things are. Now, I'm very sorry. It looks like this red one right here is closer to the black. It's because of the scaling on the axis right here. I did notice this last semester, and I'm remembering it now. But we were trying to condense the slides a little bit, and this graphic has been distorted. Very, very sorry for that. It blew my mind last semester, and I'm like, oh, yeah, this is like the one thing I don't like about these slides since we like condensed them, but we made it less slides and easier to go through. But I promise you, if we don't have the axis distorted, it's actually closer to the red right here. So we're going to assign all things that are closest to the black to be closest to the black. They're going to be assigned that they are group black, and then these are group red right here. And now what we do, so step 2, assign cluster identification to the points that are closest to those cluster centers. Step 2, assign cluster identification to the points that are closest to that cluster, to that mean. Assign cluster identification to the points that are closest to the mean. So this point right here, this red one, is assigned red because it's closest to that. This black one right here is assigned black because it's closest to this. And it's very sorry for the distortion. Andrew, 100 points. Great job putting those notes in the chat right there. And Madeline. So assign the cluster identification according to which one points are closest to the mean. Yep. And then step 3, redo your cluster centers. So now we update the center of the clusters such that you notice the red moves over here because this is the middle of the red. So now we redo where the cluster centers are at because now we're just going to go to the mean of the red points and the mean of the black points. And guess what we then do? We reassign the cluster memberships. We go back to step 2. So we reassign the memberships now, and then we update the cluster centers. And then we reassign the memberships, and we update the cluster centers. We just keep doing this repeatedly, and these are called iterations right here. So we're going to keep doing iterations. How many iterations we do is when we reassign the cluster centers, and then we will assign cluster IDs, move the cluster centers. 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 And you keep doing this till you reach what is called convergence, which means the answer does not change because you find this right here. This is probably convergence because if you were to reassign cluster IDs, they'd come out the same IDs. So we've reached what is called convergence. If you notice, I thought the cluster center was here and the other cluster center was here, but I was wrong. The algorithm found this. Now, this might not be the right answer. More on that in a moment. But does everyone understand the process right here? We start the algorithm by randomly picking 2 spots if we're doing k-means 2. If we're doing k-means 3, we randomly pick 3 means. And then we assign the IDs by which points are closest to those means. Then we move the cluster centers. Then we reassign the IDs. Then we move the cluster centers. Then we reassign the IDs and we remove the cluster centers. When you reassign the IDs and you move the cluster center and you keep doing that, that is called what's is. It's in the notes here somewhere, I bet. That's called iterations. That's a really good question, Anisha, right there. 100 points, Anisha. We do not know, and there's going to be a code in here called itermax. So in the k-means algorithm, there's an argument, called itermax. And itermax is the maximum amount of iterations you'll let it go through until it reaches convergence or doesn't. So convergence can be achieved. When is it appropriate to use this algorithm? When you want to create clusters to describe your data. Like if you have let's say we're trying to market clothing to people, and then we want to figure out who are our customers likely to buy clothing. So we could or likely to buy the new product. Like when we put out new products, who's the customers most likely to buy it? So we have a new product line coming out and we want to send out really nice flyers to people. And we only want to send those flyers to our customers who are likely to buy it. So then we could create these clusters right here of customers. And we could say, okay, what are the characteristics of the people who are likely to buy and what are the characteristics of people who are not likely to buy? And we're trying to kind of describe this going on right here. It's more of a predictive model, so it might be bordering on a little bit should we be using it for that? But we want to describe the characteristics of people who are likely to buy and describe the characteristics of people who are not likely to buy. And it's going to try to assign these cluster centers and figure out the variation in our data. And so we can use this right here. We can also use it for other techniques just to say like, what kind of groups of customers do we have? So let me clarify, Sarah. Probably a better way is if we work for this clothing retailer, we're talking about clothing all today, and we say like, okay, we have 1 million customers. We're American Eagle, and we have 1 million customers. What like are our groups of customers? So we'd create like the different groups of customers we have. Got to go way back in time right here. And here's our different groups of customers. So we could create a bunch of different groups of customers and then create marketing strategies for these groups of customers. So we would say, okay, here's all the characteristics of our customers, and then how many like different groups of customers do we have? Because then the customers who are clustered around a mean are very similar in what they do. Because if we find a really good like clustering scheme, then it'll limit the variation within the cluster. So it's basically putting like-minded things together, saying that these customers share all these characteristics, not like they're perfectly identical, but when you look at the clustering scheme right here, you'll see that we're trying to obtain things that are very close to each other. The goal is, and especially if you get a really good clustering scheme, like the dream is to get something like this. Now, this is so obvious that we can see the answer that there's a cluster here, there's a cluster here, there's a cluster here, there's a cluster here. So when we do the marketing, these people will get the same marketing, these people get the same marketing, these people get the same marketing, these people get the same marketing. And once again, there is no right answer. You could do k means 2, and you'd get these people and these people. So if you did k means 2, you'd have a group here, and you'd have a group over here. That's k means 2. But this looks more like k means 4. So k means 4 means there's 4 separate means of centered of data. So basically figuring out the right way to do this right here. So the big thing is knowing how this works. Once again, let me repeat the process. You should have it memorized. Sorry, I missed. How do you decide to move a new point to the cluster? You reassign based on what is closest. So once again, we'll do the steps again. Very important to know these. You pick your cluster centers randomly, which is going to come up here in just a moment. We pick our cluster centers randomly. Then we assign the cluster IDs by what is closest. This point right here is black because it's closest to this. This point right here is red because it's closest to this. Now we reassign the cluster centers. So we move the cluster centers. And after we move the cluster centers, we then update the points again. And after we update the points, we move the cluster centers again. And after we move the cluster centers, we update the points. And after we update the points, we move the cluster centers. So you literally get this iterative process where it starts moving around the centers based on where it's assigning it, and then it stops. And when it stops, it's probably reached convergence, or it's reached the max amount of iterations, because you don't want it to continue indefinitely. Like you're like, okay, you can do like 100 iterations until you reach convergence. So we reach it until we do convergence or max iterations. Slide should say max iterations. So the iterations are when it moves it and then reassigns the cluster centers. Reassigns the points and then moves the cluster centers, reassigns the points, moves the cluster centers, reassigns the points. And you can see it right here happening, that we're moving the cluster centers, and then look, the red and the black dots will change. And you see there's different red and black dots. And now because of that, we're going to move the cluster centers again to where the center of those are. So we keep moving the cluster centers to the center of all the data, and then we reassign the points to see what's closest to these new centers. Does that make sense, Anisha? Like every time we move the centers, we have to reassign the points to what is closest to the new center. But now since we reassigned the points, we have to move the cluster centers. And since we move the cluster centers, we have to reassign the points to what's the closest to those cluster centers. But then we have to remove the cluster centers. So this is the iterative process right here. This is the iterations you go through, and hopefully you reach convergence. So when you're welcome. That's excellent. And there's an important thing I kept saying that would come into play right here. And the important thing that comes into play is we have to redo this. K-tools and for predictive is not a tool for predictive. That's why I corrected myself. It's more for descriptive. I've done it for predictive. Maybe I shouldn't. But it's more a tool for descriptive to describe the different groups in our data set. So you wouldn't really want to use it to predict if someone's going to buy a product. That's why I reversed my example. I was like, we should probably use it for identifying different groups of clusters in our data set as descriptive analysis, not predictive, not predicting if someone will buy a product. It's better practice to use it to explain the different segments of our data, like the different customers we have, to explain their characteristics and to put them into these are our customers who are our low buying customers. These are our champions. So using it right there, I've done things you shouldn't do in statistics sometimes, but different initial, this is it. This is the big thing I kept alluding to. we pick our cluster centers what when we start the algorithm? I want to press the button. But I don't want ads on the video from Monstercat taking the video back. So how do we pick randomly? You guys know it when Brian gets sad because he wants to press the random button. But we pick our cluster centers randomly. So because we pick our cluster centers randomly, that means that the answer we get at the end is based on randomness. So had we picked different cluster centers, we would pick different random starting points, we'd get different answers. And maybe Nitin, this, like, when you think about, like, in calculus, like local mins and local maxes, probably a lot of other people, what Nitin was saying yesterday, like doing some mathematics. But when you think about this, we could get into like a local min when we're trying to reduce the distances within these clusters, because the clusters are meant to be as tightly clustered as possible. But if you pick a random starting point, you'll get an answer that could be based on that. So you might get a local min, but you might not get the global min for the reduction in sums of squared error. More on that in a moment, or within cluster sums of squares. But so if you look at this, what do we have to do after we run the algorithm? We have to run the algorithm again. So when you run the algorithm, you actually have to repeat the algorithm. So you notice right here the max iterations. This is the iterations it's going through until convergence. So that's the max iterations right there. And we'll look more at the k-means. So this right here, yep. And even if it converges, that means we might have just found a local min. So how do we, to like make sure we have the best k-means, what do we do after we run the algorithm? We run the algorithm again. Because just because we run the algorithm one time doesn't mean we have the right answer. Maybe because our answer is based on the what points we picked, the what starting points. The answer we get will be based on our what starting points. The answer we get will be based on our what starting points. Favorite word ever. Yep. The answer we get will be based on those random starting points. So that's a key thing, that these points are chose randomly, and our answer could be like not the best answer. So what do? We start the algorithm again, and we go through until we get to convergence and we get a new answer. And this is showing you on this slide right here, the algorithm ran multiple times. I think we ran it like 3 times, and we got 3 different sets of answers. And this is k-means 3. That's why you see 3 different colored stars in here. So very important. This right here is the within cluster sums of squares, and our objective is to reduce this within cluster sums of squares. Within cluster sums of squares. So let's think about this. The way this would be calculated, let's go back to the previous slide and let's draw on this. Let's grab it and draw on it. I need to go off this for a moment here. So let's grab it and let's draw it. So we're going to use the green dot. Let's hop over here to the main screen. New slide. Hop over. Let's do it. Okay. So when you think about within cluster sums of squares, let's just say for a moment that this right here, this green thing right here is a cluster. I'm going to draw it as a cluster. Let's just call this a cluster. So that's a cluster. What is the within cluster sums of squares? If you look at the mathematics of it, it's the observations distance. So we take each of, we're going to take the sum of each of, is it a y or is it an x? I think it's an x. I'm pretty sure it's an x. Let's go with x. So we're going to go to each x, and we're going to go through all of them. We're going to sum up all of them. We're going to take its distance from its cluster ID. So we'll just put ID for the moment. And then we're going to square that, and we're going to do the sum of each of these. So we're going to take the sum of the squared difference. So it's the sum of all the squared distances from the means for that cluster ID. It's a little shorthand of it. It is here on the notes. So you can see what's going on right here when we actually put it out like this. There it is, from the mean of cluster center 1. There it is in the set of x's. So it's for all the x's. Yep. Okay. So we're looking at this cluster ID right here, and it's the sum of the squared differences. So it's the within cluster sums of squares. What does this look like visually? If you look at this point right here, that's its distance. And what are we going to do to that distance? What am I going to do to that distance? Yep, sum of the square distance of all the, yep. And then you're seeing it. You see it with the equation, and you got it. What am I going to do to that red distance? What am I going to do to this red distance? What am I going to do to all of these? That's a horrible line. What am I going to do to all of these distances right here? Like, what is this equation actually measuring? Square them. Yep, I'm going to square all these distances. I'm going to take all of these distances. These points are away. I'm going to square these differences, and then what am I going to do to them? I'm going to take all these distances. I'm going to square all these distances, and then I'm going to sum them up. So it's going to be the sum of it's going to be the within cluster sums of squared distances that they are away from their cluster center. Does that make sense? Like what this mathematics calculates right here? It calculates a numeric value. Now, what would you like this to be? What value would you like this to be? You want this to be as close to what as you can. What is your goal with this within cluster sums of squares? What would you love that to be? Boom, Caroline, 100 points, exact answer. You want it to be 0. You love it to be, because it's going to be like if it were to be 0, everything would be it would be on the cluster center. Does that make sense? If it was 0, you would just be like, and everything would be sucked in. Visuals like this is the things you want to think about, because this is what this is calculating. It's calculating the distance a point is away from its cluster ID. We're squaring that because then we want it to be like an always positive distance. Then we're adding up how much the distances are away. So you want, like, if you look at like a tightly clustered thing, like let's say this is a different cluster over here and it's just that. This would have a smaller sums of squares. You'd be squaring up all these things and it would have a smaller sums of squares. You want as close to 0 as you can get. Closer to 0, the better. For within cluster sums of squares, you'd want it closer to 0. And see, these are good test questions. Like what is the optimum within cluster sums of squares? 0, 0.05, 1, 100. Oh, that's a good test. Someone put that in the potential test questions. Wait, wrong button. Like that's such the reason. Like what is your ideal within cluster sums of squares would be 0. And the goal is that you reduce the variation within the clusters, that the clusters are all the same thing. I mean, you don't ever really achieve 0, and we will talk more on that in a moment. But the closer to 0, the better. They would all have to be exactly on the cluster center, which really doesn't happen. I mean, you're not going to see 0. 0 is the winner. It's really, you're not going to really get 0. You'll get you're lucky if you get small stuff, and I'll show you more on that in a moment, because we'll say like, well, what is a good within cluster sums of squares? The ideal within cluster sums of squares is 0. Like that's the goal, is to like reduce all variation within the clusters. So then all the clusters would be just on the point. They'd be on the mean of the cluster. And if you had that happen, you'd like hit the jackpot. You'd have like, oh, everything, these 3 cluster centers explain all the data, and it'd probably be some trivial solution. Like it'd be some like, everyone would know it, like, well, of course, people who are athletes are, and people who are not athletes are this. It'd be some trivial thing that like really wouldn't help you make decisions. So it'd probably be interesting that the strongest or the best clustering schemes might be so trivial that they don't really help us do anything of importance. Like we already would know it. Like the marketing team would be like, well, yeah, of course we know that. So we'll take a look right here. So the k-means algorithm provides a decent way to get a solution. It's important to redo the k-algorithm many times. We've said this a bunch right here. The reason is because the k-algorithm starts with random starting points. So you need to redo it. The computer will do this for you. This is the repeats. So an argument in k-means algorithm is your repeats argument, and the argument of repeats will redo the algorithm. So increasing k by 1 will always make the time. Yes, this is an easy true false right here. Because if you put more cluster centers right here, you will get smaller within cluster sums of squares, because you're allowing for more means. And if you allow for more means, like imagine this. If there are on this screen right now 200 points, what would the within cluster sums of squares be with k means 200? So there we go. We just showed a trivial solution. If there are 200 points on the screen, what would be the within cluster sums of squares of k means 200? If there are 200 points on the screen, which means we make 200 means for 200 points. 50 points right there. It'd be 0. Because every point would be its own mean. Like this would get its own mean, this would get its own mean, this would get its own mean, and everything would be right on top of its mean. So the answer would be completely trivial, and that's not the point of clustering. The point of clustering is not to have 200 clusters, because maybe if you have like a data set of 30 million, I don't know. But if you have 200 clusters, that's not really practical. And then we get into practical significance. Like, would you really utilize the information of 200 different clusters? So you can achieve a within cluster sums of squares of 0 by just increasing your cluster centers. So we really want to make sure we give this right balance. And so you will always reduce the amount. And the biggest thing, choosing the amount of clusters is an art. And how do we do that art? with an elbow plot. And so here it is right here. So the elbow plot is the following. Here is a good elbow, and here's a bad elbow. So bad elbow, good elbow. Bad elbow, be doing it with me. Who's doing it with me right now? Be like, bad elbow, good elbow. Bad elbow, good elbow. Bad elbow, good elbow. So once again, like that right there. So you got good elbow. This is good elbow. Bad elbow, good elbow. And you got to see it from the angle. There's the microphone in the way. Bad elbow, good elbow. Bad elbow, good elbow. Okay. 5 second stretch time. Everybody, let's do our, we should start class with that. Let's do our elbow stretches. You ready? You ready? Here we go. Bad elbow, good elbow. Bad elbow. I'm afraid I'm going to hit the mic because the mic's like really just right in front of me right there. So bad elbow, is this a good elbow or a bad elbow? Is this a good elbow or a bad elbow? Good elbow, bad elbow. Do you see the elbow? Ooh. Is it bad elbow, good elbow? Oh, this is an amazing elbow. This is like top tier elbow. And what does this elbow plot mean? We're looking at the within cluster sums of squares. And the within cluster sums of squares will always go down when you add more centers. So this is us adding centers. As you go across this right here, you're adding more centers to it. So you're just allowing for more means. K-means 1 with the following plot would look like, why don't we put the plot right next to it? Was it back there? Was it really all the way? Am I losing my mind? I might be losing my mind. Here it is. K-means 1 with the data right here would have a mean right here. Look at all the squared distances from this. Now K-means 2 would put a cluster center here, or right in there rather. See, because this is a cluster. And here's the second cluster. Does everyone see if you use K-means 2, it's going to reduce like the within cluster sums of squares by a good bit. But we would see the reduction in within cluster sums of squares get significantly smaller after we reach a K-means what here. When you reach a K-means what, increasing cluster centers really won't do much. Like if we increase cluster centers after this, it's really not, yep. And so here's your cluster center here, 1, 2, 3, 4, and the elbow plot, which should be previous slide or next slide, the elbow plot right here shows this, that when you achieve K-means 4, increasing cluster centers will always decrease within cluster sums of squares. Like adding more cluster centers will always decrease it, but after you go to the 4th cluster center, you're not getting a really good return. And that's actually what you want to see. You want to see there's like a clear point where like, okay, this should have 4 cluster centers. Does everyone see why this is a good thing? The elbow plot looking like this means the choice is obvious. The sharper the elbow, the more obvious the choice is. So that's why this is a good elbow and that is a bad elbow because it constantly just goes down at like a slope. You don't want just little decreases and not telling. So this is not the worst elbow in the world, but it's, is what we generally see. And at this point, how many K-means would you pick for this? I would say there's 3 acceptable answers for this. How many K-means would you pick for this? It's on the slide. I was thinking people might say 6, and I think it says down here, the elbow rule would suggest K-means. You see, it literally says in his judgment. That's Dr. Petrie in that right there. So I'm thinking in this range. I'm thinking that's where the elbow is. So you have to think of this as an arm, and you have to think, can you see the elbow in the plot? And so if you think, where's the elbow? Someone might say the elbow's here. Someone might say the elbow's here and here. I'm kind of leaning towards 4 with like a plus or minus on it. How do you know? Wait, Sarah, 50 points. Great question. Where does it say it? It literally says, oh, it said it. Where did it say it? Here, right here. Perfect. It's an art, not a science. One of my favorite, there's a Rick and Morty quote from season 1 where I think he says, Morty, sometimes science is more art than science. So, how do you know? You just look at it. Sometimes science is more art than science. I think that's in the, I used to know the name of the episode. It's the one where everyone turns into, those creatures after they turn into like, I don't know. It's the crazy one. It's the crazy Rick and Morty episode. So right here, we see a sharp elbow. If someone told me this wasn't K-means 4, they'd be, this is the science. This is K-means 4. Does it make sense why this is K-means 4 and it's obvious? It's obvious that this is K-means 4 if you look at the graphic to cheat, you can be like, yeah, there's 4 clusters. And then when you look at the elbow plot, it's like, okay, there's 4 clusters. That's where we see a stop. You're always going to see a reduction in within cluster sum of squares. The within cluster sum of squares are always going to decrease, but the sharp decrease stops here. We don't see a continuing good amount of decrease as we increase the within cluster sum, as we increase the clusters. So we don't see a good decrease anymore because it'll always go down. And so you notice that in this one, that it's going down, but I would say it's in this range is where the stopping point is. But what one's the answer? And that's the thing. Like if we make 3 clusters, we might have like our top tier customers, our middle tier, and our low tier customers. So we might have like the customers we're going to like highly market to, the medium market customers, the low market. If we do 4 groups, we might have like the customers that we, that are high brand, low, medium, and low, and then the customers we've lost. So Sarah, you bring up an amazing point, because what we're going to do right here, and we'll see this in a moment, is if we start with 3, we're going to look at 3 clusters. So take a note on this. You ready? These are the things you should write down. And these are things I put on the test. When I start saying this, I'm like, this is a test question. If you make 3 clusters, you look at the 3 clusters to see if it's a good, like a marketing scheme you would use, and to see if it makes sense. And if 3 clusters make sense, what do you do next? If you look at the 3 cluster scheme, the way they're broken apart into 3 clusters, and it makes sense, what do you do next? You would look at what? If you make 3 clusters, you try 4. And if 4 makes sense, what do you do? If 4 makes sense, what do you do? If 4 makes sense, what do you do next? So you explore 4 and you're like, well, 4 makes sense. 4 looks like a good clustering scheme. Try 5. Guess what? Crazy thing happened. 5 made sense. 5 also made sense. You're like, 5's a really good clustering scheme. I think 5 makes sense. What are you going to do now? 5 made sense. You're like, 5 makes sense. Try 6. 6 doesn't make sense. Go back to 5. And what do we mean by makes sense? Gives like new information. And you might start low. You might start with like 3 clusters and be like, okay, does 3 make sense? It makes sense. Does 4 make sense? 4 does not make sense. I'm going to go back to 3. So you have to look at these things and investigate, because this is where the math stops. The math stops here. We're not looking at just numeric measurements. We're like being like, how would I use this? So we'll look at these clusters here in a second. You'll see the next part of these notes is like looking at the clusters. Yeah, so just the amount of clusters, all this good stuff, K-means philosophy. So a message tailored to every individual would be high cost, a generic master mouse for low cost. So the goal of like this is to put all like-minded. What does it mean for it to make sense? Great question right there. Like, can we utilize it? So we're trying to like make a message or do a marketing scheme to like a group of customers. So if 4 doesn't make sense, you go back to 3. Great question right there. And so our goal is like, if you are doing marketing for like, let's do Cinnabon. I just really want a Cinnabon. Those things are horrible for you, but they're so amazing. And you're doing marketing for Cinnabon, and you're not going to make a tailored message to every single customer. You're not going to be like, hi, Brian, we think this about you, and da-da-da-da-da. It would take too long. I mean, maybe one day we'll be able to figure out how to make tailored messages to everybody. But you're like, okay, Brian is in the group of college students. Brian's in the group of like young adults. We'll call Brian a young adult. And Brian's a young adult person, and he's a young adult, high-value customer. If we get Brian eating Cinnabons every day, we need to get him on a morning Cinnabon. So Cinnabon opens next to campus, and we're going to try to get Brian to be a morning Cinnabon person, because we know Brian likes coffee. We know Brian likes Cinnabons. So we feel like Brian could be a high-value customer. Like going off of what we notice about him and his characteristics, we're putting him into this high-value thing of we could possibly, practical significance. Sarah, 100 points. That's perfect answer. It's practical significance. Like, does this matter? How can we utilize this? And if you don't find 4 clusters practically significant, you go back to 3. Like, can I utilize this? What can I do with this? And it's all practical significance. Like, because you're going to have statistical significance with these, or like there's no real p-value, but the algorithm's going to find things that are not by random chance. Like, if there might be a way to get p-values, but we don't worry about p-values here. So more clusters equals more cost. So we might go towards less clustering schemes. We might try to go towards like a 3 or 4. That's why you wouldn't go to like a 50 clustering scheme. I don't know if anyone's ever done that. I haven't. So imagine a writer charges us $1,000 per tailored message. I'm going to go to the airline example, I think. The right way to choose K. So once again here, if 2 or more clusters have no meaningful differences, fit a scheme with 1 fewer clusters and try again. If 2 clusters have meaningful differences, try going higher. So this is the thing. If 4 works, we go to 5. If 4 doesn't work, we go to 3. So does everyone see how this works? You pick your point. Like, let's say we pick 6. Tell me, did 6 work or not work? So tell me, did 6 clusters seem like a good scheme or bad scheme? Tell me, I know it's just theoretical. It's just like Brian picked 6 clusters. And did it work for Brian? Did he say, that makes sense or doesn't make sense? It was bad. So since it was bad, Brian will do what now? Since it was bad, which we're just making this up, since 6 was bad, Brian's choice will be to try what now? Since 6 was a bad clustering scheme, go back to 5. 5 was also bad. 5's also like, I don't think this 5 clustering scheme is going to go well. Then we're going to go to 4. And we could do a different thing. Like if we had picked 6 and 6 had went well, we'd go to 7. And if 7 goes well, we go to 8. So we look at it and see if we see meaningful differences. Like, do we have practical significance? Do we have a way of utilizing this information? And repeat all this. And interesting, just you go through this. This is the hard part this is the literal business side of it. This is the hard part. And we can make a table of the values, and you're going to see it right here. Let me go to the American Airlines example. I like the American Airlines example. It's my favorite one. Please tell me we didn't remove it. Here it is. So, yes. I want to look at it this way, though. Okay. So here's the American Airlines example. And I wish, did we give, here's the elbow plot. Okay. So here's the elbow plot. So when do you stop? Like if we try 6 and it's bad, and we try 5 and it's bad, and we try 4 and it's good, I'd probably stop at 4. Because you could look at 3. There's no you don't have to look. You can if you want, but you might then compare 3 to 4. And if you think 3 is bad, you could go back to 4. So could there be a case where the business wouldn't allow the optimum amount? Yeah. Yeah, that's the thing too. Jordan, amazing, because the business might dictate we want k-means 4. They might say we want 4 clusters. And you'd be like, well, it works better with 3. And they'd be like, but we want 4. And you'd be like, okay, we're doing k-means 4. It looks like that's what you want. You want 4 customer groups, even though there's no meaningful differences. I don't see meaningful. It's like, I'm the stats person. But you want 4, so we'll do k-means 4. Yeah. And wait, remember the key to this. Is there a right answer to clustering? This is so huge. Is there a right answer to clustering? Is there a right answer? We should see a resounding 1 in the chat for 20 points. Is there a right answer to clustering? Can we get the right answer? The answer is a resounding what? No. 20 points. Yeah, the answer is no. There's no right answer. There's no, we figured out the clustering. So that's why we don't use it for predictive, really. We use it for descriptive because you can describe things in any ways. So, oh, I'm so sorry. I'm so sorry. There's no right answer. So when the business is like, you have to do a clustering scheme of 4, K4, you'd be like, okay, I'll do it. So here we go. We're looking at the characteristics. What's the first thing we're going to do with our data? Is we're going to take our data, we're going to transform it for normality. And so you see right here, we've got our data, we've got it scaled and transformed. So we're trying to make data that's slightly normal because we looked at the data and we saw that it has a lot of skew. Like look at this bonus miles right here. Oh my gosh, this bonus miles, someone's got 250,000 bonus miles. I've got some bonus miles, got to figure out what to do with those. And then right here you see we can take and look at it and we can do some algorithms on it. We can make it normal and we're going to scale these like we've been doing right here. So here we logged one of them to make it more normal. So now we have the log of all the data. I guess there's no, yep. Oh, Anisha, you're at 300 points. I know that. All clusters are wrong, some are useful. Anisha, that's awesome. I know that George Box quote. I've got a book signed by him. All clusters are wrong, some are useful. So here, wait, I'll show you guys. Oh, wait, 2 seconds. Another, this I'm not giving away. My dad gave me this. So for those who didn't know, that's a famous quote, especially from 320, but it's a famous quote from George Box. And this is Box Hunter Hunter. And so it should be signed. Here it is right here. But there it is right there. Gotta be careful with the book. There it is, Box Hunter Hunter. And it's my dad's book, my dad being a statistician. But this was his book right here, Wiley Series in Probability and Mathematics and Statistics, signed by, because it's Box Hunter Hunter, and it was signed by Box Hunter Hunter. So that's a prized possession right there. But yeah, famous quote: "All models are wrong. Some are useful." And so Anisha, that is, I'm going to start saying that all clusters are wrong, but some are useful. They're all wrong. None are right. There's no right clustering scheme. And it applies even more to clusters. So thank you, Anisha. That's awesome right there. Good quotes. Definitely earned the points by knowing that. So right here we have, I think I'm back and talking good. We're good. And so what we're going to do is we're going to take our data. A lot of these algorithms, remember, we don't want the data to be on different playing fields because we don't want one characteristic to dominate the clustering scheme. What do we do so that one characteristic does not dominate the clustering scheme? What do we do so that one characteristic does not dominate? And I think the algorithm probably does that for us. Oh, no, it's doing it right here. Here it is. It's right here. I was like, where's that being done? What do we do so that one characteristic does not dominate the clustering scheme? Scale it. Yep. And look at this right here. It's literally taking the whole and saving it as a data frame. We're looking at a histogram afterwards. But the code right here says as.data frame. So it's turning this thing into a data frame and storing it into there. And it's scaling the data frame. So we're going to scale everything, which turns it all to z-scores. So you've got some awesome codes right here. Literally the code scale, if you didn't know it, which I think we did this in an assignment earlier, the code scale literally turns everything into z-scores like that. You want to z-score it? Scale. Done. And then we're just storing the scaled data into a data frame, or we're running a data frame on it and storing it. So the as.data frame takes that and stores it as a data frame. Truthfully, I think it would work even if you didn't do that. Maybe you have to. I don't know. I just a lot of times I'll use the code as is, but I think it would work without it. And right here, we're taking the log 10. Now you might wonder, why are we doing +1? This is a very important thing. This is in your previous assignment too. Someone gets 300 points. We're doing 200 points today, but Anisha's already broken the rules, so someone else is getting 300 points. Why do we have to do +1 right here? Why are we doing the log 10 of all the values in those columns +1? Why are we doing that? And the answer is on this slide. Why are we doing +1? So we're doing the log 10 of those columns, but we have to do log 10 of the value +1. Can't start at 0. Andrew, 300 points. Yep, perfect. These zeros right here are going to be a problem for us because you can't log 10 0. That'll get negative infinity. So the zeros, or to make it positive. Great job, Madeline, right there. You got 300 also. We have to, a lot of times we like for the lowest value to be 1 because if the lowest value is 1, log 10 of 1 is 0. Because what do you have to raise 10 to get 0? You raise 10 to 1. So log 10 of 1 is 0 because you raise 10 to 0 to get 1. It's so confusing with logs. It's just like talking a coded language. Yep, log 10 is 0. Log of 0 does not exist. Does not exist, or is negative infinity? Inside of R, which I think I can show R right here. Come over here, R. Get over here. Get over here. It's horrible. That was the worst Scorpion impression ever. It says negative infinity inside of R. Yeah, don't worry. It's like talking a weird like language no one knows. Only Nitin will explain it to us. Whoever invented logs undo exponentials. So it's like every time I read a log, when you read log of 0, like log 10 of 0, it's what power do you raise 10 to get 0? And you'd raise 10 to, there's no power you raise 10 to get 0. And that's why log 10 of 0 does not exist. So I guess it does not exist. Or it approaches negative infinity, like the limit, right? And then it's going to approach negative infinity, but it never, it's a limit, right? Am I talking correct math here? Real 9 does not include, but I want it to. Knitting 300 points. Definitely correct my mathematics. Yeah. So infinity is not a real number. Infinity does not exist. It's a concept. And you always feel to correct me, especially on the mathematics, because it's funny sometimes when people think like, which is all right, they'll be like, Brian, don't you know this? This is like advanced calculus. And I'll be like, I don't. That's not what I do. I don't do advanced calculus. I do statistics and business analytics. So when we make our cluster centers right here, we're once again going to analyze these. Let's look at the analysis. I hate that it wraps around the screen. So what we're going to notice right here, is there any key characteristics? Now, somebody for 300 points, tell me everything in... You're cracking me up, Nin. Nin, you're at your 300. I do not know at all. Everything inside of here right now is a what. This is very important. You have to know this. I think about the easy questions I can put inside on the test. All of these values, every single one of these values is a what right now. Every single one of these values is a what. because they've been scaled. Hint, hint, hint. Jordan, 300 points. You got it. They're all Z-scores. You have to know that instantaneously that these are all Z-scores. So what do you see any, yes, everyone's saying it gets 300 points. I'm feeling really generous today. Remember, be here tomorrow. Be generous tomorrow, but tomorrow's Friday. Don't miss Fridays. Don't miss Fridays. Test is coming up, and I'll start putting on practice this weekend. Who's our low value customers? Group what? It's not group one, hint, hint. Group what is our low value customers? Group what is our low value customers? It says it on here. Group what is our low value customers? What's our low value customers here? 3. Yep. Nisha, great job right there. Group 3 is our low value customers. They're well below average. And so you see they're below average in all key characteristics. I know this is not a super unusual Z-score, but a Z-score of negative 1.6 is not an outlier. They're below average in everything, and that's decently below average. It's pretty good below average. It's not super below average, but everything's below average, and that's pretty below average, so they're pretty low. So wait. This clustering scheme worked. So what do we do now? This clustering scheme, I'm like, yeah, it kind of worked. We've got our high value-ish. I mean, these people are pretty high right here. Group 1 is pretty above average. Group 2 is kind of average. Group 3 is below average. So since 3 worked, next one, good job right there. Vedrina, you get your 300 day. So right here we go. We're going to go to 4, and immediately this jumps out to me right here. This jumps out right here. This is immediate to me. That jumps out. What else jumps out to me? Nothing there. This jumps out. That jumps out. Ooh. How did I not see this? What in the world am I doing not seeing that? That is look at the notes down here. Wow. I could just read the notes, but what fun is that? So the notes literally tell you the answers. But that jumps out, and see, I'd be iffy here. I'd break from the notes. I might stop at 4. And I don't know about 4. This one down here, maybe it's just our average customers again, like cluster 4. And here's the thing: when you increase the clusters, everything can get jumbled up. This is a keynote. When you increase your clusters, it might jumble up what was in what. It's not like the same people are going to get split off into new clusters. You could have total reassignment of where everyone's at, and cluster 2 is no longer cluster 2. I mean, it could be, but it's going to have maybe new people in it. You can see clusters break apart. So it's not like you just split off a little bit here and make a cluster 5. Everything could get reassigned with more clusters. Here's cluster 5, and it's a little hard to see, but this one just didn't work. We really didn't get anything good. So since there's no actionable insight, there's no real okay, we'd make these groups and call them this. Guess what we do? We go back to cluster 4. So don't worry about the numbers there on that one. It's pretty much we didn't achieve anything better. So with this 4 clustering scheme, what we're going to do now is we're actually going to go to the original values. If you look at the code right here, we're going to take and assign a variable of the cluster IDs. So we are assigning a cluster ID variable to our data frame. And then we're using the super powerful aggregate function in a way you would never expect. We're using a dot right here. So this is all the Y variables aggregated by their IDs. So now we can see every Y variable by the IDs. So look, here's your IDs, and here's every Y variable, and we can look at the median. We could look at the mean, the median, but probably better to look at the median because this won't take outliers into account because due to the skewness of the original data, so we're using the original data values. We're not using our scaled data set. We're not using our transformed data set. We're going back to the original values, like the in context, because we want to talk to the people about what's actually going on right here. So we go to the original data and then we analyze the clusters. And what do we notice? If you notice right here, cluster 2 would be defined by what? Cluster 2 would be our what customers, people who like our whats. I'd say there's 2 key, I see 2 major things. I see 1 major thing. What do you notice about cluster 2? These are the people who we probably need to market to with what? There's 2 key things I would say about them right here. There's 2 key standouts. They have the second most bonus miles. Bonus miles is kind of high, but they're kind of tied for these other ones. Total miles, they have the top total miles, so they're like a very important customers to us. And then also the only ones that have status miles, and this is the median. It's not like no one has status miles in the other ones, but the status miles is a big thing. So if I'm going to market to those people, I'm going to talk to them about their status miles. What would you call a cluster 3 right here? How would you describe, come on, oh my gosh. What would you call cluster 3? Okay, nope, sure. What would you call a cluster 3? You're going to have to look across it without me helping you. What would you call a cluster 3? What do you notice about cluster 3? Just look at this. Oh, look at we did it. We achieved it. So what do you notice about cluster 3? I mean, they're not the worst there. They've been with us a bunch of zeros, yeah. They've been with us the shortest amount of time and a bunch of zeros. Those are like customers who we've lost them. Those are kind of the lost. They rarely travel. Exactly. Great answers right there. Non-customers, bunch of zeros. They don't fly with us. Oh, yeah, the middle person didn't fly with us last year. Now, these people don't fly with us last year also, but there may be customers we have not lost. These are potential lost. I would call these customers are danger customers. Cluster 3, I might call my lost customers, and cluster 4, I might call my potential lose. Like, we have to watch these customers because they didn't fly with us last year. They have flown with us a good bit. Like, the total miles is closer to these individuals. They didn't fly with us last year, though, so I'd be a little bit worried about these customers. Like, these are the customers we need to get, like, reinvigorated. So cluster 4 is the ones we need to get reinvigorated. Cluster 3 are the ones we've maybe lost. Cluster 2 are our champions. And cluster 1 is probably going to be our general customer. And we can look at how many people are in each of these groups too, because I think maybe that might be an outlier right there. But cluster 1 might be our general customers. So, and the names you come up with these are just you just make them up. You make up the names. You say, like, I think these people are this. So you see here's the names, the superstars, the duds, the high values, the credit card users, because of the, see, it's cluster 4, and they might have moved around. Oof, hopefully these aren't the wrong customer. The names or whatever you want it to be, and there's the amount of people in each cluster right here. So this is a table of how many we have in each group. And this is real data once again. This is actual data from American Airlines to see, like, how their customers have different groupings. And all of that stuff right there. I think we have time for a little bit more. Here's a visualization of it. Fun. It's hard to see things in a multi-dimensional space. We'll be able to finish this tomorrow, but I want to start this today. So we'll be able to finish this tomorrow. We'll be able to talk about assignment tomorrow, and we'll do a little bit of market basket analysis tomorrow. And I think we'll be able to finish up market basket analysis on Monday, which will be on the test on Tuesday. So we will definitely get to market basket tomorrow, but I want to talk a little bit about dendrograms right now. So we've got 8 minutes, and we can definitely talk about dendrograms. I'm going to do a speed run of dendrograms. So let me put the timer on the screen. Can I put the timer on the screen? I don't think I can, because I'd have to put it here. I can't put it behind me. But I'll go to a smaller screen if I do it, and my screen's not set up. Do you guys want the speed runner timer on the screen? Yes or no? Tell me, do you want the speed run timer on the screen? Yes or no? I could scrunch it. Should I put the speed run timer on the screen right here? Nah, okay, that's what I thought. It might be a distraction. Let's move the speedrun timer off. Okay. It's because we're not on the speedrun timer screen. Okay, speedrun timer's not on the screen. You guys voted. It's not happening. You ready? And I talk too fast when it's on the screen too. So when we talk about the k-means algorithm, is the k-mean algorithm agglomerative, bringing stuff together, or divisive, splitting stuff apart? So think about this. When you look at it, the k-means algorithm, is it going to be divisive? Like, as we go up here, is it divisive, or is it agglomerative, bringing stuff together? Is it dividing things into more groups, or is it splitting stuff apart? When you go this way, is it agglomerative? It's divisive. Yep, it's divisive. The k-means algorithm is divisive because it keeps dividing it up. So that's what divisive means. It means it's going to split it up into more groups. But agglomerative means to bring together. Agglomerate, I think it's also another word for it, but agglomerative. It literally took me like 2 semesters to say the word right. I'd literally be like agglomerative. Agglomerative. I can't speak. So agglomerative is to bring stuff together, and it's like bottom up. It's going to start down here and bring stuff together. And we'll repeat this tomorrow, but we have complete linkage, single linkage, average linkage, words linkage, and these are the methods we use to link things together. More on this in just a moment, but here's how it looks. So when we talk about complete linkage is the distance between, could it be both? If you go backwards, it'd be agglomerative, but usually we think about it going forward, so it's divisive. So yeah, kind of, Sarah, good point right there, 50 point Sarah right there. It's kind of like if you're going forward, it would be forward. It would be divisive. If you're going backwards, it would be agglomerative because it's bringing stuff together. So you could say, let's go more agglomerative on it. Let's start at a high point and bring things together. So then you're using it in an agglomerative fashion. Fun word, agglomerative. I'm very proud to say it. So when we talk about the way we look at the distances the clusters are apart with the hierarchical clustering, we can look at the shortest distance, which is single linkage, or we could look at the furthest distance two things are apart, which is the complete linkage. Do you see how there's blue dots and there's red dots? So how far away are these blue dots from the red dots? Well, maybe we take the farthest red dot and we look at the farthest blue dot. That is complete linkage. Maybe we take the closest two dots to each other. That's single linkage. Maybe we take the distances from the middle. That would be average linkage. And then Ward's distance uses a reduction in the within cluster sums of squares. So Ward's distance would try to keep the within cluster sums of squares the smallest. So it would literally start with everything in their own cluster. And then it would say, if I join these two together right here, like you have this and this joined at this center, then what is the within cluster sums of squares? A little harder to visualize, but it would go for the minimum within cluster sums of squares differences with Ward's distance right there. That goes for the increase the sum of the squares distances. So this graphic right here, try to understand, we're showing complete. To always work with Euclidean distances. There is the Manhattan distance. So you might know that. It used to be in the notes, and then they just decided to take it out. I miss it. But Manhattan distance is absolute distance. So it's kind of like RMSE versus MAE. So you can use Manhattan distance or the absolute distances. So you could calculate distances by that. And you can see how it works. Yep, taxi cab. Yep, you know Manhattan distances then. Yep, it's just taxi cab. That's why they call it the Manhattan distance, because it's absolute. So if you were to do the absolute distance right here, it'd be this and this, because you take the absolute distance, not the Euclidean. So you can do that. Yeah, no, great question. And that's, yeah, no, it used to be in the notes. And then they said we have to reduce the notes because it's so many notes. I mean, you look at, we're like going like this, and it used to be like 50 more pages of notes. So I just want, and I will come back to this. I will talk more about this more tomorrow. We still got 3 minutes. I just want to show you a dendrogram to end class, and I'll go through this more slowly tomorrow. But if you look right here, this is where people get super confused, is we have a distance matrix. 1 and 2 are the closest 2 points to each other. Since 1 and 2 are the closest 2 points, they will now merge together into their own cluster. And now we have to recalculate the distances things are away from 1 and 2. You can see the red dots right there. So 2 is actually the closest to all of these points right here. 2 is closest to 3, 2 is closest to 5, 2 is closest to 4. So are we using single or complete linkage? Don't cheat, don't look at the slide. We're using 2 to calculate distance for how far it is away from 3 and how far it is from 5, how far it is from 4, and how far away it is from 6. Is this single or complete? Because we're using 2 to find 2's distances from 3. And because 1, 2 is a group now. This is single linkage because 2 is the closest point to 3. So we're calculating, does that make sense? Like we're calculating the distance 2 is from 3. So when you look up here, 1, 2's like 1's distance, so we're doing 2 right here. 2's distance from 3 is this, and 1, 2 is now a cluster. You can put them together. If it were complete, if it was complete, the distance from 1 and 2 to 3 would be calculated from what's distance. So if it was complete distance, the distance 1, 2 is from 3 would be what? If the difference is complete difference, the difference of 1, it'd be 1 and 3. Yeah. And then it would be the 2 furthest points. And the 2 closest points now are 3 and 5. So in single linkage, here we'll do another one. Let me ask on the next page, 4 and 6 merge next. How would we calculate the single linkage between 1, 2 and 4, 6? So this is a really good question right here. How would we calculate the single linkage from 1, 2 and 4, 6? How would we calculate the single, 2, 4. And then how would complete linkage be calculated? The distance of what we would carry for the complete linkage. Complete linkage between, so, and then 1, 6 is the complete linkage. And then average linkage, you'd have to you'd have to go here, and you'd have to go, show me my box. You'd have to go there. That's average linkage. And then wards is hard to visualize because you'd have to see what the sums of squares would be if you put a new center. Can you repeat about single and complete? So single uses, and so here's your two clusters. Oh, we're almost done right here. Single uses the two closest points to calculate the distance. So we have two clusters right here, and the two closest points within the clusters, single linkage would be the distance of 2 and 4. So that tells us the distance they are apart. And then complete linkage uses the two furthest points in the cluster to calculate the distance they are apart, which is 1 and 6. Does that make sense right there, Anisha? That single linkage uses the two closest points within the clusters, which are 2 and 4. And we use that distance down there in our distance matrix to say how far are these 2 points apart, or these two clusters, excuse me. And then if we want to calculate the distance of the clusters with complete linkage, it'd be 1 and 6 because those are the two furthest points in the cluster. So complete is like the total distance they are away, and we do it by Euclidean distance. And you could do it by Manhattan, though, if you really want it. There's nothing wrong with that. You can see if it works better. And so we have that right there. Now, the whole point of this, and we get to see it last second of class, is to make a dendrogram. And what does the dendrogram show us? It shows us the heights at which they merged at. So if you notice right here, you can see that 1 and 2 were the first two things to merge together, then 3 and 5, then 4 and 6, then cluster 3, 5 merged with 4, 6, and then everything merged into one data frame at a height of 2. And so this would actually be the final distance right here, which it looks like 2 and 5 are away. Now I know just because of the scaling, but 2 and 5 right here are the two closest points. Sorry, the axis has been squished right there for slide. But this distance right here, I know it looks like 2 and 3. It confuses me too, but it's due to the way the axis is squished. And so, yeah, no, we can get it. Yeah, it right here. We don't do it by hand, and so class is over right now. So I'll try not to, I'm not going to go through any more notes, but no ask away. I'm not leaving right now. But you can do it just with this right here. You can do hierarchical clustering of your data based on this right here. And we should have the data. I do have the slides uploaded with it. So there's the data to plot. Let me see. The data should be on here. So should have the data. So here's the data right here. And then are we not storing as a data frame? There's the x coordinates. Really? And let's hop over here. Let me hop over to the main screen. Let's see if we can get this graphic going. It's in the notes. Like if you actually, I've got the R. Why am I gone? Why was I gone? What happened? So here's your x coordinates. And great job, everyone, today. Excellent work. A lot of material. Pretty big thing right here. And then we have it coded as the, data. Here it is, data frame. Haha, of course. Why didn't I just write that? And so there's the data frame. And so all we're doing is just putting the two vectors into a data frame. You guys have seen me do that code before. And then if we go over here, we can take the hierarchical clustering right here. And this is, I'll show you something really interesting. So this should work unless there it goes. Yeah, that's it. So there's the dendrogram. But here's the thing, watch this, Nitin, is if I just change this right here to complete, it changes the dendrogram drastically. And so this is the key right here. If you're still watching, this is going to be helpful. Can you guys, in my screen, it doesn't look like the lines here. Can you guys see that line on yours? Hopefully you can. But this right here is the dendrogram. And this distance right here looks to be the distance from, you can see it good. You see 4 and 6. You got 1 and 2 merging together, 3 and 5 merging together, 4 and 6 merging together. And let me make the visualization of it from the previous page. And once again, all the colors are in here, so all the slides and all this good stuff, so you can easily make the graphics. Sure. Make this one. Okay. So when you look at this right here, and are these the original points? I don't know if those are the original points. Let's not use those. Let's use this right here. And then the line is added right there. There's the lines. I don't want the lines. So let me just, no, go away. Sure. Grab all this right here. We'll go down, go back to R, and placed, and run. And, oh, why's our points on there? Plot. Lines. Really? Gotta do that? What? Where's the points? Plot. Plot x1, x2, limits. Data. I already have it. What happened to my plot? What happened? What? X2 and x1. Are they not stored in here? Am I going mad? There's the limits. Oh, cull white. Oh, no. Hey, there we go. What? How is that? Why is that working on this? Oh, because it's got the numbers. Did we add in those numbers? Did Dr. Petrie add in those numbers? That's interesting. Round as matrix digits. Oh, wait, and then I think he added in right here. D is for the digits. And so I think that's what he added in right there. Oh, no, that's the matrix. Cool. And that's the distances. Yeah, okay, so there's the distances. But here's the points. And when you look at this, and let me make them bigger, that's going to be the CEX. No, it's P. Why is my brain blank? It's CEX, right? 5. Oh my gosh, what is going on? Oh, it's still white. It needs to be black. So, go here. There we go. That's what I want. Cool. Okay. So, when you look at this right here, these points are going to merge with these points. These points are going to merge with these points. These points are going to merge with these points. And then it gets confusing. So, when you look at the dendrogram, which I don't know if it'll let me have the dendrogram open too. Can I open the dendrogram and this? I could put them both on here. What I'm going to do is I'm going to take some screenshots right here. Let's take some... really? Okay, so we'll put this here. Let's take a screenshot of this. And then I think it changes the graphic when I change it. So we're going to take a screenshot of this. Then we're going to go back to our dendrogram. And there's the dendrogram. Did it change the screenshot? I think if I have it open. Yeah, it does. I knew it did that because I've done that before and it changes the screenshot. So there's this. Don't like that little bit of editing on the side. Crop. And so, wrong button. Show me crop. And right there. There we go. Cool. Okay. And so that's that graphic. Crazy huge points right there. And here's our dendrogram. So with the dendrogram, what we want to notice is the way that these join together, which we'll cover this a lot more tomorrow. So now we go right here and we look at the dendrogram on it. And we look at our points. And so just so we can see, we can get these inside of R right here real quick. It's nice that everything's in here. We can just reproduce the output. So here's the dendrogram. Here's the, and let me zoom in a little bit. Here's the points, and here's the dendrogram. And so I think it goes 1, 2, 3, 4, 5, 6. So let's go here and draw in the points. And let's go here as 1, 2, 3, 4, 5, 6. So with the dendrogram, yep, we're in office hours. Yep, feel free to ask anything. You're free to. The first points that join together are these right here, where 1 and 2 join together. And 1 and 2 are joined together like this right here. Yes, let's do that. Let's do that. I'll do that next here. And that joins together there. And then 4 and 6. Oh, I did a wrong labeling of points. No. 4 and 6. 3, 5, 4, 6. Okay. 3, 5, 4, 6. 3, 5, 4, 6. Okay. And so this is 3, 5, and that's 4, 6. I'll make sure that's the 6 up there in the corner before I have another error. I got 6 up there in the corner. Okay, so this right here, when we see 1 and 2 join, it joins like that. And then 3 and 5 and 4 and 6 basically join. And what is this height over here? If you look at this height, the height you're seeing right here of like 1.9 or so on these, like if you trace across, that height is the distance these are apart. So that height they're joining at. So when you see a height of 3.2 or so right here, that height of 3.2 is telling us where 1 and 2 and 3 and 5 join together. And this is complete linkage. So this is complete. And I'm going to do it. I'm almost done with this one. And so that means that 1, 2, 3, 5 join together on complete linkage. So, okay, this last question, 100 bonus office hour points. Since this is complete linkage, what is this distance of 3.2 right here? This distance of 3.2 is the distance of what and what. Since this is complete linkage between these clusters right here, which are these two clusters right here, since this is complete linkage, what is the distance right there? It's complete linkage though, and it's between those two. To to make it very clear, I'm talking about just this right here, that value. Be careful. No one's gotten it yet. 100 points. No one's gotten it yet. We're almost done with this example, and I'm going to start doing all the 474 questions. What is it? Yes. Yes, Jordan. Great job. It's 1 and 5. Because this distance right here is the furthest points between the two clusters. Does that make sense? Since, and hopefully you might not be able to see, that's a 6 down here. 5. Oh my gosh. See, I misspoke. It's the distance between 1 and 5 because it's complete linkage. And so it's this distance right here. And then the distance we see, this is the last question on this. The last thing I want you to know is this distance right here. What is this distance right here? This distance right here of 6. Sorry. Preference. No, that's a great question, Nitin. Just depending on how it looks. Once again, it's an art, not a science. You look at it and say, like, does this work? And you say, like, okay, which of these clustering schemes looks better? We'll go by like how good the separation is. Like this looks to be 2. So you would say this has a good, because there's a clear delineation right here. You could technically go for 3. So when you cut across, that's when we do a cut on it. So we'd cut across and say, okay, like 2, maybe 3 look like a good clustering scheme here. So, and this would be the distance from 1 to 6, yeah. This is going to be the 2 furthest points right here. So when you merge here, everything merges on the maximum distance. But if I do single linkage, it's going to drastically change how things merge. So single linkage, and I think, yes, let me start doing the 474s and the 320 questions. But hopefully this makes some more sense. We're going to go through this again tomorrow. It's the last part of clustering. Then we're going to get into market basket analysis. But this is the last part of clustering right here with dendrograms and single complete, wards, and average linkage. We won't visualize average and wards, but single and complete we should have an understanding of how the points are connecting. So this was complete linkage right here, and here's the dendrogram showing it, and here's the following through. So I'll try to do more like this tomorrow. First question on 474 was, could you help me with complete the skeleton and the for loop for number 4, question 4? Was that the first one? I think it was. Yep, I think, and if I missed someone's, please tell me. I think Jordan had the first one right here. Jordan, let's do it. Let's do it. I really want to drink that second Red Bull. I'm like, no, I'm not allowed to drink the second Red Bull. I think your guys is called homework. Homework 4, functions. Let's do this. And then I've got the other homework out. I think right now, I think your guys' homework is due tonight. And we've got another homework out. Did we release homework 5? We should have. I think I did release homework 5, right? You're welcome, Nin. Great job. Everyone, great job. And then, so Alex, keep hanging out. We'll do it here in a second, Alex. We will get that question done. And sorry, my brain blanked. Could you help me with the skeleton for loop in number 4, homework 4? Okay, we're here. Let's go to number 4. Here we are with number 4. Let's do it. Okay. So this one here wants us to do what? Write a function called leaps that takes 2 arguments. Okay. So first thing I'm going to do, I might just do a little bit of work right here. And I know that my function, and we usually don't write our function first. That's a key. Don't write your function when writing your function. We're going to write a function called leaps, and it's going to take 2 arguments. It's going to take a vector x, and it's going to take lag, which defaults to 1. Now, we'll use this later on, and you might want to delete these things. Watch out. I'll do some work that, like this, if you leave this in here, actually wouldn't break it. I don't think this would be horrible. It's kind of clutter, but that wouldn't break it. You could go on this, and you could say, there you go. If you do this right here, this is probably the best way. If you do this as a practice thing. So, Jordan, you could leave this in here if you want, just as a thing for yourself. This will not evaluate and runs, and it will not include in your output. So if you notice here, I went to chunk options, and I put show nothing, don't run code. So you can do that and write things right here to like help yourself out. And then when you knit it, it won't show up. So have your function return the vector of x, leaps defined as the absolute value. So actually, you know what we need to do? Return the vector of x, leap defined as the absolute value of the difference between the elements of x separated by the lag. Okay. So for example, imagine x is the vector yada, 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 yada. The lag is 1. The function will return with vectors of elements 0.2, absolute value of this and this. So it's going to go here and say this is 0.2, and then the next one is 0.2, 0.1, 0.3, 0.4, right? Okay. Oh, is there an error? Oh, that's 0.4. I can't do math. I don't know how to do differences. So it's 0.2, 0.2, 0.1, 0.4, 0.4. If this was leaps 2, if this was leaps of 2, then what would the difference be here? If this was leaps of 2, what should the vector return? If it was lag 2, which it doesn't do in this example, if this was lag 2, what would the leaps function return right here? If this was lag 2, what would the leaps function do right here? Yeah, the first one would be 0.4. The next one would be what? It'd be 0.4. Then the next one would be what? Next one would be what? Would be the next one. What did I say? 2? 1, 2. Oh, no, I'm making mistakes here. Oh my gosh, I said 2 right. This would be 0.4, and then this would be 0.3, and this would be 0.3, and this would be 0.8. So sorry, I think Jordan, you were right. 50 points, Jordan. Office hours points, bonus points on top today. Brian doesn't know how to math today. It gives examples and it walks you through. Have your function be able to output the following warnings. Okay, those are warnings we need to add. So cool. So these warnings we'll add in afterwards, but we need to know like what we're doing with this vector. Now what I'm going to do is I'm going to make this work. Sure, we'll leave that there. Oh, and it gives us the test vector. Well, that's so nice of you. So we already got our test vector. So I'm going to take the test vector and put it up here because I want to actually use it. So what I want to do is I want to code this on the test vector. So when you think about this, you can think about how the for loop works. The for loop is going to go to test position what to start. What position will we go to in test position what? Like every time we do leaps, you have to go to test position what to start. Yep, position 1. And let's say we're doing leaps of, great job everyone, 50 points if you're responding. So let's say we're doing leaps of 1. If we're doing leaps of 1, then, yep, Ryan, we'll do that. You got it. I think we'll do 1 474, then we'll do a 320, and we'll bob back and forth so that way the 320 can see it right here. If we're doing leaps of 1, where will we go in test vector next? We'll do test 3, position 1. If we do leaps of 1, it'll be test 3, 1. Where will we go? If it's leaps of 1, where will we go? Because we're like taking distances. +1 basically. And actually that's a better way to code it. I'll show here in a second. Because this is the first distance and we also need to take the absolute value of it. So once again, if you highlight code, you can, like if you have something and you highlight it, you can just put parentheses around it. That's a trick I do a lot of times. And we're just going one position over. So actually what Jordan is saying is really good advice, because if I want leaps of 2, this would be the answer. But we should go to 1 plus 2. Does this makes more sense to code it this way right here, because this is what's going to change. Does this make sense? Like this is the value of leaps. Like my value of leaps is here now. Does this make sense? Like putting +1 separates it out to original position plus the leaps. Original position plus the leaps. Whatever my value of leaps is can be changed here by doing this. So you might say, well, isn't 1 plus 1 2? Why don't we just code 2? It's because now we have it separated out into this. Did you mean to put 4, 6 in the vector for test 3? Oh, did I do that? If I did, I didn't mean to. This is the vector right here. Oh, it is. Right? Or are you talking about this right here, Madeline? This is saying there are 6 elements. So that's giving me how many elements there are. So if we were to like make a vector of numbers 1 through 1,000, it'll tell me that there are 1,000 positions. So if you notice they're in square brackets, great question, Madeline, 50 points right there. That's telling me the positions, because it says num square bracket, there's positions 1 through 6. And then we can see over there the values in test 3. But these are num square bracket positions. You know what? I didn't even notice that, Madeline. That's worth 100 points, because it's telling us with the square brackets, those are the positions, but not the elements. And then it shows some of the elements in those positions. But great questions. Yes, love it. And question 4, where you at? And so right here, we see, unless I did something else, we see here test position 1 minus test position 3, or test 3, position 1 plus 1. And so with this right here, we now want to algorithmically go through this. So now we want to continue this process, because check it out. You ready? Okay, what have I written? Jordan. What does it look like Brian's written? What have I written? I need someone to tell me what I've written here as I keep writing it repeatedly. What have I written? Because this shows it right here. This shows that we've done it by doing this. Something that needs to be looped. Yep. We've written a skeleton. We've written our skeleton because it just repeats. And you can see right here what's repeating. And remember, clean up your code. This is the for loop. You got it right there. We're going to take one of these. We're going to go down here to our for loop and put it inside of there. So we wrote the for loop. We're going to put this as I, and this will be I. I is our variable name. That's just the name of the variable. That will change. And then I will go from what to what. 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 What will I go from? And we're going to make it a little bit smarter here in a moment, because you'll probably say what I think you're thinking of. Is it close? Close. So you have to go from 1 to the length of x. So you have to go from 1 to the, or it's test. You have to go from 1 to the length of the test thing. Yeah, because if you just do length of it, it'll only run it with 6. And I did that. I've done that all the time. It's like, don't worry. Like when I say I do this all the time, I mean it. Like I used to always code length, and it's like, oh, it only inputs one value then. So you have to go from 1 to the length of it, and that'll create a vector of numbers right here. So you have to do that. You have to do the 1 through the length of it. And now when you run this, we do need to store this in a spot. We need to store it in leaps. And if we're storing it inside of leaps, we're going to store it into position I, and we need here leaps. And leaps could, I think it says stored as X or something, but that should do it. That should return it. There we go. And it gets an NA at the end. Let me double think this. Okay, because we should have stopped it. Yeah, that's why. And that's the thing I was kind of mentioning, is that we were going to make it a little bit smarter, because we don't want it to get to 6, because it can't run on 6, because it will go to 6 plus 1 position. When do we want this to stop? When do we want this to stop? When do we want it to stop? When do we want this to stop? How many positions before the end? How many positions before the end? When do we want it to stop? Very close. Very close. Very, 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 very close. Like just do a little, very close. We want it to stop because look, I went one too long. So just think of like this. Yep. You got it, Jordan. Great job right there. That, we want to stop there. And we'll rerun this now and we'll see if it does it. And it does it. But look at this. This is my leaps, right? So do you notice how this is going to be controlled by this? So let's go in here and let's say lag equals, oh, I don't like that equals 1. And this should be lag now. Oh, what it was, yeah, let me explain that. Here, I'll show you, and that works now. The reason we got the NA right here is because the last time the for loop ran, it went to test. So remember, we did 1 through length of this right here, right? So this was 1 through 6. You can see it right here. This was 1 through 6. So the last time the for loop runs, it goes to test position 6, which does exist. It was test position 6 is this. And then it goes to test position what? Like, why do we get an NA? It goes to test position 6 and tries to subtract from it what? So here's position 6. So it goes to position 6 and tries to subtract from it what? And that's why the NA occurs. So it goes to test position 6 and tries. And so does that make sense where we're getting the NA? Because it does it and says, like, can't do this. There's no answer. We can't run this mathematics. It's missing. Like, there's no answer to it. Yep. No, Jordan, great questions. That's what you're like, well, why does that NA occur? It's because it went outside the vector. It tried to do mathematics. And then we say, okay, don't, and that's why we added in the lag right here. We don't want it to go from 1, and be very careful. I've seen this before. This is why I'm very careful where I put my parentheses. If you do this right here, this is not the right answer. This will give 0, 1, 2, 3, 4, 5. So this makes the vector and then subtracts off the lag. Like the order here is make your vector, then subtract the lag, where the order here is go from 1 to length of the vector minus the lag. So this is evaluated inside of the parentheses right here. I think I got that. No, that's one too many. This is evaluated right here inside of this parentheses, and it's 5. So it doesn't make the vector and then subtract 1 from the vector. It subtracts 1 from the length and then makes the vector, because this is evaluated first, and then we go 1 to 5. You just have to be careful, because if you do it this way, you will make your vector first and then subtract 1 from the vector. I try to do it. I'll be trying to do it more, Ryan. I think so. Yeah, and I think this does it for this question. I might stop on this question here, because at this point it's turning it into a function. Are you feeling a lot better about this one, Jordan? Like, I got through the main bulk of it. Turning into a function is one of the big things we need to know how to do. And so I think this gets people pretty far in this problem. Like, the warning messages and stuff aren't bad at all. You just do like checks, like if class is not numeric. So you would just take and do like is dot numeric of test3. So, and that returns true. And then if test3, and we want to do is not numeric, so then you do warning. You go warning and message. So this will not print out right here, but if this was something like this, it will say no. So if it's not numeric, does that make sense? And so this is how you can see if something is not numeric. Like, this will return true now because that's not numeric. So I'm asking if it's not numeric. But if something is numeric, like the actual test3 vector, which is numeric, we don't get the custom warning message. You could put else, like, and then you put your, like, congrats. And if it's a stop message, you could put, yeah, we'll put warning here. Else warning, yay. And now it should say yay. And then you could say stop, but it's probably going to say, yeah, if I think it's mad because it's, oh, stoop. And something's weird's going on there. Yeah, the stop is used. I think it's mad about that because I don't think you can use a stop outside of, oh, but then yeah. Let me try. I want to see something. Yeah, now okay, that does work. You can use them outside of functions. I don't use them outside of functions, but you can. And that's just showing how these work right here. So it's giving the error, which would stop the function. And this is a warning, which will just warn you. And so Ryan, let's jump to Ryan's question right here. And then we're going to do another 474. Ryan's 320, or Alex had one. Alex, are you still here? As long as you're still here. And then Ryan, did you have one also? So here we're going to do Alex's question right here. 3A, after plotting with using points, core demo, how do we input into the plots print? Oh, the 4 plots in print? Okay, great question. Alex, are you wondering about using core demo and how you get those into your assignment, right? So the core demo, when you use core demo, great job working on the assignment right here. When you use core demo, you want to go ahead and you make one of your plots and you make it nice and neat. We can make fonts a little bit smaller here. So just make it as nice and neat as you want. And then you make like, okay, this is a correlation close to 0, which is one of the ones you have to do, which we kind of did in class 2 too, a correlation close to 0. You put then a point over here, you got a strong correlation. You go here to snipping tool or Command-Shift-4, and then you can also export images, but I like to just take a screenshot like this. Take a screenshot with snipping tool or Command-Shift-4 and jump over here, drop it in, resize it up, and there's your picture inside your thing. Be careful with using things like that. That's going to distort it. So you don't really want to, you always want to grab the side. Probably a lot of people know that. But if you grab this, it'll keep the aspect ratio, which is very important to a clear image. So and we can always zoom in. Like if you keep the aspect ratio, you can always like zoom in. Don't make it too small. Don't make it too large. You know, it's like, what's a good image? But these can be inserted afterwards. Make sure to include them. You can also code them to be in your project. But I would just, if I was in the class, I'd probably just insert them afterwards. I would knit my document and just insert them afterwards. But there's a ton of ways to put them in as images within your project, which we should. The assignment 0 shows how to do that. So do we still have assignment 0 on here? Assignment 0. I so rarely use it. I think I always forget it. It's like you call exclamation. You have to go outside. It's just easier to insert it via Word sometimes. And you call like this, and you give like name of the image, and then you call the location with the parentheses. You see there it does it, and then you put the location of the image right here. So you see this is turning a special code. Paste over it, yeah. You can do like, if you want to paste over it after you do it, click on the image itself, and then go to wrap text and go to in front of, and this way right here, when you move it, if there is some stuff, random phone calls, so many random phone calls. If there is some text right here, when you do this, you'll go over it, or maybe you want it to be behind it. So just depending how you want. So now the text would see through it. So this right here would watch right here. Let me see. Ooh, let me take a look. Alex, you're the best at this paste bin. Oh yeah, you want to put it like in those, right? I wonder if we could do that. You know what you could do? See, I'm trying to think of, so let me explain what this does. The parameter par mflow, here I'll show it to the chat. And so here we'll drop these in. So we'll make this inside R, we'll stop this. I wonder if I can figure out a way. You guys, you gotta go to finish. Okay. So let's see if Brian can think of a way. When there's a will, there's a way. Okay. So let's plot this right here. Okay. So what this does right here, the par mflow, and I think this right here is just turning it back to a 1x1 grid. So it's resetting the parameters of the window right here. And so this is creating the margins on it. So we create these margins right here. This is creating this plot right here. That's creating that plot. So that's 1 through 10, no points. And the X and the Y, the X label, the Y label. So you could add in like a Y label and you could just say random. This would be a lot of work to plot these out individually. And oh, it's not showing up? Can we not see my random thing? Really? Where's the Y lab at? Legend, top left, A, legend, oh, that's the legend. Okay, cool. Color white, go blue, and run this again right here. Ah, ha, 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 ha. Yes, that makes sense. So what Dr. Petrie was is he made a plot with 10 points in it, then he colored the points white so you can't see them. Tricky move right there. So he put the 10 points in with here's the X coordinates and the Y coordinates. So you could theoretically come up with points that follow like, so this will take a moment to think about, is I want to go like, let me think right here. Someone's going to totally steal this. This might be, it'd be a lot of work to do this without the, is I want to put in like, let me think, 1, 2, 1, 2, 10. Okay, 1, 2, 1, 2, 10. 1, 2, 1, 2, 10. And then that's the Y coordinate, right? Oh, is it? Let me think. Y tilde X, X comma Y. Okay, reverses it when you do this. Okay. And then this one will be 2, let me think here, the Y coordinate. So what did I just do? 1, 2, 1, 2, 10. So this is 1, 1, 2, 2, 10. 1, 1, 2, 2, 10. And let me plot this now. That's what I wanted. Cool. So maybe this is helping out. Let me look at the chat again. So you can also make the points bigger. If you want to make the points bigger, you can go to CEX, and that'll make the points bigger. Oh, that made the box bigger. I don't want the box bigger right there. Oh, I'm inside the legend. Okay, that's an extended. Wait, I just did that. That's depending on their legend. So, whoops, made the legend bigger. So CEX equals 2. CEX controls the character expansion. There we go. And I want to also go PCH on this. PCH is point style. 16. Let's see what 16 does. Yeah, there we go. No, it's really, no, Alex, I love this kind of stuff. If you can't tell, I get so excited with like, you know, you could actually put all your points inside of here and do the plots. But if you notice, I was kind of like 1, 2, 1, 2 and trying to figure it out and how to plot it. But it obviously, you know, is easier. I find this kind of stuff fun. Maybe I'm crazy, but it's easier if you go here And if you kind of create the plot, like kind of get it the right dimensions, if you increase font size, it doesn't have to look perfect, but you can try to make it look as nice as you want and get it looking pretty good, and then insert the images. I won't be mad if it doesn't look perfect. I mean, don't worry, I'm not gonna be like, oh, and so the whole thing I do right here, let me finish this off, looks a lot similar to this. So if you see, I'm able to, how quickly I was able to create this image and create that image up there. And I don't think that's the answer to A, but these images, and I'll make myself go away. These two images right here, this and this, like I was able to create this relationship right here, which is an outlier making a weak relationship look strong. And over here, I'm able to create this. So you can figure out the points and create it and then draw them inside of here. Or when you have this right here, if you have this output, here's what I would do, is I would knit it. And don't worry, Alex, this is a great question because it gets asked every semester, like, how do I get the images in? Everyone, it's all right, because it'd be more fun to do it with code. And that's why I like doing it with code. But once you get your images from R, I would go over here and I would take this image right here. And if I was doing this for a class, I'd probably do it this way. It's the quickest way to do it. And then I'd go back to my Word document and I'd paste in the image. Let's see here. Jordan's got a question. So there we go there. I'm going to go wrap text in front of, and then I'm going to go here and do the following. So I might just do that. It might be covering up that A. I'm okay with that. Or you go a little smaller right here. There we go. So you could go like that. That's perfectly fine. Put it down here in the corner. And we'll go like that. That's about the best we're going to get if we put the image inside of there. Yeah. I'm getting the X should be numeric vector. Warning message every sanity check. Is that supposed to happen still on question 4? Yeah. Oh, we're just having some fun right here. And I'd understand if you could cover up that A and make it bigger. There you go. So that's perfectly fine right there. Any of these is fine. So if you do it this way, or if you go all out, I mean, I love seeing the innovation that people come up with and the ideas. So again, the X should be a numeric vector. Yeah, let's see what's going on with that. The X should be a numeric vector? Why should it be numeric? Why does it need to be numeric? I don't know. Go ahead and drop it in the chat, Jordan, and we'll take a look at this. I don't know if X should be numeric. I'm fine with it not being numeric. X should be a numeric vector. Oh, I'm still vanished. What am I doing? If numeric or is integer warning. Okay, cool. Okay. So let's go and take a look at number 4. Number 4. Here we go. So we're going to drop this code right here. And if is not numeric or is not integer should be a numeric value. Okay. So if it's not numeric or is not integer, and we're going to go here and grab test3, and we're going to put test3 here as this, and delete this custom warning message for now. Okay. And so, okay. I see it. Because we don't want the and right here, Jordan. So because test3 right now has a class that is one of the two, and let me look what the thing says. So it's numeric. And let me look at what it says. If, here it is. Do you see it, Jordan? Do you see it? It's right there. Yeah. No, good job, Jordan. Like these are tough ones. So what is the issue? Do you see the issue in the code? It's right there. And I think you have it right there. Yep. Once you see it, it's like, oh, it's like, you're like, oh, yep. Boop, boop, boop. There we go. Now it does nothing because it's one of those two things. So we're seeing if its class is one of those two things. And there's another way to do it. Let me do it the other way real quick and ask more questions if you have them. If class of that is not contained in the vector numeric, comma, integer. So you spell integer? That's how you spell integer. I don't know how to spell integer. If it's contained within this. Okay, so we should get the warning message now. Yep. And since we got the warning message, we're going to go here and put not around it. So if it's not contained in those, now we don't get the warning message. So that's another way of coding it right here, Jordan, just so you can see and keep up the good work. Like I want to show as many things as I can. It's a little small in the text right there. Now maybe it's a little too big. But just so you can see this way of coding it right here, where I'm doing if the class of test 3 is not contained in this. That's just a totally different way. Yeah, and that fixes up. Awesome. Great work. Great work. This is if the class of the object is not contained in this vector. So we're just seeing, is it not one of these? Which kind of, there's just different ways to code it. And the question, literally the spirit of the question is choose an and though. So it says if it is not this and it is not this. So the way it's written, like if you code it by the way it's written, it would be that. But you could also say, is it not contained in one of these? Is it not one of these values? So if lag is not an integer, so there we go, i.e. lag is this. And so, yeah, so this is pretty obvious right here. I think you may assume it will always be a number. The message should say, yeah. So you don't have to check to see if it's a number. You just have to check to see if it's divisible by 1. But someone could put in like A and then it would break your code, which is all right. They're just breaking it in a way that we didn't put a message in for. If lag is too big, i.e. the lag equals the number of elements in X, or is greater than, it should say, equals number of X, or larger, there it is. The message should say value of lag should be fewer. And if this is the case, the function should immediately return NA and not return any additional code. So this isn't gonna, so message should say this. And so you can get this done in 2 steps. I'd probably do it in 2 steps. I'd probably put like if, and then da. And then we're gonna put here, you need to put a warning if you don't want the code to stop, and then you put in your warning, and then you're gonna put in the same thing right here, and if, and then you're gonna put inside of this, you're gonna put return. I always have problems with my ifs not doing 2 things, and then you'll return NA right there. So does that make sense right there, Jordan? We'll see if more people have questions. Who has questions? Questions. Ryan, if you're still here, we got tons of times for questions. 320 question 1. Oh, Ryan, here we go. 320 question 1. Let me load up 320 question 1. Just saw that, Ryan. Sorry about that. Let's see here. Scroll back up. Saw it in the chat. Tomorrow is the halfway point for the summer course. Tomorrow, we are halfway done. Can you believe it? Tomorrow, after tomorrow, you can be like, this class is half over. I mean, we have the mini term coming up. Yep. And we have the mini term coming up, all that good stuff. I didn't click the thing. We have the mini term coming up. We have so much good stuff. Voicemail. Oh my gosh, you get so many fake phone calls. They're not real phone calls. Let's see, how's chat doing? I know it's totally wild. I put the warning and return under the same. Yeah, will it run? I think it'll run. It's just like we code things a certain way and we get in practices. So I'll start coding things certain ways and then I'll just like, it'll work if you do it another way. But, you know, I code things a certain way. You get used to coding something a certain way. You code it, it works. And then you don't realize you can do it other ways. So it's always, and Jordan, I really want to say this, like, Jordan and Alex and everyone, you all push my mind. You guys and gals, you make me think harder about these things. Like one of my students, she's going on to get her PhD, and I keep telling my students, like, you're gonna come back and teach me things. And they're like, oh no, and I'm like, no, you're already like PhD in computer science. Like, congratulations, like that is an amazing accomplishment. And I say to them, you know, the things you learn, like Nitin, you know, has amazing knowledge. I mean, we all have knowledge in different areas, but I mean, working on a PhD right there, very, 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 very great job on, you know, being in a program that, you know, a lot of us, you know, often aspire, like, be like, oh, I want to get to the top of education. I still aspire to that. So I'm very, very honored that I can help these people because they, yeah. And so you might think like, oh, Brian's my teacher, I can't show him things. No. Like literally last semester I learned how to block comment stuff. So it was last semester I learned the block comment, which is, I like it. I use it now and I've got it memorized. It just became part of my repertoire. So block comment is Command Shift C or Control Shift C on a PC. So you just do Control Shift C and it block comments it out. So instead of like, I'd be like going and commenting. Someone's like, you can block comment. And I was like, what? And so you can just go to something. And what happens if I do it here? Will it block comment here? Whoa, I've never done that. What does that mean? I don't even know what that means. That's some sort of, that's what I call like RMD coding. So I don't even know what that does. I don't know what that does. Yeah, and yeah, all these little things. It was a student who told me that. Student told me that. They said, hey, do this and it does this. And I tried it and then I gave them extra credit. So you will teach me things and I will continue to learn. And so keep showing me things. That's why I love Alex was showing stuff yesterday and being like, hey, check this out. I made this for loop. I thought that was so cool. So I want everyone to know that I'm totally like, I'm still learning. I mean, I know a lot and that's why I teach the class, but yep. Exercise 5 on page 72. Exercise 5. If I knew everything, then what fun would that be? Knowing everything would be so boring. You'd be like, I know everything. It's like, okay. I doubt you do. Do you really know everything? Or are you just saying that? Who knows everything? It's impossible. Exercise 5 on page 72. And so I think question A is not on here. Yep, because question A was a bonus on the last one. Okay, so this is going out to Ryan right there. We're going question 5, our first one right here. So the variable most correlated response rate is homeowner HH, the fraction of the households that own their home. Calculate the R-squared and interpret the value. Boom, we can do this. We can crush this. Okay, so the previous question's kind of needed for this. Oh, why don't we get a code for this? Insert code chunk. So we're going to go here and load up library reg class. And we're going to go to all correlations. And we're going to need the ex2 census. And then we're going to put that inside of here. Runs. And then we're going to take response rate from down here. Where's my response rate at? Where are you at, response rate? Really? Where is response rate? Am I in the wrong data set? Or is it census? Maybe it's census. And yeah, it looks to be. Okay, that's why. Wrong data set. Probably said in the question. Is this the right data set? Oh my gosh, am I going mad? Let me look at the question. EX2 census. So it is EX2 census. EX2 census right here. Copy this. Copy. Run this. And we should see response rate in here. Unless I'm going mad. I probably am. And you know it's easier to do? It's easier to just like... Let's do it the easy way. Here's the easy way. EX2 census. $, response rate. There it is. Cool. Copy that. Good. Got it. The reason I do that, you might say, why did I do that? I want to spell it correctly. Could have also looked over there. There's the first variable in the data set. Now, what argument am I going to put if I want to look at response rate only? What argument am I going to put if I only want to look at response rate? I only want to look at response rate. What am I going to put? What am I going to put to only look at response rate? Who knows the argument we will add to this to only look at response rate? Let's do some hints. Let's write all correlations and let's look at it. That's going to give some hints right there. What are we going to put to only look at response rate? And we need to put it in quotes after we do this. We need to write another argument and put the name of the variable in quotes. And so we got hints on the screen right now. That's telling us how to use it. So what do we do? What do we possibly do? Uh-oh. I might be stuck. 100 points, first person, office hours, bonus points. Does anybody know what argument we will use? Not sorted. Good guess. Still worth 100 points. I'll take it right there. So sorted will, once we make the list, sort it based on these values. Still worth 100 points. You can still get another 100 if you say the right answer. Because I like when people are listening and following along. So, and this is a good review. And if we want, watch this. We can go to this. And, yep, you got it. Yep, it's interest. And I'll disappear for a second. Interest right here, if you can see what it says, it returns only the pairwise correlations of the variable we're interested in. So it's only going to do that. Sorted is going to control how we sort the list of the numbers. Interest is only going to choose that specific variable. So when we do interest, it's only going to return that one we're interested in. So if I go here to interest equals and put it in quotes, it'll only give me a response rate. So the only variable I now see that it's going to return on everything's relationship with response rate. So just by putting in a new argument, interest equals this, it does that. The variable most correlated, so then we need to do a sorted, not assorted, but sorted. And we're going to go here and go sorted equals, and we're going to go to magnitude. Magnitude. I always have to say it because I don't know how to spell magnitude. So there it is. I put like an extra ID, like magnitude. I don't know how to spell it. And now it sorts it on the magnitude. And right here, with the sorted version of this, we see here that this is the strongest. And you would think you'd do strength because everyone's always like, well, why don't we do strength? Because strength sorts by the lowest correlation to the highest. And lowest is terms of like the strongest, most negative. So it goes by most negative. So strength, just to show again, strength shows you the most negative to the most positive, but magnitude sorts it by order of magnitude. And you have to be careful because if you do misspell it, it won't tell you and it'll just run it. So this ran, but it didn't tell me there was an error. And you know, it's Jordan and Vedrina, are you still here? Because I'll show you something. So this is pretty much answering their question right here, like, and now to calculate the R squared, I'll show you guys something real quick. I'll show y'all something real quick. You're here, check this out. Okay, so you notice how with sorted, the function runs no matter what I enter into sorted. So do you notice that that's a problem? Alex, random question. I wanted to generate a sequence. If I use print sequence, how can I separate each number with a comma? I'll list you Alex's question, then I'll explain this. And so R squared is you square the correlation and then interpret it. Ryan, if you're still here, I'll come back to it. But we got this started. So this right here, this is the start of this question. Make sure you do this right here. This is the start of this question. Let's answer Ryan's question, or Alex's, then I'm going to show something real quick. So that's that. And you want to separate each by a comma, right? So you want to because you want to print this out to something and have it separating each by a comma. What you probably want to do is you might want to do this. And let's see if this works. Does this work? That didn't do what we wanted. Sep equals, is it string concatenate? I don't have string concatenate on, right? I don't have string R. String R is how you work with strings. Strings are just like the words. So we need to use string R here probably. And it's going to be like string concatenate. There's string concatenate. There it is. Here we go. And let's take this right here and put it inside of here. Why is it not doing the comma? What? Join strings, or no, it's string glue, right? It doesn't like that. There's that. Turn a numeric vector into multiple strings in R. Separate a character column with multiple columns, strings, separate. That's not what we want. That's too complicated. That is way too complicated. How to convert a data frame into a vector multiple strings. Convert an object to a character string. ToString. Okay, so maybe it's ToString. Okay, let's just worry about getting this to a string right here. So ToString. Who'd have thought it'd be that? ToString. Okay. Okay, good. Whoa. Wait, is this what you're looking for right here? Alex, was this what you were looking for? Is this the output you want? Is that quick? Is sometimes the code is right there for you. So it's just turn it to a string. And then it's printing it also. If you want to just put it to the string like as the screen is one thing, you could do cat, and that will put it to the screen like that. So there we go right there. Yep. And if you just want it to print to the screen like that, it'll just print. And you could remove the separations. Probably, like if you don't want to have the separations, you could remove those probably. Let me try one last trick on that. And the biggest thing about this class is just helps you understand the structure of this. When you're welcome, Alex. Great questions. Because probably if we go to paste, I know we want to go to string. String remove. There we go. String remove. I should get better with my string remove and stuff. And there we go. So if you wanted like your numbers printed to the screen with just like this, you could do that. So notice the difference between this one right here and this one right here. So if you don't want the spaces, you can remove all those spaces. If you didn't want the commas, you could do a second string remove on it and remove all the commas. And so you can choose how you want this to look. Like you could remove the comma and then it would look like that. So however you want this to print out and like to print a sequence. So there you go. You could remove the commas, you can remove the spaces, and remove just removes one instance, remove all removes all instance. And I literally try to practice this stuff to help myself remember all these different things you can do. Because the quicker you can remember more things, the more options you have when you do code. It's all about knowing as many things as you can with coding. You're welcome, Alex. Great questions. Good questions. Now, here, let's look at this one last thing. With this all correlations, this is huge for 474. For 474, if we look at the all correlations function, so how do I need to put a good question, Jordan. What do I need to put in the if statement to only allow a single number? How do we evaluate how many numbers are in something, Jordan? How would we look at how many numbers are in something? Like, how could I evaluate that object X has one object in it and object Y has two objects in it? How could I look at this and see that object X only has one? What could I evaluate about object X to see how many objects are in it? How could I evaluate object X and look at how long it is? How could I evaluate how many objects are in it and see? Yep. Length of X and then equals 1, and then lengths of X or Y. There you go. And that is false. So you can, if you want it to be 1, you could do this. If you are seeing if it's not 1, you could do this. So if you're running an error message, you'd want to do is it not 1. So if the length of it, if someone enters in more than one value, so this would return the error if someone enters in more than one value. So if you're having an error message or something occur because the length is not 1, then you would want this to evaluate to true. You'd say that the length is not equal to 1. Does that make sense right there, Jordan? Great questions. And watch this. We're going to fix our all correlations here. We're going to go to all correlations and we're going to fix it. Gotta delete that. Okay, so this right here is how you can open up a function. I didn't know this for a long time, but you can open up a function with this, and we're going to override a function as all correlations 2. And now we're going to make our own all correlation functions. And so what we want to do is we want to see what someone puts in for sorted. So sorted can be right here. If sorted does not equal this and does not equal this, stop. Sorted is only supposed, oh yeah, okay. And type, okay, cool. So we're going to go here to if, and we're going to go if, I like doing it like that. Dr. Petrie and I code differently. Sorted is not contained in, and I'm going to go here, valid options. Valid options. So the valid options for sorted are none, and strength, and we got to be careful here, magnitude, and you can see right here, none, strength, significance, and we have to go here and put one more and double click. So these are the valid options, and we're going to see if sorted is contained in valid options. We could do nothing, and it's going to do nothing, else stop. And stop, we're going to say, pick a valid option. And there we go. So now we're going to rerun this with all correlations 2. We've now saved that to the global environment. And we're going to change this to all correlations 2. And we're going to do sorted and just add a few little typos in there. And look what we get. So now we updated the function Dr. Petrie wrote. And this is a really good help for 474. But does everyone see this code I entered into the start of this function? This code I added on to Dr. Petrie's function right here is going to take and create a vector of valid options that people can pick from for their all correlations. So these are the valid options I want people to pick when they write all correlations and they put in a sorted value. And so we're going to look to see if what they did for sorted is contained over there. And if it's contained over there, what will we do? What will we do if they pick a valid option? If they pick a valid option, what will this code do? Yep, Jordan. Yeah, this is the goal. Like understanding how we can change things. Like as you get better and be like, oh, I could update my functions. I could fix it. I could change it. You can change anything you want. You'd be like, let's make this work this way. Let's change this. Let's add in a warning message. And like, and so you could write, pick a valid option from, you know what? I have want to see one more thing. How long did it take Petrie to make all these codes? I think he took like a semester or a semester and a half off. He wrote so much code. And I need to talk to him more about this because he really wants to update his graphics, and I'm the one who works more with Plotly, and we want to make it so that all these plots you make would be Plotly made plots, and I'm gonna have to learn more Plotly. And I think he wrote the book, he wrote all the code, and if you look, all these codes are, I mean, if you think about this, a lot of it's repeating. Like, look at this. I'm not trying, Dr. Peach, amazing job. But you sit down, you start writing these things, and before you know it, like, look at this repeating here. But this is a for loop. So this is a for loop, a nested for loop with an if inside of it. And so, you just look at the structure of it. It's going to go through. Okay, so it's making the list right here. This is when it goes through and it uses the I and the j variable. So it's making, and he's creating a z outside of here as a kind of maybe a control for the loop. Okay, yeah, then the z is a tracking how many times the loop is done, and then storing into results. Okay, cool. So his z outside of here is, he starts z at 1 because it's going to store into results the first row. So the reason z is 1 is because when it runs this and makes all the correlations and all correlations, it creates the first row, and then here it goes to z2, and then it runs the loop, and then it'll change the variable. So this is the first variable changing, then the second variable changing, then the third variable changing, then the fourth, and it changes the variable here, like your first variable, and then it loops over all the variables inside of there. And then right here, he's got the different methods, core test method. So if this is this, so if the column, okay, he's checking the class of the column here to make sure he can run it. So this right here, good, let's see what Alex says. And then, so the class of the column is checked. And if the class of the column is checked, and he didn't put an else because you don't need an else, but he's checking to make sure you can do correlation on it before running it. And he's storing the core for the Pearson and the core for the Spearman. And then I guess at the end, he's only going to return, he's going to only return the interest they select. So here's where he's only returning the interest they select, and then he's sorting it. So he actually, what's interesting about this is, and so maybe his, like, I'm not trashing the code, but his code actually computes all the Spearman and all the Pearson every time it runs. So when the code runs, it actually computes Pearson and Spearman, and then it narrows down your list here to only your interest. So if is not interest, then he should be removing those in here. That's probably what he's doing. I'm just set difference. I was looking at the difference. Yeah. I know, just trying to read it and being like, and then he's only going here and he's getting, so if you look at this is the easiest thing to read. He's going to the results and he's only taking the selected, what you selected. So it's good naming conventions, and he's doing a union of what your interest is with what the set is, and he's taking only the things you selected, and then here's your results. And at the very end of it's going to be return results. So he's going to return your results, and he's going to sort it, and here's where he's sorting it. So you see he's using the order function, which we've learned. Remember how we go to here, results, I mean, he's ordering it by the correlation. So if you look at the magnitude, it's by the absolute value of the correlation. So that makes sense. Like, he's ordering it by magnitude, where strength is just ordered by correlation, which goes from most negative to most positive. Now, what we could do, watch this, is we could go here to order and go to decreasing equals true. And now, as long as I didn't write anything over this, this is the last thing I'll look at. I'll look at the next thing here. If we go now and do this and go to strength, now when we do this, the way the strength output will look is it's going to go from positive to negative. So I was able to change it, and we could put in strength. We could put in different strengths. Like, I could add in here as like strength, positive, strength, negative, and it would start with the most negative. I mean, it would take a moment to code, but you can just, I mean, I don't want to code it. It's just so much fun to like be like, oh, how would we do this? We would just go here to this if. We're going to grab this line of code. Let me see where this ends. Is this ending? That ends there. Okay, cool. So if this right here, okay, cool. And so if, no, we don't want, okay, we can take that one actually. If this, And let's go strength, pos, strength, negative. And so then we remove this off of this right here. And that's removed. I don't think I broke anything. Good, that's not broken. Okay, that looks good. And now we've got a strength negative. And now we go back up to here. And this should be strength pos. Do I have a capital letter on that? I got to see if it's capital or lowercase. That's very important. Strength negative, strength positive. Okay, cool. And then this should be strength positive, lowercase, as long as I didn't mistype anything. And then those are the options, and that should be good. Okay, now what we should have is I should be able to enter in here strength positive. And if you notice, this is by the strength being positive. Yep. See, correlation's highest to start, and correlation goes down. And I should be able to enter into here strength negative. And now, it says not a valid option. Did I not change my code to say that? Let me look. There's, it's capital. There we go, it's lowercase. And let me copy this. And this is why I always make only small changes. And that's valid options, right? Okay, there's that. And then we go back to here, we put in that, just perfectly spelled. And there it is. Yep. So just looking at this, it's not doing it. Last check. I got to put down this code in a moment. If sorted equals to strength negative and type equals both. It's got the both on there. And type does not equal both. Run the results of the... we don't want the absolute value. That's the reason. We don't want that. We want this. Order by this. Order by the results, the correlation, this. Okay, this is my last thing. I love coding. Okay, now it should do it. Did we finally do it? Why is it not doing it? I got 30 more seconds, that's it. If sorted equals this right here, and type does not equal both, then store into results the ordered results on correlation. The ordered results on correlations. Did I do this inside of an if? Well, we fixed one of them. And then it's still running the code. Move out my valid options. Let me remove out this valid option code right here. I just want to see if I get it to work. Well, it's still running, so it's... But the other one works, which is confusing to me. Well, the positive works. That's a positive. That's the fun of code. Yeah, exactly. No, and this is what you do is you just like learn how to edit code and like see, I need to make a positive linear heteroscedastic. This is similar to what we do, or I'm on the right track and am I using the sequence function to generate the plots? To make a positive linear heteroscedastic. Whoa, did you write this out? Whoa, this is awesome. Oh my gosh. This is so cool. Congratulations. This is really awesome. And nice job. You wrote in your vectors and everything, and then you added the vector. Wow, you are doing amazing things right here. I like this a lot. Let me hop over to an R script. And maybe you're just like me, because to me, it's just kind of fun to do this. Like, you made your vectors right here. We'll see how these vectors look. And you can always like look online for stuff and try to figure out how they're doing. An awesome job. Thank you, Andrew. And I mean, Alex, sorry. So as of now, I wouldn't know where to start these. I feel like this is... And both of your guys' names are like exact blue, so it's a little... Okay, let's see. Oh, the plots are going to get interesting. Okay, let me run all the plots. You don't need this... It resets the parameter flow of that tool one by one. Yeah, and so these are positive linear heteroscedastic, and you only need one of them, right? Yeah, those are perfect. Yeah, excellent work. And if you change the PCH or the CX, you can do that. And you can play around with these. But these are all positive linear heteroscedastic. What does the second one say for us to do? Let me look at the second one. So the first one, it says in the book, right? Oh, wait, positive linear heteroscedastic, negative nonlinear. Okay, so negative nonlinear. Let's see if we can do that. Like, see if you can beat me from doing this right here, like quicker. A positive. Oh, nice job. Negative nonlinear would be something like this right here. So when you think about this, let's just think. If we're making 20 points right here, the 20 points are going to go down, but they're going to slow down. So we need 20 points that go down, but start to decrease in the speed they go down. So we're going to start at a high y value. And then the x value for this is going to constantly increase. Like we can just do a constant, like the x value could just have a constant increase of x, but the y value needs to go down and start to slow down. Does that make sense, Alex? Like the y value when we write it needs to go down, but decrease in the way it's going down. And it could be like 20. So wait, we're starting at, the plots start at 10, right? The plots, let's look at the plot thing on it. Where's that plot thing? I'll go over to here. The plots go up to, I think they go up to 10. And I think your numbers kind of confirm it. Or no, they go up to 6. Do they go up to 6? Another 15, 20 minutes. I mean, feel free to ask a question, Jordan. Feel free to ask it. I mean, I just kind of, hang out. So here's the x coordinate. This needs to go up by like a constant amount. So we can do a sequence for that. So we can do a sequence going from 1 to 5, and we'll do like 10 numbers. Okay, so there's the x, and then the y for this needs to go down, but it needs to change the rate at which it's going down. And so the y needs to go down by a slowing rate. So we're going to concatenate 6, 5, 4.2, 3.5, 3.1, 2.8, not 28, that'd be horrible. 2.8, 2.6, 2.5, and then we could repeat 2.5. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. And so with this right here, 2-string, why can't I do 6-1? Let me see that. I'll look at that, Alex. And let me see if this works. Alex, I think this is super cool doing it this way. Like, this is not required. Oh, wait. Argument 6 is empty. What did I do? Which one broke? BY. Oh, is there... Oh, haha. Are there 6 elements in BYX? BY? There's 11. Uh-oh. We don't want 11. We want 10. We want 10 arguments. And sequence... Oh, sequence from 1 to... Wait, what's going on? Sequence from 1 to 6 by 10. Oh, haha. I don't know how to code. There we go. Here, let's take a look. Lots of questions. I love this coding stuff. There we go. Look at that. There is a relationship right here. So excellent work on this. And let me see right here. Alex's question is 2-string sequence 1, 6 by 0.2. Why can't I do 6, 1? You should be able to. Oh, and are you like printing these out and then doing them that way? So let me see what this produces. Okay, unexpected symbol. Oh, cover myself up. You should be able to do 6, 1. It says wrong by. Is it? Oh, you gotta do this. There you go. There it is right there. That's, oh, and then are you using that to copy it? Oh, so you can just write the sequence. Oh, because you wanted to like copy it. Yep. No, don't worry. Don't worry. That's very common. And then I think we have right here, is there a way to do, but instead of 0.2, do like a random number between, oh my gosh, that's such a cool question. Watch this. We might be able to do, that is such a good question. I don't know if this will work. I don't know if this will work. You could do 10 numbers maybe. Let me do this. From 1 to 100 by a random number, and from 1 to 5. Error in sequence by must be length 1. Yeah, I don't know of a way to make it. You would have to code your own. You would have to code your own sequence function that randomly does it. I could code that after this. I could code, like, you want something like this right here. So, and then you would want to take this and you'd want to go like, you'd want to go round. That's currently open. That's why it's mad at me. So you'd want to go to here to round, and you'd want to take whatever you get there and round this to 1. And so you would use these numbers right here. You round it to 0 decimals. Oh my gosh, we don't want that. So you'd want to round this to 0 decimals. So this code, so this code right here is how you could choose, and then just depending on how many decimals you want to do. But that code right there will take random numbers between 1 through 5, or you could sample numbers from 1 to 5. It would be the same thing if you did sample numbers from 1 to 5 and take 100 of them. And then, we could write a code that does like a random sequence, which randomly does it. That's kind of cool. Yeah, there might be better ways of doing it. There's probably quicker ways than writing all our own code. Let's look at Jordan's question right here. I remember for this question, I just plotted the points on the paper. Oh, wait, are you ready? Jordan remembers it. You sound like that. Is there any way to do... Wait, Jordan's. Okay, I've been working at number 6 on homework 4, specifically the logic argument example. Cool, let's hop back to that. Number 6, homework 4. Da-da-da-da-da-da. What? Oh, that's the wrong homework assignment. Here we are. Okay, so number 6. Chunk 6, not chunk 6. Number 6. Bottom heavy. Okay. So with the bottom heavy function right here, we're going to see if a vector is bottom heavy, if I remember correctly. And where's it at? Where'd you go, number 6? I am losing my mind. Here we are right here. And yeah, drop your code, do it. Write a function called bottom heavy that takes 2 arguments. X is a vector and n is an integer. The function should return a logical true or false. No quotes depending on whether the sum of the last n elements of the vector is equal to or larger than the sum of other elements in X. So no logical checks. So sum of this right here, we got this. You got it. And let's drop it in the chat. Okay, there we go. And so I think we're gonna go 1+ on the font. I like that right there. It's easier for me to read too. And I do that and it keeps moving me around on it. There we go. And so now, for example, x is a vector of this and n is 1, then the function will return true since 18, the sum of the last element is equal to or greater than 15, which is the sum of these elements. Okay, so if you look at how this code works, it's going to take the vector and it's going to tell us whether it's quote unquote bottom heavy. So what bottom heavy means is there's more of the data in the end of the vector of how many elements we choose, which n being the number of elements we choose, and there's only one element. Like if this was 5, would this be bottom heavy? So if this was 5 right here, would this be bottom heavy? Would we get a yes for bottom heavy right here? Would we get a true for bottom heavy on this? If this is the vector, if we just did n equals 1, would we get a true? Would that be bottom heavy, yes or no? No. And then would this now be bottom heavy, yes or no? We have to add up these two. False, exactly right. Great job right there, Jordan, 50 points. This is false because 8 and 5 add up to 13, so that is now greater than 7. So if you did n equals to 2, then you would get that this is bottom heavy because the end of the vector has a higher sum of the data than the start of the vector. So that's what we're evaluating. We're evaluating in n, which is the amount of values we're evaluating. So we're evaluating n amount of values. We're summing them up to see if the sum of those values is greater than the other side of the vector. So you could just do like 1 and this would not be bottom heavy, or you could do 2. So when you think about this, let's look at the theory here. So inside of here, we have a vector x. Let's change this back to what it was. And we've got a vector x. So we're going to take right here and just store this as x to check it. So the first thing we're doing is we're taking the tail of x for n values. Okay, so this should right here only return 18. And what's it not like? Tail of x for n values. NA is applied. Tail of... Oh, it's the n. Haha. N is not stored as 1 yet. Okay. So we have right here 18. Good. So that's doing what we want it to do. So that makes sense. That's working fine. And then we're just going to take the sum of it, which is what we want to do. That makes sense. And then we go here, and this is where code gets a little more complicated. Now we want, and I think you've done it. You might have done it because the inner part of this is taking the tail, which is the end of it, and then you're subtracting off. But here's the issue. The issue is you're subtracting off position 18. So this returns 18, and so think about this as just 18 right here. So that's subtracting off position 18. And so that is the issue right here. Now what we could do, so we can do this an easier way. As I think through these things, why not take, watch this. Why not take the sum of x minus the sum of the tail of x? So with this right here, we can get the sum of the vector, and we can subtract off of it the sum of the tail, and we'll put this in a parentheses right here to make sure it evaluates, because we don't want this to evaluate with this. We want everything right here, like this is x, and this is y, to evaluate this way. So always use your parentheses to your advantage, where you say this will evaluate, like if you want to be really super careful, you do that. And you'd say this over here on the left evaluates with the right. Does that make sense, Jordan? What I've done here is that I've just taken the full amount of the vector and subtracted off these, because that'll give me the other side. Like I'm saying, here's this. Well, let's find the total of this vector and subtract off this from it, and that'll give me the remaining portion. It's basically the complement. Yeah. No, and that's and so great. No, excellent work. Like, I'm so glad you guys are working on this, guys and gals, everybody, because when you come with a question, when you're like, hey, wait a minute, how do I get this to work? And your code is so close, and you can do it that way. The problem with subtracting off the positions is it's going to be like hard to find, because even if we did it like a which, we would get like, you could find things with the same position due to the same values. So even doing a which would cause a problem, because you would find the positions which are equal to those values, but then you could have a value in the tail that's equal somewhere else, and you'd subtract off those positions. So the which does not seem like the best way right here. A lot of coding is all logic and everything. It's all crazy. And this should return bottom heavy true. So this should tell us it is bottom heavy now. Yeah, we did it. We've got the bottom heavy function right here. We did it. And now all we do is turn to, I want to do it. I want to turn into a function. I want to do it. So now this takes x, it takes n. We've already got it written in here. We'll just ignore those things. Now what we'll do is we'll store logical. And that's just going to store a logical statement. We'll go to return. We'll go to logical. And we'll go right here. I need to practice. I've always got to make sure I can do these things, because my code, let's go to re-indent lines. And so that should, and we'll go here to bottom heavy, copy paste, your best friend ever. And then we should get true. Can you uncomment codes with this? Whoa. If anyone didn't see that, I'm using the block comment, and I highlight and unblock comment. Didn't know that till right now. Just thought, wait a minute, if I can block comment, can I unblock comment? And the answer is yes, you can, with Control Shift or Command Shift C. Faster you work, the better you work. So what is it about the for loop for that question? So now when you do the for loop, we're going to like go through different like spots. Like if we were to do 1, 2, 3, or 4, and let's just check. Sanity check's working. Cool. So now, because it wants us to do a for loop on this, right? Then initialize results, then use a for loop to determine the elements from 1, 2, 3, 4. The value in elements I should be the output of the bottom heavy when spots defined is used as the first argument. The second argument is equal to I. Print to the screen the average number of results close to this right here, as well as the first position in the results, which is true. Okay, so this right here is, we're going to do it on the spots. Leave the following interactions, find spots, yeah. And I think we're doing it on the spots data, right? Results. Yeah, on the spots, yeah. Okay. So we're going to use the for loop we're going to use this function in a for loop. And we want to store a vector called results. And we need to go here and go results and store into. Now, that just creates the blank vector as a blank space where we're going to store into it. Now, what do you think we'll be storing into? Like, just think like when we run this for loop algorithmically, what do you think will run this for loop? We'll store it into something when we run it. Like here, we'll do this right here. Let's grab, let's use the bottom heavy function. And the first time the for loop runs, it's going to run with the first. So we're going to go right here and do sunspots, or spots it's called. And we're going to go to spots. And that's the answer, basically. This is the steps of it, because this will pretty much answer it right here. So, you got it. And what did we just write? What did we just write? What do you think we just wrote? What do you think we just wrote? Because we just wrote something very important. Yep, we wrote the for loop, but we wrote the, what did we write of the for loop? 50 points, who knows? What did we write of the for loop? What did we just write of the for loop? We wrote the this thing. The what? What did we just write? Skeleton, 50 points right there. We wrote the skeleton. Because now, from now on, the for loop's just going to do this right here. That's all the for loop is going to do. And we can check to make sure it's working. And we can look at the results, and we're getting false. Eventually, it'll give a true. But that's the skeleton of the for loop. And so all we have to do is put that inside of a for loop, put the variable, put the vector it goes through. Done. So I'm going to leave that part. But the hardest, and if you notice, once again, when we wrote the function right here, we originally wrote this out, and then we just put it into the function because we were like, okay, this is what I want, and then we just returned it. Like this line of code right here was written, and so now, yeah. So hopefully, the better you learn how to code, it's literally like coding better takes less time. And I know that's like obvious. Like if you code better, it takes less time. But that's the hard part about it. It's like, how do you learn how to code better? You have to do these practices like don't write your for loop. And I'll make these mistakes where I'll start like shifting stuff and writing stuff, like, messing around with the functions. Like, so that's where I'm creating errors because one, there's things going on. I'm like, okay, what am I inside of? What's doing this? And you literally try to write, you make it work on one case. That's the deal with functions, is like, I made this work on this right here. So I have my vector, I have this, and it works. So now all I'm going to do is allow someone to input these values like I input them here. So now this runs. And then when I write my for loop, I get my for loop to work on one instance. And then all you're going to do is just change, this to write this. And I mean, this is literally 99% of the for loop right here. Like now I can just change the I and I can just do this. So this is literally the for loop, but running it manually. So that's the for loop, and then it'll just return. Yep. So this is, it just needs to go through the length of the vector. That's literally the answer. So if people know how to code this and you hear that, you'd be like, oh, I just need to put that in a for loop, put in the variable name, and put it through the length of the vector. But if you don't know how to code, that's going to sound like, nonsense. You're going to be like, what? Put it in the for loop, put it in the variable, and like the variable's already written for you. What is the variable in here, Jordan? What is the variable I'm using for my for loop? What is the variable I'm using for the for loop? You can answer it in chat, and you can leave it in the chat. What is the variable Brian's using for his for loop here? What is the variable I've decided for the skeleton to be the for loop? Yep. And then what do you think this for loop will have to go through? What will this for loop have to go through? This is where people make a mistake on this one too, is they put the wrong vector that it goes through, and it creates a bunch of weirdness. What vector will it go through? What vector will I go through as the for loop runs? You can put in chat, in the chat. They'll see it in the chat if they're watching. Which are like, yes, awesome. Thank you, Jordan. Yep, that's it. Yeah, it just every position. Because 1 through the length of spots will do it for every position. So we're going to check every position. And it's actually going backwards through it, so which is odd. And then when you want to find the first true, see, that's weird. Yeah, the first true, you have to like reverse it. You actually want to find the last one. So if you find the first like false and go one position before it. Wait a minute. When you're storing no, it'll do it. It's just weird the way this one is because it's not at that position, it's bottom heavy. It's that many positions from the back of the vector. If this had returned true right here, the last position would be the bottom heavy position. So if we get position 100, it's 100 positions from the back, it's bottom heavy. What's confusing you, sorry, it's the whole idea of bottom heavy and the number you get for this is a little confusing because if you get position 1000, that would tell you that position 2177 is where it's bottom heavy. So whatever you get, like if you get position 1, so it'd actually be 2178 because that'd be the 1000th position. So don't worry, they grade that one nicely. Finding the first true. So to find the first true, yeah, all you need to do is if you find, here I'll kind of explain it in words. You could just literally take this logical vector. Here's what you can do. Once you get this Here, watch this. I'll do this. Let's do something ridiculous here. See, I'm doing position 3000. That created a bunch of NAs, though. Ignore that this is creating NAs. Like, it created a bunch of NAs. But now watch this. There you go. That returns, what does witch do? It's a witch. Yeah, you called it. Yeah. And then what could you do to the witch? There you go. Yeah. Yeah. So the reason I went to position 3000 is I wanted to eventually get a true. It put NAs in for all the positions that I didn't evaluate. So you see, I was running my loop here, and then there's, like, if we were to look at results, positions that are not evaluated will have NAs in them. So if I go results, positions, whoops, wrong button. Boop. And now, oh yeah, out of dimensions. Yeah, I know. That's what's the point. What? Oh, ha ha ha. I was trying to do two-dimensional. Yeah. So this is where I evaluated these positions, and there's NAs and everything else, but this is where I ran. You won't get NAs for these. I'm doing it manually here. I didn't do the for loop, but there are trues right there. Like, I could go and evaluate one of these positions using my manual for loop right here. And now when I run this, you see there's a true there. So, but you wouldn't want to do this manually. You want the for loop to do it, and for loop will just do every position for you. So this is making good sense, Jordan? Yay! I think you're getting it. Great work. Lots of good coding, knowing how to do this, and understanding what it's returning. And Jordan, so like if Alex is still here and everything, has coding gotten a good bit easier? And Alex is doing a great job too. Like, so many people are like, makes sense, yep. And how do you feel like your coding knowledge has increased a good bit? Like, when you first started in had you ever coded before 320? Like, I'm not shocked when people, like, if you told me, yeah, I've been coding or I do this or this, I wouldn't be shocked. But then some people are like, never coded a day in my life before 320. I'm like, whoa. Like, that's what shocks me, is when people say, like, I've never coded a day in my life. Yeah, one more thing. Go ahead and ask Alex. No way. I mean, no problem. No way. No, you didn't. Yeah. And I think you're at a very impressive level right now. Like, I think, and this is what I love to see with the students, is like, I think you're really getting there. It is absolutely easier. Awesome. Here, I'm going to disappear for a second. I'll still be here. I'm still here. Here, I'll look at this, Alex. Like some real quick. Let me see here. Alex, which question did you have? I think I got a strong relationship whose strength would be well modified by Pearson's for D. Yeah. Oh, yeah. Let me look at that. Pop back on the screen here. Let's look at this. I bet you did. And here, Alex, I'll drop you the other one. I'll drop you that other vector here real quick, since you've been here working hard, working along. And oh wait, do it the vector. Okay, wait. Yes, that is perfect, Alex. That is perfect. And I'll drop you the other code here in a second. Oh, time to go. Bye, everybody.